Hi everyone and welcome back to PrepFusion. So this will be the revision with P-PYQ, R-PYQ series of network theory, the AC part. Okay, we will not do the DC part because DC part was taken by Himanshu sir. So I will not be, because I don't have the content right now prepared to do the DC part, and I think the amount but of depth that he has taught, that should be more than enough for you to crack anything in DC. In EC as well, I've covered everything, mostly what is possible, but sometimes it happens that EC aspirants, they might feel like they don't want to study the AC part because it is very less question comes. Yeah, 2 to 3 marks, sometimes 2 to 3 marks comes with the AC portion. DC portion is the important portion because after that they directly go into the analog circuits. So that's why maybe few EC students might feel like I have to watch 25 hours of content, that will be a bit too much. So this video will be around 10 hours of content, and in this R-PYQ series, in this video, I will cover every single concept. Okay, I will not skip any concept. Okay, I will try to cover every single concept of all of this chapter: AC, phasor, locus, resonance, complex, network theorems for AC and two-port networks. But I cannot guarantee you that after doing this, you will be able to solve all the questions. I cannot lie to you, right? Because of course, if I have already a 25 hours course, and that is completely free, right, on YouTube, that is all completely free, you can check out the playlist. If I already have 25-26 hours of course there, right, uh, uh, and if I am compressing it to 10 hours, 8 hours, right, of course there will be some difference. I cannot lie to you, but what I can say to you, you will be more confident after watching this marathon than you were before, and all your concepts will be revised. If you have studied a bit previously, all your concepts will be revised. Your brain will work much faster. I will also obviously explain few tricks how to remember the formulas, what are the important portions, what are not that important, though all those things will be covered. Okay, so definitely I can say, if you watch this video, you will feel more confident and you will be more prepared for your gate 20 gate examination, right? If you also have not prepared the EC part, right, that's also fine. You can watch this video, that is also fine, but I cannot guarantee, I cannot assure you, you will be able to solve all the questions. Okay, that I cannot guarantee because I cannot lie to you, right? Of course, if I'm reducing the content to 8 hours, there will be some drawbacks. I think the content for AC part is around 30 to 35 hours, something like that, right? So with that, I want to say, watch the video fully, solve all the questions, make sure you are solving all the questions, right? Whatever questions I'm showing, make sure you try it out by yourself, then you see my solution. Initially I will explain the theory, and after finishing the theory I will go into the questions. And yeah, that's all. Basically I will pick the most important recent question from gate 2020 to 2025 from the branches IN, BM, EC and EE, right? So IN and BM will work as a refresher because I know that most of the aspirants only solve their own branch PYQs. You will not solve other branch PYQs. So if you so those will be new questions for you. So I want you to attempt those questions and tackle those questions, okay? So that you will be more confident. So with that, I want to wish you all the best, and yeah, let's start with phasor diagram. Let's start with the R-PYQ series of network theory, the AC portion. So in AC portion, we will discuss phasor, locus, resonance, complex powers, network theorems, and two-port networks. And don't worry, even if you don't have any prior knowledge, I will try to take those students as well without any prior knowledge. In this single video, complete AC analysis will be completed. Okay, but of course, those who have studied the full course for me, they will understand how comprehensively I have gone there. Maybe I will not be able to go that much comprehensively in this R-PYQ series, but I will try to cover every concept. I will not skip any concept. Okay, that will be my priority. I will not skip any concept. So first of all, we'll discuss about phasors. Before understanding phasors, we have to understand sinusoids. So I am 100% sure that you have seen a waveform like this in your college days, right? This is nothing but a sine waveform, okay? And a sine waveform, if I zoom in a bit, this has two properties. One is the peak value, okay? What is the peak? It is known as the peak or amplitude of the sine wave, peak amplitude of the sine wave. Another one is the frequency. Frequency is defined by this omega term. Another term is there, that is the theta, that is known as the phase shift, that is known as theta, okay? So we will understand these three terms slowly. So what is Vm? Vm is the peak amplitude of the sinusoid. Basically, every sinusoid will have a positive peak and a negative peak, okay? It defines basically how much maximum the sinusoid can go or minimum, okay, that particular sinusoid, okay? The peak value of the sinusoid, like upper peak and the lower peak, okay, minus Vm plus Vm. Sinusoid varies from minus Vm to plus Vm. and omega is the angular frequency in radian per second. What do we mean by frequency? Frequency means in a single time period, like how much does this wave take to complete a single time period. Okay, so let's say currently this is in 2 pi, you will not understand it. So I might have a different waveform here, here, right? So let's take example that my sine wave takes 1 second to complete a cycle. Okay, so it will cover complete cycle in 1 second. So in 2 seconds, how many cycles of sine wave I will get? 2 cycles, right? 2 cycles. In 3 seconds, how many cycles of sine wave I will get? 1 cycle, 2 cycle, 3 cycle. Now what is frequency? Frequency is just the inverse of it. Frequency is cycles per second. Per second, how many cycles I am getting? Per second, here in this case I am getting 1 cycle. In a second I am getting 1 cycle. Let's say my time period of the sine wave is 2 seconds. Now what will happen? Now if the time period is 2 seconds, that means I will complete a whole cycle in 2 seconds. Now what will be the frequency? Frequency means per second how many cycles I am getting. Cycles per second. If you see here, this per second term is there, right? This is angular frequency, that is in radian per second, but in hertz. Hertz is basically the inverse of the time period. Okay, then I will define the angular frequency. So per second how many cycles am I getting? So this is 2 seconds now, right? So half cycle will be 1 second. So in a second I am only able to cover half a cycle. I am not able to cover full cycle. So what is the frequency? Frequency is half. So that's why you will see frequency is 1 by time period, that is 1 by 2, that is 0.5. Same like whatever I have discussed physically and mathematically also I am getting the same value. If the time period is 0.5 seconds, if the time period is 0.5 seconds, then what will happen? Then I will cover a complete cycle in 0.5 seconds, right? In 1 second, how many cycles I will cover? 2 cycles, because 0.5 for the first one, 0.5 for the second one, 2 cycles. Okay, so now what is the frequency? Frequency is cycles per second. How many cycles am I able to cover in a second? 2. So what will be the frequency? 2. Same, I can apply the same formula here. Like my f will be 1 by t, that is 1 by 0.5, that is simply 2. Okay, that is what I mean by frequency. What is omega? Omega is angular frequency, because frequency, unit of frequency is hertz. Okay, unit of frequency is hertz. Omega is defined as radian per second. Okay, to convert anything into radian, I just need to multiply it by 2 pi. So it will be 2 pi into f. That's it. You have to remember this. This is important actually. You have to remember we have to multiply 2 pi into f to get omega, and omega will be placed here. Okay, normally omega will be placed. Okay, and it depends actually whether omega will be placed or something else. I will discuss about that, don't worry. Now what is theta? Theta is the phase angle in degrees. So we have learned about Vm, we have learned about omega. Now let's discuss about theta. Theta is the phase angle in degrees. So currently let's assume theta is 0. If theta is 0, my waveform is Vm sin omega t. This is the waveform for Vm sin omega t. Now if I add a phase shift, right, like this, Vm sin omega t plus 90. What does it mean? At omega t equal to 0, it is sin 90, right? Sorry, this should be minus 90, sorry. Let me add, negative means lag. I will explain, don't worry. Minus 90. So let me put omega t equals to 90. So at omega t equals to 90, it is sine of 0. Sine of 0 is what? 0. At omega t equals to 180, it is sine of 90. So when my omega t is 180, I am here, right? Omega t is this in radians. For now it is in radians. The unit of omega t is radian, because your what is the unit of omega? Radian per second, right? And what is the unit of t? T is seconds. So radian, I am multiplying radian with radian per second. Sorry, I am multiplying time second with radian per second, right? Omega. So second will get cancelled. Only radian will be left. It is also known as the argument. Okay, this theta is also sometimes known as the argument. Okay, so the unit of omega t will be in radians. So omega t, like this is the x-axis, and x-axis is basically the omega t axis. So when my omega t is equals to 90, that is pi by 2, in radians it is pi by 2, then I am lying here pi by 2 minus 90, or otherwise you will get confused. If it is in radians, right, I should not write here degrees. You cannot, let's say I have 1 Newton of force and I have 1 kg of mass. Can I add these two quantities? No. So you should actually never do this, like and because we do this every day, so that is understood by us. But always add quantities which are of same units. Don't add quantities which are of different units. Okay, just give me 1 second. So here if omega t is in radians, so this also should be in radians. So let me write pi by 2. Pi by 2 is in radians, right? Pi by 2 means in degrees. What is pi by 2 in degrees? 90 degrees. I hope these things are shouted by you. Okay, pi by 2 in degrees is 90 degrees, right? So if omega 2 is pi by 2 at x axis, that is I am lying at pi by 2, my point is pi by 2, then what will be the y value? Y value will be sine of 0, because pi by 2 minus pi by 2 is 0. So it will be 0. So that's why this is 0. Okay. Omega t equals to pi, that is I am lying here. Then this is pi minus pi by 2, which is sine 90. Sine 90 is the highest. Sine 90 is 1. So sine pi by 2 is 1, right? Sine pi by 2 is 1. That's why Vm is also there. That's why I'm at the highest. So basically this term, right, theta, it will either delay the waveform or take it forward. I mean, delay it or take it forward like this. Lead the waveform or lag. So this actually is called as lag, which we will discuss obviously in AC. That is what we discuss. So from the reference waveform, this second waveform lags. From the reference waveform, this third waveform leads. Okay, we will discuss about what is lag, lead. Don't worry, this is just the starting. Don't worry about this. Okay, that was about the sinusoid. Remember, what are the units? Unit of Vm will be volt. Unit of sine omega t plus theta, this will be unitless actually. Here I have shown you voltage waveform, it can be a current waveform as well. This sine omega t plus theta will be unitless. There will not be any units of sine omega t plus theta. Okay, because I am multiplying a unit quantity like Im or Vm, then it automatically gets converted into unit, because let's say I am multiplying 2, which is unitless, into 1 Newton. So it will be what? It will be simply 2 Newton, right? If I multiply 1 meter into 1 meter, like area, right? I am calculating area. It will be 1 meter square. So units are also getting multiplied. Okay, I hope you remember these basic unit things. So Vm will be in volts. The amplitude will have a unit. This will not have a unit, but inside terms will have a unit. Omega t. Omega, what is the unit of omega? Radian per second. What is omega? 2 pi f. What is the unit of f? Per second or hertz. The unit of f is per second or hertz. What is the unit of theta? The unit of theta will depend on the unit of omega t. How? So here I have told you that omega t is in radians. Sometimes what will happen, they will just give you this waveform, Vm sin omega t, and they will say omega t is in degrees. Then here, right, in the x axis, everything will be in degrees, 90, 180, 270, 360. So don't get scared. Don't get scared. What they have done, they have just simply converted the radians into degrees. I hope that you know how to convert radians into degrees, right? How to convert radians into degrees? Simply, I know pi is 180 degrees. So 1 radian will be 180 by pi degrees. Okay? Am I correct? Yeah, 180 by pi. So here, if I multiply 180 by pi, what will I get? 90. If I multiply 180 by pi, what will I get? 180, right? So that's what they have simply done. So sometimes it is the x-axis unit will be in degrees. So don't get scared. If x-axis is in degrees, and then this value also will be in degrees, this value also will be in degrees. Now sometimes your x-axis is in time. It is in time. So if it is in time, right, then what they will do, then your sine, it will be 2 pi upon t into 2 pi upon capital T into t. Why? Because what was your omega? Do you remember what was your omega? Omega was 2 pi f. What is f? 1 by t. So what I have done, I just simply cleverly replace my omega with 2 pi upon t. That's it. I have replaced my omega with 2 pi upon t. Okay, because f is 1 by t. So I have just replaced it over there, so that my x-axis can be now time in seconds, because maybe they are comfortable in time. So it can be in time, unit can be in time. Now this time and this time is there. So x-axis can be in time, it can be in seconds, it can be in degrees, it can be in radians. So these three are the main units in which they can give you the question. Okay. Now one more key point I want to say, don't worry, I will explain what is my RMS voltage later on. My VRMS will be equals to Vm by root 2. What is VRMS? Don't worry, I will discuss about this in complex power. For now, just take my word, okay, the RMS value of any sinusoid always will be the 1 by root 2 times the peak amplitude. The RMS value of any sinusoid will be 1 by root 2 times the peak amplitude, okay. So that is the case over here. Now let's discuss about few key properties, okay, of sinusoids, between sinusoid and cosine. So I hope you remember what is cos and sine. So I always tend to forget this relation, right? This I don't like. I always tend to forget this relation. I'm not able to remember this relation. So how do I remember it? I remember it vectorically. So if you remember, when you used to draw the graph, right, for a circle, the cos theta, r cos theta would have been the x-axis and r sin theta would have been the y-axis during our JE days or school days, right? So that's how I will remember. So my x-axis will be cos omega t and my y-axis will be sin omega t, but it will lag. Okay. Don't worry, these are also phasors. I will explain what is my phasor, but for now just understand that cos omega t will lie in the reference and sin omega t will come in the bottom. Okay, just draw these two vectors, just draw these two arrows, okay, and with this you are done. Just draw these two arrows and with this you are done, basically cos omega t and sin omega t. Okay, now what you will say is, one more thing you remember, that whenever we used to move in the clockwise direction, our angle is added, right? It is positive. Whenever we used to move in the anti-clockwise direction, our angle is negative. I hope you remember, right? So like in graph, right, in graph, whenever we used to move in the clockwise, or if you don't know, now you know that whenever we will move in the clockwise direction, right, from, let's say, from this negative y direction, I'm moving into positive x. So how much angle have I moved? Plus 90. From positive x to negative y, I'm moving in the clockwise direction. Now how much angle I have moved? 90. But what is the direction? Clockwise. So it will be minus 90. It will be minus 90. So let's say I'm lying here, cos omega t. If I want to come back to this point, it will be what? Cos omega t, if omega t is in radians, minus pi by 2. Okay, cos omega t minus pi by 2. So if I'm lying at this point and I want to come to this point will be what? With respect to cos omega t, it will be cos omega t minus 90, and this point is actually equals to what? Sin omega t. So this is one relation, cos omega t minus pi by 2 is sin omega t, or other way around, how can you remember? That if I'm lying in this point, what is the value of this point? Sin omega t. I want to move in the clockwise direction. I want to move in the anti-clockwise direction, 90. So if I want to move towards the cos omega t direction, right, from sin omega t, what will be the value here? So I have moved 90 degrees. So this will be sin omega t plus 90 or plus pi by 2, because I have moved in the anti-clockwise direction. So this point value will be sin omega t plus pi by 2. And what is the actual value of this point? Cos omega t. What is the actual value of this point? Cos omega t. Okay. So from this I can say that, yeah, cos omega t is sin omega t plus pi by 2. So all this we are doing just to remember this thing. Okay. If you can remember it, well and good for you. But sometimes I tend to forget it. So that's how I remember. I draw this cos omega t. Okay, I remember x-axis will be along the cos omega t direction and y will be in the bottom. Sin omega t will be in the bottom. As soon as I have drawn, now I know all the relationship between the cos omega t and sin omega t. Either this relation will follow or this. Both of them are saying the same things. Both of them are saying the same things. They are not saying something different. Okay. This was about the relation between cos omega t and sin omega t. Now if I have two sinusoids, one is cos omega t, one is sin omega t, I can actually combine these two. I can actually combine these two into a single cos or single sin. Again, don't remember this. Okay, that's why I have told you, don't remember, right? Just take help of the diagram. Okay, take help of the diagram. So let's say that this is my cos, right? This is my sin, because sin is in the negative y, cos is in the positive y. So let's say I'm adding two, like 3 cos omega t and 4 of sin omega t. So what is the amplitude of cos? 3. What is the amplitude of sine? 4. Now what will be the, like these two are vectors. Now you just simply do the vector addition. So this is 90 degrees, right? So what will be the, like I can draw the resultant vector, right? And this is 4 units, this is 3 units, right? What will be the hypotenuse? 5. 3 square plus 4 square whole under root. Hypotenuse will be what? Hypotenuse will be simply 5. This will be my hypotenuse. Under root 3 square plus 4 square, which is simply equals to 5. I hope there is no doubt in this. So hypotenuse is 5. That means my amplitude will be 5. Remember, if you are writing 3 over here, that is the peak value, and you are putting the peak value over here, then the resultant also will give you the peak value. Don't worry, this will be cleared once we'll discuss about RMS and peak, right? For now, there is, you just assume that there is one term named as RMS. I'm not explaining you what do we mean by RMS. Okay, so there is this huge confusion. I will clear that confusion. If you are writing peak here, like if you are taking the peak values here, right, then your resultant also will come out to be the peak. So this resultant 5 is the peak of the resultant. If I am writing the peak here, so peak of the resultant I have got 5. What about the phase angle? What will be the phase angle? So phase angle can be with respect to two things. Either you can write with respect to cos, or you can write with respect to sine. And remember, these two must be same frequency. If they are different frequency, this will not work. Okay. So if let's say if I am writing with respect to cos, so I need to calculate phi 2 because my resultant will lie here. I hope you know vector addition. Right? So my resultant will lie along this. I just need to calculate phi 2 so that I can understand how much do I need to move from my cos to reach to my resultant. So what will be phi 2? Phi 2, I hope you can simply calculate the angle. So it is tan inverse y upon x, right? Tan inverse y upon x, that is my phi 2. So it is tan inverse y upon x. Y is what? 4. X is what? 3. What is tan inverse 4 by 3? You have to remember this. It is 53.13. It is a very handy value. You have to remember. What is phi 1? Again, in this triangle, what is my x? X is this one, right? Because what does define x? X means to the base for this triangle. So angle is this, right? So the angle should touch the base. Here, what is my base? Base is this length, right? Where my angle is touching the side. So this length is 4. So for this case, your phi 2 will be tan inverse 3 by 4, just the reciprocal. How do you remember? It will be 37 or 36.86. How do I remember these values? Simply, you understand this, that 4 by 3 is 53.13, right? So the reciprocal will be just 90 minus this. It is just the opposite, right? It will be 90 because this whole angle is 90, right? If I know phi 2, I will be able to find out phi 1. What is phi 1? Phi 1 is 90 minus phi 2. If you remember this value is automatically inside your brain because this value will be 90 minus this. Okay, because this whole angle is 90. Okay, these are the tricks that I am explaining you. So like I'm not just teaching you a subject, right? I'm teaching you for GATE examination. Okay, I'm not teaching you just AC analysis. I'm preparing you for the entrance examination. Okay, so in other institute you will see like they will just teach you the subject. They will not go into the concept that will help you in other subjects. But this thing, right? This thing will help you everywhere. So I'm trying to teach you every single thing that is feasible in this short span of time. Okay, so this is 3 by 4 now. This is 53.13. This is 36.86. Okay, now, so if I am writing in terms of cos, so the peak value will be 5 cos now I'm moving in the clockwise direction, so I have to subtract from cos. This is cos, right? This is cos. I'm moving in the clockwise direction, so I have to subtract my angle. How much? 53.13. This is in degrees, right? Omega t is in radians, then this also will be in radians. If omega t is in radians, this also will be in radians. How can you convert this in radians? You just do pi by 180, just the inverse. You multiply pi by 180, this will be converted into radians. But you if you say, sir, I want to write in terms of sine, how will I write in terms of sine? We can write in terms of sine. So from sine, I need to reach this point. In which direction I have to move? In the anticlockwise direction. If I have to move in the anticlockwise direction, so I have to add the angle. If I have to move in the anticlockwise direction, I have to add the angle. So this will be what? Again, the peak value will not change. 5 sine omega t plus, because I am moving in the anticlockwise direction, phi 1. What is phi 1? Phi 1 is this 36.86. Like without this, right, you could have directly done it actually. If you have found out this cos omega t minus 53, you can use this formula, use this relation, you will get back the same value. What is cos omega t? It is sin omega t plus 90. So if I add 90 here, I will get to sine. So the same thing is happening, right? Cos omega t is sin omega t plus 90. Cos omega t is sin omega t plus 90. So cos omega t, basically whatever is inside the angle, inside the brackets of cos, right? If I want to write it in terms of sine, I have to just add an additional angle 90. That's it. It will be sin omega t plus theta plus 90. Okay. I hope now finally this relation is totally clear in your brain what is actually happening over here. So now let's discuss about the phase shift. What do I mean by phase shift? So a phase shift refers to the displacement of two sinusoids in time or in x-axis basically. Okay. So let's say, like I have already discussed about this. This is my reference sine wave. Okay. V1 is my reference. So you have to always choose a reference. Either the reference will be, like I have told you, you have to choose reference. Either the reference will be given to you, or there is a general theme that we follow to choose a reference. And most cases reference will be given to you in the question. You have to be smart enough to understand what they have given me as the reference. Okay. So here we are assuming that my V1 is a reference. Okay. So if V1 is a reference, what is the phase shift between V1 and V3? So I see that the peak of V1 is coming at pi by 2, the peak of V3 is coming at pi. So the phase shift between V1 and V3 is pi by 2, because it is basically, it defines the either shift in the zero crossing paths or peak. So the peak of V3 is coming after pi by 2 of V1, right? And peak of V2 is coming before, it is coming earlier, right? Before V1 pi by 2. So there is a term actually, phase shift is pi by 2. Phase shift is pi by 2. But how do I explain this plus and minus sign? Because this V3, right, it comes later. That's why there is negative sign. V1 comes, V2 comes earlier. That's why it is plus sign. But how do I explain this negative and plus sign? So we explain this negative and plus sign with lead and lag. Lag basically means it is lagging from the reference, so it is coming later. V3, peak of V3 is coming later. Peak of V3 is coming later than V1, and V2 is leading. So that's why I have written here V2 leads V1 by pi by 2 or 90. V3 lags V1 by 90 or pi by 2. So one more thing is there, that is what I mean by lag. Lag means the peak of the waveform will come later than the reference. Lead means the peak of the waveform will come earlier than the reference. Now, a very, very important point where the most of the students get confused is they assume that lag means the waveform V3 will come after V1. No. No. So let's say I have this waveform here. Okay. This is my V1. They simply understand if V2 lags V1, they will say that okay, my waveform will start from here, that's it, by 90. No. The waveform is actually here. Waveform, both of them are present already. Before t equal to 0 or somewhere, they are present. Both waveforms are running. But simply the lag basically means that the peak comes later than the green waveform. That is what it means. Nothing else. It does not specify that when the waveform has started or no, nothing like that. No. It just specifies regarding the zero crossing point or maximum minima peak points. Okay, both are saying the same thing. Either you take the zero crossing points or the peak points, you will get back the same answer. Okay. So please don't get confused by this point that lag means the waveform will come later, lead means the waveform will come earlier. No. Lag means the peak of the waveform will come later than the peak of the reference waveform. Just the peak. okay, not the actual waveform. Actual waveform may start at minus infinity, I don't care. Okay, so if you have enjoyed this point, if your confusion has been cleared, put a hearts in the comments below and let me know. Okay, now this was about the lag, lead and phase shift. Now let's finally come to our actual topic, that is the phasor representation. Let's come to the actual topic, that is the phasor representation. So our main target is to not every time write this 5 sin omega t, 5 sin omega t plus 90. It is actually bit hectic for us. So what we do, we convert our sinusoid into a phasor format. We convert our sinusoid 5 Vm sin omega t plus theta into phase format. Okay, so which has a theta angle and Vm. So what is theta? Theta is the phase angle with respect to a reference. Let's say this is Vm sin omega t. First of all, whenever you are converting into phasor, you have to identify your reference. In this case, our reference is sin omega t. That is what I have written over here. My reference is sin omega t. So with respect to sin omega t, what is Vm sin omega t? I have to multiply a Vm here and I have to add another phase shift of plus theta. So that is what I have done. So this is my reference. Reference in phasor format is 1 angle 0. So to get to Vm sin omega t plus theta, what do I have to do? I have to multiply Vm. So that's why this is Vm. And I have to add a phase shift of theta. That's why this is theta. That's it. That's why this is theta. Okay, that is my phasor. Now, this is my reference. Now what will happen? Let's say I have another waveform, Vm. So my Vm sin omega t plus theta. Plus theta means, let's assume the theta is greater than 0, right? Theta is positive. Let's assume the theta is positive. Theta is not negative, right? Theta is positive. So where will I lie? I will lie somewhere around here. So I'm multiplying Vm, right? Vm, so this length of the vector will be expanded. It will be somewhat more than 1, or I don't know what is Vm. Vm can be less than 1 as well, more than 1 as well. So this will be Vm angle theta, because I have rotated in the anti-clockwise, because theta is positive. Now let me make another waveform, Vm 2Vm cos omega t. What is 2Vm cos omega t? So 2Vm cos omega t, what do I have to multiply with the reference? I have to multiply 2, right? I have to multiply 2. 2Vm, I have to multiply 2Vm. What else? What is the angle actually? What is angle? So we know my cos omega t is here, right? Cos omega t is here. This is my cos omega t. My sin omega t is here. Sin omega t is here. Now this is my waveform that I want to plot in the phasor, 2Vm cos omega t, right? So I have to write this cos omega t in terms of sin omega t, because my reference is sin omega t. So I have to write in terms of my reference. So how much do I have to move from cos? It will be what? From cos I have to move 90. Or let me do it like this, that how much do I have to move from sin? From sin I have to move plus 90. Sin omega t plus 90 will be equals to cos omega t. So simply I have to add 90 with the angle, then I will get my sin. So I will add 90 here. So this will be simply 2Vm sin omega t plus 90. Okay. So now how much do I have to move with respect to the reference? So let me bring this here. I hope you can see it. Let me reduce the size. Now how much do I have to move with respect to the reference? I will come back to these points, don't worry. I have to move 90 degrees. From my reference, I have to move 90 degrees in the what? In the anti-clockwise direction, because it is plus 90. So this will be plus 90. So this will be, now what will be the amplitude? As amplitude is double, so this will be actually very large. Length is represented by the amplitude. This phase shift is represented by the theta. Okay. So 2 Vm is the amplitude and the angle is plus 90. So that's how I represent. Now, if a phasor basically, that's how I will represent a sinus chart. Now, one thing is there, that one important information about the signal is lost here. Can you identify what is the information? I have already written it. The information about omega is lost. So once I convert, you see there is no omega term. There is no frequency term. Where did it go? Where did the frequency go? The frequency is actually hidden. So what we assume is all these vectors, right, are actually rotating in the anti-clockwise direction because it is plus omega t, in the plus omega t, right? So when omega t is 0, this will be 90. When omega t will be some, let's say 30 degree, this will be 120. Then again, when omega t is 50, this will be 140 and so on. So basically what is happening, with increase in omega t value, these angles are also changing. So what we are assuming is that all the vectors are actually rotating at a speed of omega. All the vectors are actually rotating at the speed of omega, but the relative angle between them will not change because all of them are rotating with same speed. It is same as, let's say I have two boys, Anish and Himanshu. Okay, Himanshu or Anish is moving with a speed of 2 meters per second. Himanshu is also moving with a speed of 2 meters per second. The distance between them is 5 meters. The distance between them is 5 meters. So if both of them are moving with speed in the same direction, both of them are moving in the same direction with a speed of 2 meters per second, the relative distance will not change, right? Like this, right? If both of them are moving in the same speed, right, the relative distance will not change. Yes, their initial position, their actual position will change, but their relative distance between them, right, will not change. It will remain constant. Same is happening over here. All the vectors are actually rotating with the same speed, so their relative angular displacement is not changing. That is the advantage of phasor. So our task was to not write every time this, right? This is hectic for us. To represent this in a much more easier format, to do calculations, complex calculations, because you see, right, you have seen doing this was much easier than this. Remembering this, there is a formula. I hope you have seen this formula. Remembering this is difficult. Doing this is much easier for us, right? We like things which are in pictorial format. So that's why we had to find a way. So that's why it is called a rotating vector. That's why it is called as a rotating vector. I hope now the point is clear why it is called as a rotating vector. Okay. Now, one more important point. I have told you that frequency of about omega gets lost. So if you have to come back to your sinusoidal form, you have to see your reference, because everything is linked with a reference. If you want to convert this into phasor format, you have to take help of the reference. If you want to come back to my sinusoid format, what I have to do? So this is 2 Vm plus 90, right? So with the reference, the amplitude I have to multiply, that is 2 Vm. So this will be 2 Vm, and the angle I have to add 2 Vm sin omega t plus 90. What is sin omega t plus 90? Cos omega t. So it is 2 Vm cos omega t as we have written over here. So to come back to my sinusoidal format, to go to my phasor format, in both cases you will need the help of reference. That's the importance. That is the importance of reference. Okay, and trust me, no one will explain you all this. They directly move into questions in phasor. They just say देखो phasor है, AC है, solve करना होता है, बस हो गया, vector phasor होता है, rotating vector होता है, ये बस हो गया, खत्म. I hope you understand all these things, right? I know you have studied from somewhere else. Phasor rotating vector होता है, हो गया, खत्म. Now I hope it is clear what do I mean by a rotating vector. Now as the information about omega gets lost, I cannot use phasor to in the same phasor diagram of different frequency components. That is a disadvantage. That is a disadvantage. Let's say this is sin omega t and this is cos 2 omega t. No, I will not be able to represent both of them together because their speeds are different, right? Their speeds are different, their distance also will keep on changing. So I cannot represent them in the same phasor diagram. That is the disadvantage of phasor. We will learn this in the next few slides. Now one more thing, is there. As I've mentioned, there is a term known as RMS. RMS is the root mean square value. How to calculate RMS, I will discuss about this in the complex power chapter. But for now, I have told you to remember that your RMS of sinusoid will be Vm by root 2. RMS of sinusoid will be Vm by root 2. Now there is this huge confusion that when I convert my phasor, like when I convert my sinusoid into phasor, what shall I write here? Should this be the RMS? Should this be the peak value? Now the answer to this is both are applicable. There is no problem in writing any one, right? But by default you will choose RMS. So here I have chosen peak, right? But by default you will choose RMS, that is Vm by root 2. You write here Vm by root 2. But make sure once you're coming back from phasor to reference, make sure you remember that this value, right, is not the peak value, this is the RMS. So here what comes? Peak value. So again you have to convert this back into peak and then write. Just like, let's say I want to write the RMS format of this, it will be Vm by root 2. So here this will be, if I want to write, like currently we have written the peak value, okay, with peak value I have everything is clear. Now I want to write the phasor in RMS format. So nothing will change, phase angle will not change, just this will be Vm by root 2 angle theta, that's it, Vm by root 2 angle theta. And here also I will write Vm by root 2 angle, this will be Vm by root 2, this will be simply Vm by root 2, that's it. Now once you come back to your sinusoid, remember, because this is RMS, right, because this is RMS and I know Vrms is peak value by root 2, right? So what will be V peak? V peak will be root 2 times Vrms. Let me write over here itself, right? Vrms is V peak by root 2. So what will be your V peak or Vm? Vm will be root 2 into Vrms, okay? So that is the case over here. So that's why where is it? Yeah, here. So that's why once, like this is Vm by root 2, once you will come back to your sinusoid, you have to multiply another root 2, right? So if I multiply Vm by root 2 with root 2, it will be Vm, because I have to put here, right, this is fixed, this should always be the peak value, whatever is in front of the sign, this should always be the peak value, okay? I hope that part is clear. Just you have to multiply and divide another root 2, that is the additional task that you have to do for RMS, okay? So yeah, those things are shorted, those things I've explained. Anything else is left over here? No, most things I've explained. So here, right, same thing. So now I can actually write my other waveforms in terms of my V1 waveform in phasor format. That will be much easier for me. So let's say I have a V2 that is actually in anti-clockwise direction, 90 degrees from V1, that is my reference, and I have another waveform V3. So I have actually taken these three waveforms. So my V3 actually, what? V3 lags V1. So if it lags V1, there is minus 90, right? Minus 90 means clockwise. So that's why you see V3 is in minus 90 with respect to V1, and V1 is plus 90 because V1 is plus 90 because it leads. Sorry, V2 is plus 90 because it leads the reference. So if I assume V1 to be my reference, so V2 will lead, so I will go in the anti-clockwise direction, and V3 will lag, so I will go in the clockwise direction. So that is also another way to understand whether a waveform lags or lead. If I am going with respect to a waveform, if I am going in the clockwise direction, that means it is lagging. If I am going in the anti-clockwise direction, that means it is leading, right? And one more thing, the peaks of all these waveforms are same, so their amplitudes are same, but their phase angles are different. This is 0 because it is leading plus 90, because it is lagging minus 90. As you can see, 0 plus 90 minus 90. Okay, I hope this part is clear by you. How do I represent phasor in terms of voltages? Okay, so a phasor diagram is a visual representation between sinusoid voltage, different sinusoid voltages or currents. Okay, in AC circuits, we will use this mainly to solve complex circuits and make our lives easier. Now one more thing is there, we generally want to write our angle, right, between minus 180 to plus 180. That is what we prefer. How will I do it? So we know this thing, right? If let's say I have minus 270, if I add or subtract 360, will it change? No. So let's say, what do I mean by minus 270? Minus 270, I'm lying minus 270, right? Means basically with references, let's say 0 degree, minus 270 means this is minus 90, minus 180, minus 270 here, right? So if I add 360, 360 meaning full circle. So does it make a difference? No. So how can I represent this point? This point also can be represented like plus 90, right? From the positive x-axis plus 90, because I'm going in the anti-clockwise direction, right? So that is what we do. We do not like this minus 270. So what we do, we add 360 to make it plus 90, right? Or let's say I have plus 270. So I do not like angle greater than 180. We do not like it, okay? So I will subtract 360. It does not make any difference because I'm moving a whole circle, right? It will not make any difference. So this will make it minus 90, okay? This will make it minus 90. So I hope that is clear by you, okay? So yeah, so here also I have written the same thing, that if I move in the clockwise direction, lagging, it will be lagging. If I move in the anti-clockwise, it will be leading, okay? Now few more things are there. I will slightly prove later on, but the impedance provided by a inductance, right? If you remember it, it will be good actually. Impedance provided by inductance will be, if I have a L, in frequency domain, the impedance provided by inductance will be J omega L. The impedance provided by the capacitance will be 1 by J omega L. What is J? J is the complex number, right? I hope I don't have to explain what is J. J is complex number 1 angle minus 90, or it is under root of minus 1, okay? 1 angle plus 90 or under root of minus 1. So basically, if I plot in the complex plane, right, Argand plane, this will be my x, this will be my iy. So J will, or I or Ji, so J will lie here. So that's why it is 1 angle plus 90, okay? Now one more thing is there, that this 2 angle 30, right? This representation you have studied somewhere else as well. Where have you studied? You have studied this in complex numbers during your JE days, right? Class 11 complex numbers. So there we have not discussed anything about frequency. So actually I cannot say whether this term is a Phasor quantity or just a complex number. I cannot say it actually. So this can mean two things. Either it can be a point in the complex plane, because what do I mean if I have a complex plane x, I, y, right? What do I mean by 2 plus 30? 2 plus 30 basically means that I have to shift plus 30 from the positive x-axis, right? And the amplitude will be 2. Okay, I have to shift plus 30 by the x-axis and the amplitude will be 2. Okay, it is just a point in the complex plane. It is just a point in the complex plane, but also it can represent a Phasor quantity. That you don't know. That how will you understand? With the question. With the question, automatically you will understand whether this is a complex number, just a complex number, or a Phasor quantity. So this, right, will be what? This will be in sinusoid, if my reference is sin omega t, this will be 2 sin omega t, if 2 is assumed to be the peak, plus 30. Okay, so this can have two meanings. Either it can be a point or a sinusoid. That is what I have written here. If it's a point, it will be lying in the complex plane. If it's a sinusoid, it will be a Phasor quantity. Okay, it will be a Phasor quantity. So yeah, these are the things that I wanted to say to you. These things you keep in mind: impedance provided by a capacitance and impedance provided by a inductance. Okay, so there are multiple ways in which I can represent a Phasor. This was the polar format. This was the polar format, right, which we know in complex plane. But also we can represent it in different formats: rectangular format, exponential format. Okay, I hope you remember all these things. So I'm not going through over this, because I hope you know during your JE days this is understood by you, right? In complex plane, I can plot a point. It is just like a complex number. It will follow all the properties of a complex number actually, okay? But internally we know it is a phasor. Internally we know it is a phasor. So I can apply all the like properties of a complex number, whatever are the properties of a complex number, I can actually do all of that, okay? So yeah. Now in a series circuit, let's say in a series RLC circuit, if I want to write everything in terms of phasor, so let's say my voltage is my reference Vm sin omega t, where I have assumed peak to be the this amplitude right here in the phasor. So Vm angle 0, this is my reference. So what will be Vr? Now remember, okay, Vr will be Vm sin omega t plus theta r. So in phasor I can write it Vmr theta r. Ir will be Imr sin omega t theta r. Now one thing you have to remember is in resistor, right, there is no phase shift between its own voltage and its own current. So what is the Ohm's law? Ohm's law is Vr will be equals to Ir into R. So R is a completely real quantity, right? So there is no phase shift between the voltage of the resistor and the current. So the voltage of the resistor is what? Vr. What is the current? Current is I. It is a series circuit, current is same across. So this will be I current, right? This current will be I, okay? So if this current is I, what does it mean? It basically means that so that's why there is no phase difference between these two. Like you can observe that the angle is same between the current of the resistor and the voltage. Now one thing you have to see is what will be the voltage relation between the voltage of the inductor and the current of the inductor. So voltage will be I of the inductor into ZL. What is ZL? ZL is IL into ZL is what? J omega L. So J omega L, J is what? 1 angle 90, right? It is just a like it is like a complex number, 1 angle 90 into omega into L. So what actually happens is I am shifting my IL by plus 90. So the voltage actually leads the current by plus 90 for an inductor. For inductor, voltage actually leads the current by plus 90 because I am adding plus 90, okay? What about capacitor? Capacitor, okay, VC, it is IC into, remember this current is the inductor current, this is not the circuit current. Please remember, whatever I am defining with respect to the inductor voltage and the inductor current, I am not defining it with respect to the circuit current, okay? Remember this. This also was with respect to the resistor voltage and the resistor current, okay? The overall voltage and overall current might have some phase difference. Overall voltage and overall current might have some phase difference, but I am just discussing about the resistor voltage and the resistor current, okay? Resistor voltage and the resistor current. So VC will be equals to IC into ZC. ZC is what? ZC is 1 by J omega C. Now for the students who know few basic properties, I will also explain few basic properties. 1 by J is simply minus J. 1 by J is simply minus J. Don't worry, I will come to this, okay? So this will be minus J by omega C into IC. So what is minus J? Minus J will be minus J is nothing but minus 90. 1 angle minus 90. Don't worry, I will explain this, don't worry. So 1 angle minus 90 means that the voltage is lagging the capacitor current by 90, okay? So the voltage of capacitor lags the current by 90. So these are few important key things that you should know. So yeah, here I have just written how can you write the voltage and voltages and currents in terms of the phasor quantities. That's what I've written. So you can see, go through this. Now this part is actually very important. How do I write angles? So I have explained a bit about angles, right? If you know all about this, right? So try this out. So tell me in which quadrants these 4 points will lie, and what will be the angles of these points, arguments of these points. So first one is 3 plus j4, next 3 minus j4, then minus 3 plus j4, and minus 3 minus j4. Pause the video and tell me where all these points will lie in the complex plane, and what will be the angles, arguments of these 4 points. So this will lie in the first quadrant. the first point will lie in the first quadrant. Very simple, because both my x and y, like this is my x coordinate, this is my y coordinate, both are positive. So z is equals to x plus iy. So I lie in the first quadrant. In the first quadrant, the angle is tan inverse mod of y upon mod of x. I do understand this formula is seems like bit complex, but don't worry, very simple. Okay, visually I will explain how to remember this formula. Okay, so basically my 3 comma 4, right, will be lying somewhere here, right? 3 comma 4 will be lying somewhere here. 3 is the y axis, 4 is the x axis, right? So this is 4 and this is 3. Three and 4, right? So here, what is the angle? Simply I can use the simple rule of triangle. It will be tan inverse y upon x. Height is 3, base is 4, so tan inverse 3 upon 4. So what is the angle? Tan inverse 3 upon 4. What is tan inverse 3 upon 4? Tan inverse 3 upon 4 is what? 36.86, right? You need to remember this value, tan inverse 3 upon 4. Okay, sorry, y is 4, x is 3, right? Because it is 3 plus j4, right? X is 3, y is 4, sorry about that. So y will be 4, x will be 3, so it will be tan inverse y upon x, so 4 upon 3, right? So it will be 53. Just give me 1 second. Point 13 degrees. It will be 53.13 degrees. Okay, so that is what my tan inverse 4 upon 3 is, right? Now the thing is, what about the second one? Second one is, in which quadrant am I lying? Actually, it is lying in the fourth quadrant. No, it is not. Yeah, it is lying in the fourth quadrant, where my y is negative because it is minus 4j, right? Y is negative, x is positive. So x is positive, meaning I will be lying on the right hand side, right? X is positive, meaning I will be lying on this side, and my y is negative. Y is negative, meaning I will be lying in this region, which is quadrant 4. That's why it will be quadrant 4. That's why it is written plus minus. Y is negative, x is positive. Here, what will be the angle? Minus theta, but you don't have to remember it. No need to remember. Okay, just draw the point. What is the point? Point will be lying somewhere here approximately. Okay, so the height will be again 4 because it is minus j4, and the base will be 3. This will be same 3. What is this angle? Again, it will be angle of a triangle. So tan inverse y upon x. So this is tan inverse 4 upon 3. Now the important point, that is 53.13. What is the important point? Important point is, previously I had to move in the anti-clockwise direction. This is my reference. Positive x-axis is always the reference. Angle is always calculated with respect to the positive x-axis. Okay, angle will always be calculated with respect to the positive x-axis. So with respect to the positive x-axis, previously I had to move 53.13 degree in the anti-clockwise direction. That's why this was plus 53.13. Okay. With respect to the positive x-axis, I had to move in the clockwise direction. With respect to the positive x-axis, I had to move in the clockwise direction 53.13 degrees. Will it be plus 53.13 or minus 53.13? It will be minus. That's why this angle will be minus 53.13, because I had to move in the clockwise direction. What about this one? Minus 3 plus j4. Minus 3 plus j4. Minus 3 means negative x, plus means positive y. So I am lying in the second quadrant. Here it is 180 minus theta, but you don't need to remember it. I will say how to understand it. So again, I will draw the triangle, right? So positive y, that is this will be 4, right? And this x will be 3, minus 3 or 3 I can write here. I'm just concerned about the length. Okay, I'm just concerned about the length. What is this angle again? Again, tan inverse y upon x. What is y this time? Again 4. X is again touching the angle, that is 3. So this is again 53.13, no problem. So this angle is actually 53.13. But is this angle with respect to the positive x-axis? No. This is just with respect to the negative x-axis. But I have to calculate with respect to the positive x-axis. So with respect to the positive x-axis, I have to move total 180 degrees. With respect to the positive x-axis, I have to move total of 180 degrees, but this much is 53, right? So how much will be this much? 180 minus 53.180, 53.13. That is what is written over here. 180 minus theta, 180 minus 53.13. That will be the angle over here. Similarly, you can do it for this one as well, the last one, but both are negative. This will be quadrant 3. Here, this will be again 53.13. How much do I have to move now? I will move a total 180 with respect to the positive x-axis in the anti-clockwise direction. Additional theta I have to move. Additional theta I have to move, right? So it will be 180 plus theta. So this angle actually becomes 180 plus theta, right? Additional theta I have to move, so this angle becomes 180 plus theta. Now, one thing I have told you that we generally don't want to write our angle greater than 180 or less than minus 180. So I will subtract 360 to make it smaller than, like basically in our range. So that's why I subtract 360. But the both these are same only. This is not nothing different. Both these are same. Both of these are same. Okay. One more thing is that if I'm lying in the negative x-axis, right? If I'm lying in the negative x-axis, it does not matter whether I add 180 or subtract 180. Both are doing the same thing because ultimately I'm reaching the same point, right? So basically your minus 1, right? Angle of minus 1 will be what? It will be either you can write like any minus 1, right? How can I write the angle of minus 1? It will be like, what is 1? 1 is just 1 angle 0. The angle of 1 is 0 because it is positive x, right? There is no imaginary component, right? It is real. What is minus 1? Minus 1 you can write as 1 angle 180 because from here is my minus 1, right? Here is my minus 1. So I have to rotate in the clockwise direction, anti-clockwise direction by 180. I will reach my minus 1, or I can rotate in the clockwise direction and reach my minus 1 by 180 degrees, right? Same thing. So this is same as 1 angle minus 180. Can I prove it to you? Yes. Just subtract 360 with this, you will get minus 180. And I have told you that subtracting or adding 360 will not make any difference to the angle physically. Okay. So this was about it. You can go through this and have a revise because like this is like a crash course, so I cannot cover everything here. But I hope I have explained the most important parts. Okay. Now these are a few important operations or arithmetic operations of complex number. I will not go through this. You please have a read and go through this. Have a watch and go through this. Revise it quickly. Okay. These are basic things. I will not explain this over here. Just one thing I want to explain, that what is j? What is 1? 1 I have told you already. 1 is 1 angle 0. Okay. Minus 1 is either 1 angle 180 or 1 angle minus 180. Both are saying the same thing. What about j? Now j basically means j is nothing but the positive x-axis, y-axis. So what is the angle? Plus 90. What is the magnitude of j? Magnitude of j is 1, right? Magnitude of j is 1. So it will be 1 angle plus 90. What about minus j? Minus j is somewhere here. What is the magnitude of j? Minus j? 1. Magnitude of minus j is 1. What is the angle? Minus 90, because with respect to the positive x-axis, I have to move in the clockwise direction by 90. So this will be minus 90. Okay, that's how we represent minus j. Now what about 1 by j? What about 1 by j? So one more property is there, that I know j square is minus 1, right? J square is minus 1 because j is minus under root of minus 1. So if I square this, right, this will become simply minus 1. Okay. So what will be 1 by j? I will multiply and divide by j on both sides. This will be j square, j by j square. This will be j by minus 1 or minus j. Okay, so it is nothing but 1 angle minus 90. So 1 by j is 1 angle minus 90, as I have told you over here as well. Minus j. This becomes minus j simply, 1 angle minus 90. Okay, I hope now it is clear how it is minus 90. Okay, now let's say if I want to add two phasor quantities, it is similar to vector addition. Similar to vector addition, I hope you remember the parallelogram law. Okay, what used to happen in parallelogram law, that is what I have told you over here. I am not going through it because I am expecting that you already know this. Okay, so basically it will be if x1 is magnitude of x1 into theta 1 angle, x2 is magnitude of x2 into theta 2, then the resultant, right, resultant x, if I am adding these two vectors, right, x resultant, the magnitude, I cannot comment about the angle, okay, I cannot comment about the angle, but the magnitude will be what? Resultant. Angle you have to calculate separately. Resultant will be, magnitude of the resultant will be basically magnitude of x1 whole square, magnitude of y2 x2 whole square plus 2 into x1 x2 cos of the phase difference, the angle between them, right, that is theta. That will be the magnitude of the resultant, not the angle, not the angle. I am just discussing about the magnitude. How can I find out the angle as well? So let's say, like, how do you do? So let's say I have a quantity here. This is my reference. Okay, I have two quantities. Let's say this is one of the quantities, x1, and this is the other quantity, x2. So the simple thing is we will break it down into components. We will break it down into y component, vertical component. This will be broken down into two components, right? This will be broken down into two components. One will be along the y axis, another one will be along the x axis, and this also will be broken down into two components. One will be along the y axis, another one will be along the x axis. Okay. So if I break it down into two components, then I will do the addition. So these two are in the same phase, I can add. These two are in the opposite phase, I have to subtract. Okay, so that's how you will do. So just, I hope you remember how to do vector addition and stuff, how to break down into components. I'm not explaining this because my expectation is you already know this. Okay, now let's come to few important things. Like if I want to add these two quantities, can I take help of phasor? Like I will write this in 1 angle 30, I will write this in 1 angle 60, or this will be what, cos 60, right? So I have to add another 90. This will be 1 angle 150. So I will simply add 90. This will be 1 angle 150. Can I add these two quantities? No, because the frequencies are different. So you cannot use your phasor representation here. Whenever the frequencies are different, you cannot use the phasor representation here. So this also again not possible, right? I cannot convert this again into 1 angle 30, right, and 2 angle 150 and multiply. No, this will not be possible, because, like, I hope you remember, right, this is 2 sine A cos B. So the resultant actually is like sine A plus B cos A minus B. The frequency content changes, right? And in phasor I have already told you that the frequency information about the frequency is lost. So the resultant is actually something else, right? So you cannot multiply two phasor quantities. I can definitely multiply a complex number 1 angle 30, right, or like let's say 1 angle 30 into a phasor quantity sine omega t plus 30. This is possible. This is only possible if I already know, and you must know, that this is a complex number. Complex number, okay? Just a point. This is just a point. Then this is totally valid. Multiplication of a complex number with a phasor is totally valid, as we have done here. As we have done over here. Totally valid. No problem. Because IC is supposed to be a phasor quantity, right? It is current, it is AC current, it is supposed to be a phasor quantity. The resultant will come out to a phasor quantity, no problem. Frequency will not change, because I knew that this, right, this complex number will not do anything with the frequency. It is just a point. That's why this is valid operation. This is a valid operation. But this operation is not valid at all. Multiplying two phasor quantities is not valid. Multiplying a complex number with a phasor quantity is valid. Adding two phasor quantities of different frequencies is again invalid. Again invalid. Okay, I hope these points are clear. Again, multiplying a complex number and a phasor quantity is valid, but adding a complex number with a phasor quantity again is invalid. It is again invalid. I cannot do it. Only multiplication of a complex number with a phasor quantity is valid. Okay, with this basic concepts, now we want to solve few questions. So these will be a bit new questions, just not just your like own branch PYQs, different branch PYQs. So pause the video, try these questions out by yourself, whatever concepts I have told you, and we will solve all these questions after we come back. Okay, yeah, let's solve this question. The time delay between the peaks of the voltage signals V1 of t and v2 of t. So they are asking us the time delay. Remember, they are not asking us the phase delay. They are asking me the time delay. So you have to be very careful. I have told you what do I mean by time. Okay, remember unit is in seconds. So you have to convert everything in seconds. So this is in degrees. So this also will be in degrees, right? If this is in degrees, this also will be in degrees. So we have to be very, very careful here. So they are asking me the time delay between this quantity and this quantity. So first of all, I will convert everything into same format, either in sine or cosine, either in sine or cosine. So remember the frequencies are same, right? So here I have, so whenever there is sine and cos, I will draw the cos here, and this will be my cos 60, this will be my sine 60, right? Now I will convert this minus sine 60 into cos in terms of cos, right? So where will be the minus sine 60 lie? Minus sine 60 will lie here. Minus sine 60 will lie here, correct? Minus sine 60 will be just opposite. And in what direction I need to move from minus sine 60 to reach cos 60? It will be simply just give me 1 second. Yeah, from sine 60, if I want to move to cos 60, I have to move in the clockwise direction 90. So minus sine 60 minus 90 will be equals to cos 60, right? Or let's say I want to move from cos 60 to sine 60 minus sine 60. In which direction I have to move? Anti-clockwise. So cos 60 plus 90 equals to minus sine 60. Both of them are like, I'm doing the opposite here. I'm moving from cos to sine to minus sine 60, right? So minus sine 60, right? So minus sine 60 is actually cos 60 plus 90. So 3 I can take outside. So this will be minus 3, or 3 into minus sine 60 will be equals to 3 into, what is minus sine 60? Cos 60 plus 90. You can mathematically do it as well, no problem. But I am doing it with a diagram so that you don't have to remember anything. So this will be sine of, cos of 60 plus 90. Cos of 60 plus 90. Okay, this is sorted now, right? And the other waveform, this is my V2. This is my V2 actually, right? What is my V1? V1 is 2 cos 60 plus 30, plus 60. Now what is the delay between them, right? What is the phase difference between them? 30 degrees. The phase difference between them, that is theta 1 minus theta 2, is 30 degrees. They have just asked us the delay, right? Magnitude. I will not care, I will not think about the sign. 30 degrees is the delay. This is in degrees. So I have to convert this in seconds. How do I convert this in seconds? So one thing I know, I have already told you, always write this theta equals to omega t. Okay, and omega is always in radian per second. Omega is always in radian per second. Okay, so even though here they have written in degrees, but internally it is understood. Whenever I will come back to time, so theta is omega t, so that is the delay basically. Your delay is 30 degrees. But remember, this is in radian per second, this is in per second. So basically your theta delay, I know the angular displacement, but I don't know the time delay. So if I have to write the time delay, right, omega will be fixed, omega will not change, into t delay. So for that I have to first of all convert, because this is in radian per second, this also must be in radians. Okay, so I have to convert this in radians. How will I convert this in radians? So I know that my pi is 180 degrees. So what will be 1 degree? 1 degree will be pi by 1 into pi by 180. So this will be theta d in radians will be 30 into pi by 180. Okay. What about your omega? What is omega? Omega is the angular frequency that is already given to you, 6, right? 6. Always here, this will be always omega t. This will always be omega t. Internally, when I will come back, I will always convert this into radians. Okay. So omega is 6 into td, the delay time that we have to find out, because but I don't know the delay between the waveforms in time domain, in seconds. So that is what I have to calculate. So this will be 5. So if I cut this, right, this will be 5 by 180, but I see that everywhere there is 360. I see everywhere there is 360. So I will multiply by 2. This will the TD, the delay time will come out to be 10 pi by 360. Okay. So this will be the. So here option B will be the correct answer for this particular question. Let's now move on to the next question, this one, right? So we have been given currents through ammeters A2 and A3 in the figure. Okay, currents through the ammeters are given. The reading of the ammeter A1 will be, okay, A2 and A3 currents I know. What will be the current ammeter A1? So basically I can apply KCL. So KCL will always be valid, right? If it's AC, if it's D plus I3, I just have to do basic phasor addition, right? So I1 will be equals to, I2 is 1 angle 10 and I3 is 1 angle 70. Now I will do the phasor addition. Okay, how I will do the phasor addition? So you don't have complex calculators here, right? So you have to assume a reference. Reference is 1 angle 0. Okay, so from 1, I1 is leading like the same length, 1 angle plus 10, and I2 1 angle 70. Okay, so now this will be 70, this will be 10. Okay, I have to break it down into components. What have they asked? They have just asked me the reading of the ammeter, right? So for calculating amplitude, I don't need to do all this, right? So what I can do is one formula I have told you, right? That formula you can use for adding two phasor quantities. So your resultant, right, magnitude of I1 will be under root of magnitude of I2 whole square, that is 1 square, magnitude of I3 whole square 1 square, plus 2 into magnitude of I1 into magnitude of I2 into cos of the angle between these two. What is the cos of the angle? 60 degrees, right? 70 minus 10, it is 60 degrees. So only this much will be enough. So it is 1 square, 1 plus 1, that is 2. Cos 60 is half, right? Cos 60 is half. 1. So it is under root of 3, that is 1.732. I can do the in the calculator, it will be 1.732. So 1.732 will be answer. They have asked us to round off to 3 decimal places. So this will be my answer, because they have just asked me the reading of the ammeter, and ammeter always will read the magnitude. Okay, it cannot detect the phase. Okay, that was the answer. Now remember, here they have not mentioned you what are these values. Are these P? Are these RMS? I don't know. But as they have just mentioned, as they have just told me to calculate the magnitude, I will just calculate the magnitude. I don't know what. Yeah, sorry for the interruption. Actually, I was checking, the audio was cut for a second. So now, like, this is the answer. This question is done. What if you had to find out the phase as well? How would you have calculated the phase? Because you don't have complex calculator there, right? Magnitude you will easily be able to find out using this formula. But what if you have to find out the phase? How will you find out the phase? What you will do, you will break it down into two components, both the vectors, right? You will break both the vectors into two components. So this, right, this green one will have two components, one along the x-axis. What will be this value? This will be 1. Now what is this angle? 10 degrees. So 1 cos theta, right? 1 cos theta along the x-axis, 1 cos 10, and the y component will be 1 sin 10. Okay, same for this one as well. You will break it down into two components. This will be orange one, this will be 1 sin 70, sin 70 will be higher actually, and x component 1 cos 70. Okay, so overall your y component will be both the addition of these two. So overall, like, your complex number z will be x plus iy. This will be the x will be sum of the y component. Now in this case we are lucky, both of them are in the same direction. Sometimes what will happen, this vector, right, might be here. So then the x component will be on the left hand side, y component is along the same direction. So you have to be very careful. If the x component is in the opposite direction, then you have to subtract. If it is in the same direction, then you have to add. Because this is a smaller course, I will not write down everything. I hope you understand these basic things. Okay, so just be careful regarding this. So in this case, both of them are in the same direction. So this will be, x will be 1 cos 10 plus 1 cos 70, y will be 1 sin 10 plus 1 sin 70. Then from there you can easily calculate your angle. I have already told you how to calculate the angle if both of them are positive, if x is negative, y is positive. Already I have mentioned this in the today's lecture itself, right? So then from there you can calculate the angle. Magnitude, already I have told you the shortcut to calculate. Okay, this, if you remember this, this will be very helpful for you. Okay, in your everywhere, right? Not just in this chapter, in everywhere. So now let's solve this next question. This question is actually pretty good. Okay, this question is actually pretty good. They are asking us to find the, like, this is a gate easy question, and this question is pretty good. I will tell you what is the trick question. They're asking us to find the current I in the given network. Okay, they're asking us to find the current I in the given network. So how will I find out the current I? And z also, z value they have given me, but this is my z value. Okay, and the options are given 0, 2.38 this angle, 2.38 this angle, 2.38 this angle. So this is for certain. If the current is not 0, then the magnitude of the current will be certainly 2.38. So I don't need to calculate the magnitude of the current. What is my concern? My concern is only the phase angle. My concern is only the phase angle. That is my concern. Okay. Now let me mark this point as A, B, C. Do I know the voltage across AB? Yes. Same AB, right? Do I know the voltage across BC? Yes. Correct. So what will be current I? So I can write my I will be current. So I can write a KCL at this node. It will be I plus IAB will be like this. If this is IAB, right, and this is IBC, let's assume, will be IBC. So your I will be equals to IBC I will be equals to IBC minus IAB. I will be equals to IBC minus IAB. Okay. Now this is my I. Okay, this is my I, right? And okay, what is my I? What is my IBC? IBC will be the voltage across this divided by the impedance, VBC divided by impedance, minus the voltage across this divided by the impedance, VAB by impedance. Again, I have told you, right? Multiplication of two phasor quantities, these two phasor quantities is not allowed. I cannot multiply these two phasor quantities, but definitely I can multiply or divide by a complex number. Just a point. So multiplication of two phasor quantities is not allowed, but multiplication and division of a phasor quantity and a complex number is totally allowed. It is just a complex number. It is not a phasor quantity. Okay, that is totally allowed. So I can divide by z, totally allowed. Okay, that is one point. One more point is there, that although this you should know already by basics, that if let's say I have this 1/2 angle minus 30, I can also write this as 0.5 plus 30. This will be 0.5 plus 30. Okay, this will be 0.5 plus 30. Okay, so because your angle will just get flipped, it will, if it goes in the numerator, angle just simply gets flipped. Okay, this thing you have to remember. And this 1/2 is simply 0.5. Magnitude of like 1/2 is 0.5. Okay, the sign of the angle simply changes if I take it to the numerator, right? Sign of the angle will simply change, it will become plus. Similarly, like just like I have here my 1 by, let's say 1 by j, right? So what is 1 by j? It is 1 by 1 angle 90. So if I take it in the numerator, it will become 1 angle minus 90. Okay, so the complex number simply, if I take the inverse, simply the sign of the angle changes. Like how this property comes? This property comes like this. If I have a complex number, magnitude of z angle theta, right? If I power it to the power of n, its magnitude will be raised to the power of n and its angle will be multiplied by the n, right? So if this n is minus 1, this will become z is z inverse into minus of theta, that's it. And n minus 1 basically means it is the in fraction format, okay? That's how this like format comes, but this is not our concern. I hope you know already these things, right? In class 10, 11 you have studied this. So this is VVC and your VVC is this value, right? 120 angle minus 30 by z. Z I can take common, right? Z is some common value, Z I can take common, minus 120 minus 90, right? This is what you have to calculate and you will be absolutely wrong. Why? Because you did not notice the polarity. They had mentioned you the polarity. This polarity, my VBC is, this point is the higher potential, this point is the lower potential, but here they have mentioned you opposite. So actually this will be minus, like I cannot just write here 120 minus 30, I have to write minus 120 because the polarity is opposite. And this is a gate EC question. So it is not like, oh, this will not be asked in EC. No, this is a gate EC question. So they do take care that you understand what do you mean by instantaneous polarity. Polarity is opposite. Here it is fine. AB, A is plus, B is minus, no problem. But here B should be plus, but B is minus. So I have to write a minus sign. I cannot just simply write it. Okay. So my I will be actually equals to 1 by z is common, right? 1 by z is common between everything. Give me 1 second. Yeah, 1 by z is common. Z is complex number. I don't care about the complex number for now. I don't care about the complex number for now. Okay. Into minus of 120. So this will be minus of 120 angle minus 30 minus 120 angle minus 90. Now we can convert this into phasor, right? Like there are two ways to solve. First one is I hope you know that you will convert this into rectangular format and then solve, or you can directly solve it graphically. Okay, graphically. I am telling you the graphical method. Rectangular format you can do. How to convert from polar to rectangular, I hope you can do. I have told you how to convert angles, right? That is understood by me, that you will be able to figure it out. Okay, so now it is graphical. How will I solve it graphically? I only know how to add two vectors. So first of all, I will convert everything into plus sign. This negative sign I don't like. I don't like negative sign. So if I have a negative sign, how will I convert it into plus? So I will simply add or subtract 180, because I don't like negative sign in angle as well. I will add 180. So this will become 120 minus 30 plus 180, and this will become just give me 1 second. Plus 90 minus 90. Okay, so this will be equals to 120 150 angle and plus 120 90 angle. Now it is fine. Now I can easily calculate these values. So I have two vectors. This is my reference, let's assume. Okay, one vector is 120 plus 150. 150 will be somewhere here. Plus 150 means I will go in the anti-clockwise. So this will be 120 angle 150, right? So if this angle is 150, right, and this overall is 180, how much will be this one? 30. This will be 30, right? This much angle. And I have the other vector that is simply plus 90, right? 120 plus 90, I like this does not have any real component. It is completely imaginary. Okay, so 120 plus 90. So now okay, so let me calculate the equivalent. So its y component is fixed. Okay, y component is not fixed. So this will have two components, right? 120 cos theta along this direction, in the negative direction, 120 cos 30 and 120 sin 30, right? because it is a simply a triangle. This is simply a triangle. Okay, so this component will be, y component will be 120 sine 30 is what? 120 sine 30 is actually half. So this will be 180. Y component is 180 plus j 180 because it is in the positive axis, j axis, plus 120 cos 30. Cos 30 is root 3 by 2, so it will be 60 root 3 because I don't have any other x component, minus because it is in the negative x axis direction, right? Minus 60 root 3. Okay, so this is minus 60 root 3 plus j 180. Now I am just concerned about the angle. Certainly this is not 0, so definitely 0 is not answer. Certainly 0 is not answer. What is the angle? This angle, right, will be simply what? I have to calculate the resultant. Resultant will be lying somewhere between these two vectors, right? It will be lying somewhere here actually. Or I know x is negative. First of all, I will calculate the theta. What is theta? Theta is tan inverse y upon x, right? What is y? Y is 180. What is x? X is 60 root 3, right? So this is my resultant in which y is 180, x is 60 root 3. Like remember, the image is not to scale, so don't take stress. This is 120, how is this 180? Okay, okay, itna bhi tension nahi lene ka. So this is overall 180, this is 60 root 3. So this is my theta. Theta I have calculated is 180 by 60 root 3, which is actually tan inverse root 3. And what is tan inverse root 3? You have to remember these values. It will be simply 60 degrees. Tan inverse root 3 is 60 degrees. These values you should remember. Okay, it is 60. So this value is actually 60. But I actually don't need this value. What value I need? I need this value from the reference. So if this is 60, what will be this value? 120. This will be 120. This value will be 120. So I got my angle of this value, this resultant, it is 120. But I still will not be able to comment about the final angle because I need to know about this angle. I need to know about this angle. What is z? Z in polar form, z in rectangular format is given to me. I will convert this into polar. Z is 80 minus j 35. Here my y is negative, x is positive. That means it will be simply minus theta, right? I will calculate theta. What is theta? Theta is tan inverse 35 by 80. So I will calculate that in my gate calculator. So 35 by 80 tan inverse 23.63. But remember, y is negative, so it is minus of theta. So this will be minus of 23.63 degrees. Okay, minus of 23.63 degrees. So that will be my angle of theta. Okay, so I will put the angle over here. That overall I have some, I don't care about the magnitude, x component that has an angle of plus 120, and I have some y z that has an angle of minus 23.63. Okay, so this will be equals to, like I don't care about the magnitude, x by y, angle overall will be 143.63. So overall angle should come out to be 143.63, that is present in the option B. So option C. So option C will be my correct answer, definitely. For certain, option C will be my correct answer. Okay. Now you might ask, sir, you just took around 10-15 minutes to do this question, and you are saying that this is shortcut. No, I had to explain all this, right? Once you will do it, it will not take you much time. It will not take you more than 4 minutes. Okay. If you try to calculate the magnitude, it will take you even more time. You can definitely calculate the magnitude, which I will definitely do right now. So what is the magnitude of z? Magnitude of z will be 80 square minus 35. So 80 plus 80 square plus 35 whole square whole under root. So 87.32. Okay, what about the magnitude of this one? What is the magnitude of this one? So it is 180 whole square plus 60 into root 3. Okay, I cannot do this. 60 into root 3 whole square plus 180 whole square whole under root. It comes out to be 207 something, right? Magnitude. The magnitude of this comes out to be 207.84. So like x is 200, magnitude is 207.84, y is 87.32. Angle I have already calculated. So this will be 87.32. So sorry, just give me 1 second. 84.32. So this comes out to be 2.38, which is exactly present in the answers. All of them are 2.38. So this will not go wrong, obviously, but just we have reduced an additional step. We don't need to calculate the magnitude. That is the purpose of doing all this, right? I am just explaining that we don't need to calculate the magnitude because only the phase is different. If they would have asked the magnitude, then I would have only calculated the magnitude. I would not have calculated the phase, but they are asking both. So because the magnitudes are same, I only will calculate the phase. Okay, so I hope this question is clear. This question is actually pretty good. It came in easy, and they can ask this, like this is very basic question, right? Very basic question, but they can ask this basic question like this positive, negative, all these things. So I hope a lot of things are clear with this question. Now let's actually come back to our second portion of phasors, that is for components, like for electrical components, what will be the phasor diagram? So for resistor, there is no phase difference. Like there is actually no concept of phasor, but we can draw the phasor diagram for resistor, no problem with that. For resistor, there is no phase shift, right? For inductor, we will see the phase shift. I will explain what do I mean by phase shift just in a second. For resistor, my voltage is equals to I into R, and R is a real quantity. R is a real quantity. So if R is a real quantity, if the voltage is 5 angle 0, current also will be angle 0. There will not be any phase shift, but definitely the magnitude of the current will change. Let's say if the resistor value is 5 ohms. Okay, if the resistor value is 5 ohms and the voltage is 5 sine omega t, then what will be the current? Current will be sine omega t, right? Voltage by current, voltage by resistance, that is what my current is equals to, correct? So 5 sine omega t, so this will be sine omega t. Okay, current will be sine omega t. So you see, like there is a difference in the magnitude, but there is no difference in the phase. So for resistor, there will not be any phase difference. That is what we have written over here. The waveform will be like the peaks of the waveform will occur same time. But for inductor, things will change. For inductor, things will change. Okay, how? So let's say if I have a voltage. Okay, how will I explain? So if I have a voltage Vm sine omega t, and what is the very basic equation of inductor? That the voltage, okay, let me assume the current. Let me assume the current across the inductor is Im sine omega t. And what is the very basic equation of voltage for inductor? VL is L DIL. I will write it actually here in smaller so that I can fit my stuff. VL will be L DIL by dt. IL is Im sin omega t. So this will be Im. What is that differentiation of sin omega t? Remember, omega is assumed to be constant, t is a variable, right? So it will be omega into cos omega t, right? I hope you know the basic differentiation. So this comes out to be Im into omega L into cos. And now what is cos? Cos is nothing but sine omega t plus 90, right? This we have derived. So if I want to write this in phasor, so in phasor this will be what? This will be, let's say, Im angle 0 degree. So what will be the voltage? Voltage will be, magnitude is Im into omega L, and this will be angle 90 degree. So for an inductor, the voltage leads the current by 90 degrees, or other way I can say the current lags the voltage by 90 degrees. Okay. Also, I see this omega L term. What is this omega L? This term is getting multiplied by current. Is this something familiar? Voltage equals to impedance into current. Oh, this is something familiar. Z is nothing but omega L. Also, I have to consider the phase shift. So that's why Z is equals to J omega L. That is the derivation for the impedance of a inductor. Okay. So that's what we have seen, said here. Same thing. You can go through, have a read all these things, right? I have explained all these things very well. Simply the bottom line is the current of the inductor will lag the voltage by 90 degrees. That is the bottom line. Okay. Same for capacitor, just the opposite. Now the homework for you is your derivation, that for capacitor what will happen, the current will lead the voltage, just the dual. So capacitor and inductor are dual of each other. Current will lead the voltage by 90 degrees. Now again I have told you, right, lag or lead does not mean that one current will come first, voltage will come later. No. Both are happening instantaneously. Both current and voltage are happening instantaneously. But the peaks will come later or earlier depending on whether it is lag or lead. Okay. Peaks will come later or earlier depending on whether it is lag or lead. Okay. I hope that part is clear. Okay. So yeah, that was about the impedance of a capacitor, of a inductor. Now let's come back to few important definitions. Like impedance is nothing but V upon I. For a series circuit, right? For a series circuit, not for series circuit, for any circuit, V upon I can be broken down into its real component, that is also known as the resistive component, and its reactive component. Now generally what we say, the impedance provided by, because this provides a plus 90 degree phase shift, right? Plus 90 degree phase shift here, plus 90. So impedance of reactance is plus 90. So what will be the impedance of capacitance? Minus 90. So this is also sometimes called as the reactive impedance, as you can see, the reactance. So that's why X is called as a reactance. It is the overall combination of the inductance and the capacitance. So inductance will provide positive reactance, capacitance will provide negative reactance. You can prove it, you will see it comes out to be minus J. Okay. Now there is another term known as admittance. Admittance is nothing but the inverse of impedance, 1 by Z, or it is the ratio of current over voltage, which can be broken down again into two parts, in conductance and susceptance. Okay. So conductance is nothing but the inverse relation of resistance. Okay, but not exactly 1 by R. So G is not equals to 1 by R actually. G is not equals to 1 by R. For a series circuit we can calculate the, like for any circuit we can calculate the G. So from here, right, have I done the calculation? Yeah. So here I have done the calculation. If you see, Z is equals to R plus Jx, Y is 1 inverse of J, right? So I can do do bit of rationalization. So this will come out to be what? Like this will be R square plus X square, R square plus X square, and this will be R minus Jx. Okay. And the real part of your admittance is known to be conductance. So in this case, what is the conductance? R by R square plus X square. That is the conductance. And what is the susceptance? Minus, because negative sign is there, minus X by R square by X square. It is not equals to 1 by R. I have seen this confusion many times, that they just simply say that my conductance will be inverse of the resistance. No. Not always the case. Okay. This will be the exact value. Okay. If your reactance is 0, then only, basically if your circuit is purely resistive, right, then only your conductance will be simply 1 by R. Otherwise it will not be 1 by R. Okay. Just be careful regarding all these things. That is what I have mentioned over here. Okay. So these are the summary. In DC AC what happens, high frequency what happens, because it is a function of omega, your inductive reactance and capacitive reactance are a function of omega. So at very high frequencies I can put omega equals to infinity. So if omega equals to infinity, inductance will behave as open circuit, right? Because it is J omega L, omega is infinity, X is very high, so it will behave as open circuit. And For capacitance, if omega is very high, because the reactance provided is minus 1 by j omega, so omega infinity means this will tend to 0, so it will behave as short circuit. It will behave as short circuit. Okay. So this is a summary basically. The summary is my in voltage, inductor voltage will lead the current by inductor current by 90. Inductor voltage, remember, inductor voltage will lead the inductor current. Okay, not the circuit current, not the circuit current, not the supply current. Inductor voltage will lead the inductor current by 90, or I can flip it. Inductor current will lag, because there is minus j, it will lag the inductor voltage by 90. Capacitor current will lead the capacitor voltage by 90. Capacitor voltage will lag the capacitor current by minus 90. Okay, remember all these things. Okay, not remember, understand this conceptually, because I have explained this very conceptually. Now one more thing is there. For a passive network, right, we will never get negative resistance. Okay, we get negative resistance only for active networks. It is possible. So always, whenever you are calculating the phase angle, right, of any impedance, make sure that it is lying between plus 90 to minus 90. The impedance angle, it is also known as impedance angle. Basically, your what is your impedance angle? Impedance angle Z will be basically equals to tan inverse of x upon r. X can be either negative or positive, but r cannot be negative, right, for a passive network. So I will lie in this region, and in this region, what is the angle? Angle will lie between minus 90 to plus 90. So that's why this is known as impedance angle. It is nothing but the ratio of V upon I, because V itself is a complex number, V angle theta Z, and I also itself is a complex number, II, right? So your not theta Z, sorry, theta V. So your impedance angle will be theta V minus theta I, because if it is in the denominator, right, if I take it in the numerator, I have to take it with the negative sign. So your impedance angle will be theta V minus theta I, and the range of impedance angle will always be minus 90 to plus 90 for a passive network. For a passive network, it will always be between this. Okay, simple RLC. Okay, so if for some reason, if your angle comes more than plus 90 or less than minus 90, that means you have made a mistake. Okay, for a passive network. For a active network, yeah, angle can go any value. Angle can go any value. For a passive network, make sure your angle lies between this range. Okay. Now there are few solutions for few derivations for series RL network, RC network. I will not derive it. You can, I hope you can do it, right? So here I have done the same thing. Let's say I will do it for the first one only. I'll do it for the first one. So let's say I have simply a series RL network. For a series RL network, what have I told you? For the L, right, the current will, inductor current will lag the inductor voltage. So if I simply use a KVL, let me assume this is my, like, whenever this dot is provided, dot is assumed to be the plus sign. Okay, that is my notation. Dot is assumed to be the plus sign. So this will be minus Vs plus Vr, the voltage across the resistor, plus VL. Now what do I know? This VL itself is a phasor quantity. VL itself is a phasor quantity, and don't worry, all these things you don't need to remember, right? Just understand the analysis. That's it. Just understand the analysis. Okay. So here I know that okay, let me, this was a bit of doubt here. Okay, so what do I know? This Vs actually, let me not write it here. This Vs is actually V, right? So I can take this Vs this side. So let me assume Vs to be my reference. Vs is my reference. Okay, Vs, no, not Vs actually. For a, one more thing, for a series circuit, you'll always take current to be my reference. Okay, that is the general case. As it is a series circuit, you will always take current to be the reference. For a parallel connection, you will take the voltage to be the reference. Okay, once we will do the analysis of parallel, we will see there. So for a series network, the voltage is the current is assumed to be reference. So current is, let's say, reference I. This is my reference I. Now, what is the voltage VR? VR will be I into R, and I know the phase difference between voltage of the resistor and current of the resistor is 0, because this I is same as IR. So the voltage across the resistor will also lie in the same phase across the reference, that is VR. Okay. Now what will happen over here? Now what is the VL? VL is j omega L into IL, and IL in our case is simply I. So this will be I. So j omega L into I. So j omega L into I is simply, so j means adding plus 90. It will not change the magnitude, adding plus 90. So I will be in the anti-clockwise direction of I by plus 90, j omega L. Into I, j omega L into I. Okay, this will be my VL. This will be my VL, right? Plus 90. Because I will lead my, like, because I'm adding j omega L, j means adding 90 degrees. So from the reference, it will be 90 degrees. Also I have to multiply by this amplitude, that is omega into L. Okay, so that's why VL is here. I hope you can see, that's why VL is in the plus 90 degree direction. I hope it is clear why VL is in the plus 90 degree direction. Okay, so yeah, now from here I actually want to calculate the impedance. What will be the impedance? Impedance seen from this point, it will be simply the voltage V upon I, right? So V is I into R plus I into JXL, right? I can divide by I, like XL is omega L. So I can divide by I, V upon I, that will be simply R plus JXL. Okay, and this can be converted into impedance angle Z, theta Z, where Z will be simply R square plus X square under root, okay, magnitude of Z, and angle will be XL by R. This will be the angle of the magnitude. What will be the magnitude of the voltage? Magnitude of the voltage, right, will be this whole square plus this whole square, because here I have J. So what is this? It is nothing but VR. What is this? It is nothing but magnitude of VL. Okay, it is magnitude of VL, right? Because phase I have already considered here, J. So I will not only write magnitude of VL. So this will be the magnitude of voltage. This will be the angle of the voltage, VL by VR. Okay, same analysis. Yeah, one more key point I want to say, like let's say this is 3 volt, 4 volt, right? You cannot simply add these two voltages. Because we are in complex domain, right? And these are not scalars. In DC, we used to add 3 plus 4, 7. No, because they have phase difference, I have to write 3 angle 0 plus 4 angle 90, because there will be a phase shift of 90. So then the resultant will be 5. Okay, it will not be 7. So just be careful regarding this thing. Okay, you cannot simply add these two voltages. That's why be careful in AC analysis. Things are a bit different than DC. Okay, so for a series RL network, it is also called as lagging network. Why is it called as lagging network? Because the current lags the voltage. Overall, you will see the current will lag the voltage. Resultant voltage is somewhere here, resultant current is somewhere here, right? Current we had taken the reference. So the current is lagging the voltage. That's why it is called as the lagging circuit. Anyways, wherever inductance is present, most of the cases, if inductive reactance is dominant, then it will behave as a lagging circuit. Now we have understood this phi angle. This phi angle actually has a significance. This phi angle actually is called as the power factor angle. Okay, this is called as the power factor. What is the definition of the power factor? That, like original definition, we will learn once we will study complex power in today's video only, but that will come later. Okay, so for now just understand this phi angle is the angle between what? The voltage and the current. So current was reference here. So basically what is theta I? Theta I is 0 because it is assumed to be my reference. So it is one angle 0. Okay, that is what my theta I is equals to. What is my theta V? Theta V is theta V. It is not 0, it is some unknown value, I don't know, right? That is simply this value, right? This voltage is here, that is actually equals to phi. So in this case, the angle between voltage and current theta V minus theta I is phi. And the power factor is what? Power factor is cos of this angle. So cos of theta V minus theta I is actually called as power factor. In this case, simply it is cos of phi. Okay. Now there are many ways in which you can actually find out the power factor. One of the way is with using the voltage phasor diagram. So magnitude of voltage is here. This is my VL and this is my VR. Correct? VL is 90 degree anti-clockwise. So I can calculate this phi with this formula tan phi, right? Tan phi will be what? Y upon x. So that is one way to calculate tan phi, but I am interested in cos phi. I am interested in cos phi. What will be cos phi? Cos phi will be the base upon the hypotenuse, right? Cos of any triangle is base upon the hypotenuse. So what is base? Base is VR, as I've written over here, cos phi VR. What is hypotenuse? Magnitude of V. Okay. Now, what is VR? VR is simply magnitude of I into R. It is nothing but the current into the resistor. What is VL actually? Magnitude of VL. Sorry, no, what is magnitude of V? V will be whatever is the impedance seen from the source, right? I into Z. Z is combination of R plus JXL. Okay, as you can see, that is what my Z is, equivalent impedance. We had calculated Z, right? We had calculated Z, that was the equivalent impedance seen from the source side. So this will be magnitude of I into Z. So for a series circuit, because the currents are same, this will get cancelled. Only I will be left with R by Z. Remember, this is valid only for a series circuit. For other circuit, you have to actually draw the phasor diagram and then take the ratio. Okay, you will not be able to simply find it out. For a simple series RLC circuit, the current, like the power factor, will be R upon Z. Do you have to remember this formula? It's good if you are able to remember it, because this will help you save much time. Because for most of the cases, 90% of the cases, it will be simple A series RLC circuit. In that situation, your power factor will be simply R by Z. Okay, but for the other 10% of the cases, your power factor will not be simple. You have to actually draw the phasor diagram and have to find out the angle between the voltage and the current, and then take the cos of the voltage and the current, like cos of theta v minus theta I. That will give you power factor. What is power factor? I have not yet explained. It is just a factor of power. Okay, but we will get to this later on. We'll get to know about this in complex power chapter. Okay, so there are mainly two kinds of power factor: leading power factor, lagging. So what do I mean by lagging? When my current lags the voltage, that is basically my theta v is greater than theta I, that means my current is lagging. And what is this theta v minus theta I? Theta v minus theta I is also actually equals to theta z, right? Because what is theta z? Theta z, if this I assume it to be phasor, this will be theta v, this will be theta I. So here I am just subtracting the angles, like overall angle of the impedance, right? Theta z, right? Theta z will be theta v minus theta I. Okay, that is what my angle will be, theta v minus theta I. So it becomes very simple, right? It becomes very so my power factor angle is same as the impedance angle. What about admittance angle? Admittance is just the opposite, right? Admittance is I by V. So theta I will come first, then theta V. So angle of admittance theta y, right, will be theta I minus theta V. So it is actually negative of the power factor angle, minus 5. Okay, these things, small things add up in your actual examination. So these things you should keep in mind. Okay, this will be in the notes as well, but I am just telling you these things. Okay, so that is what my theta v minus theta I is. Okay, so your power factor angle is nothing but the impedance angle, cos of the impedance angle. Okay, these things you have to keep in mind. And if your impedance angle is positive, that means it is lagging power factor. Why it is lagging power factor? Because your XL, like your reactance, is positive, right? So if it's lagging power factor, that means the circuit will behave as inductive. If it's leading power factor, the circuit will behave as capacitive, because your X, right, overall reactance will be negative, and your power factor angle will come out to be negative. Okay, this is the notation. This is the notation that we follow. Leading power factor is said to be when the current leads the voltage, lagging power factor when the current lags the voltage. Okay, that is our notation. Okay, make sure whenever you say the power factor, it is cos phi, that is correct. Also, you should mention in brackets whether it is lead or lag. So let's say if the angle is 36.86, right, I will write cos of 36.86, that is 0.8, but in brackets I will write lag, because this was positive. Okay, the interesting thing is, because once I get the numerical value of power factor, right, I will not be able to say whether it was minus or plus the angle, because cos of minus theta and cos of theta both are same thing. So for that reason we have to specify in brackets whether it is lagging or leading. By lagging, I understand that okay, the current lags, so this angle will be positive, power factor angle will be positive. If I say bracket leading, that basically means the power factor angle will be negative. Okay, that was a short intro about power factor. Don't worry, we'll learn this more in the complex power chapter. Okay, so uh, this is the summary. Okay, so there are two kinds of diagram. One is the phasor diagram where everything is there, right? The voltage is there, current is there, the voltage across the inductor, everything is there. Another diagram is the impedance triangle. Impedance triangle will combine the equivalent resistance and the equivalent reactance. In this case, we had only a inductance, that's why it will be j omega L. Okay, so j omega L will always, like my inductive reactance is plus j, so I will always lead the R by plus 90. So plus j omega L, and this is the overall impedance. Impedance has a impedance angle of theta z and magnitude of z basically, that is r square plus x square. So magnitude of z will be r square plus x square. Okay. One more thing. So yeah, that was about it basically, about the power factor and magnitude of z. We will see. We will understand this power factor even more once we move along the chapter. Now, if no information is given to you about the power factor, assume that they are talking about the source power factor. They are discussing about the source. Power factor will always be with respect to source, because here also there is a power factor, right? What is the power factor of this load? What is the power factor of this load? It is 1. Why? What is the phase difference between the voltage and current? Theta I, let's assume that current is reference. What is theta V? It will also be 0, because there is no phase shift between the voltage and the current. In this case, there is no phase difference between the voltage and the current, right? Because it is a purely resistive load. So your phi naught is 0 in this case. And what is cause of 0? It is simply 1, also called as unity power factor, right? So whenever the power factor is 1, then you have to understand that okay, the load is purely resistive. But most cases they are actually not discussing about the load power factor. Most cases they will be discussing about the source power factor. And don't worry, you will understand. You will solve the questions and you will understand whether they are talking about the source or the load power factor. Okay. So yeah, these are the things. In AC circuit, performing addition, multiplication, division requires knowing the phase of quantities involved. I cannot simply, here if I have I, this is I1, I2, I cannot simply write that, I cannot do the algebraic summation. Let's say this is, as I have mentioned previously, 5 ampere, then this will be 2 ampere, then this will be 3 ampere. No. Currents have their phase difference, so I cannot do algebraic addition. I have to do phasor, complex addition. But one thing is for sure, these are phasor quantities. But if let's say these are instantaneous quantities, if these are instantaneous, not phasor, these are instantaneous, so at an instant KCL will always be valid. So what do I mean by at an instant? Let's say that this is 5 sin omega t, right? This value is 5 sin omega t, and if I say that this value, like hypothetically, is 2 sin omega t, then for sure this will be 3 sin omega t, hypothetically. Okay, for sure this will be 3 sin omega t. You will say, sir, you have just simply done the algebraic addition here, like you just applied KCL here algebraically, you did not do any phasor. Why? Because these are all my instantaneous values, right? These are all instantaneous, like time is involved. But whenever I write here 5 angle 90, 2 angle 30, this will not be 3, right? Because this is not a instantaneous value anymore. This has become phasor value. This is a phasor quantity. Okay, I have went more in depth in my full course. Of course, like we don't have enough time here, so that I will not be able to go too much in depth, but I hope it is clear. If it is clear, then tell me in the comments below, yes sir, totally clear. Finally this doubt is gone, right? Difference between instantaneous quantity and phasor quantity. Okay, so now you can do the same carbon copy ditto analysis for RC circuits. Okay, for a series RC circuit, what will happen? Your reactance will be negative because capacitive reactance is negative. So your circuit will be leading. Power factor will be cos phi, that is correct, but it will be leading circuit. So if you see, the resultant voltage will lag the current, or I can say in other words, the current leads the resultant voltage. You will apply the same KVL. You will observe that the current leads the resultant voltage. That means it is a leading circuit. Okay, same analysis for a RLC circuit. It depends. Your circuit will be overall lagging or leading. All of it depends between the values of XL and XC. What is XL? Omega into L. What is XC? 1 by omega C. Now it all depends. If XL is greater than XC, the inductive reactance is greater than the capacitive reactance, then circuit will behave as inductive in nature. If the capacitive reactance is greater than the inductive reactance, then the circuit will behave as capacitive in nature. Okay, these are the differences basically. Okay, I hope it is clear, and accordingly you can solve. Once you know which one is greater, accordingly you can solve the simple RL circuit or RC circuit. If XL is equals to XC, if XL is equals to XC, what will happen? Then the circuit becomes purely resistive. When will it happen? When overall the components will cancel basically. The capacitive component will cancel the inductive component. Then this voltage drop will cancel out this voltage drop. Overall, the circuit will behave as purely resistive. There is no imaginary part. So what is the power factor angle? Power factor angle is 0 degrees. There is no phase shift between theta A and theta V, because overall this is giving me plus, let's say this is plus J2, right? This reactance is plus J2 and this reactance is minus J2, right? So overall the sum is coming out to be 0. So overall the circuit, as if it is behaving as purely resistive circuit, as if, although actually it is not purely resistive, but as if it is behaving as purely resistive, because these two are cancelling each other out. Okay, I hope that part is clear. So that is the third case. For the other case I have already explained. Okay, one more thing is there, like you already know, if things are connected in series. For simple DC network, if resistors are connected in series, you say R equals to R1 plus R2 plus R3, right? Same will happen for impedance as well. Impedance is including the AC impedance, right? AC impedance is also included over here, not only the DC, not only the resistance, the imaginary component as well. So same for a series connection, Z equivalent will be Z1 plus Z2 plus Z3, and your for a parallel circuit it will be 1 by Z1, 1 by Z2, 1 by Z3, right? These will be the equivalent values. Okay, so yeah, so the phasor relationship of parallel RL, RC and RLC circuits we have already discussed over here. Like we have discussed about the series. Now we will discuss about the parallel circuits, right? Now for a parallel circuits, your reference will be what? Your reference will be voltage. For a series circuit, what was my reference? Current. For a parallel circuit, my reference will be voltage. Why? Because the voltage is same across, like if I know the voltage across these 2 points, same voltage here, right? So the voltage is same throughout. That's why I will assume my voltage to be my reference, and my current will not be reference anymore, because previously current was same throughout. Okay, so my voltage will be my reference. Okay, so I hope it is clear now. Voltage is my reference. So in this case, what I will use KCL. If I use KCL, I know that this current, incoming current, will be equals to IR, IL. Remember, these are all phasor quantities. That's why I have given here bar. Now what is IR? What is my IR? IR will be nothing but VR by R, right? Simply voltage upon resistor. Now what is VR? VR is nothing but the V, and V is assumed to be my reference, right? V angle 0 is assumed to be my reference, V by R. And what is my, just give me 1 second, what is my IL? IL will be simply again V upon V angle 0 upon XL, right? Now what is XL? XL is actually, it is a component J omega L. J omega L. Okay, so this will be minus J V angle 0. So omega L, right? Because I have just taken it to the numerator. So what happens is, the voltage, like this current, right? Actually this is the angle of the current. So this is V upon omega L minus 90. So the current actually lags the reference. So this is my IR. IR will be in the same phase along V. V is the reference now. V is the reference. It is in the same phase along, like IR is in the same phase along V. But the current across the inductor will lag the voltage by 90. Right? So it will be minus 90. So it is here. And that is the property of inductor. The current should always lag the voltage by 90 degrees for an inductor. That is what is happening over here. What is the resultant current? Resultant current will be the sum of these two, that will lie here. Overall the current is lagging again. Again the current comes out to be lagging. It is lagging the voltage. So circuit will be lagging, right? And yeah, you can calculate all this magnitude of I, angle of current, right? Again you can calculate the power factor angle. Remember this will be opposite now. Now if you calculate, the formula will be Z by R. That's why I don't recommend remembering this formula, but it's good to know because it will come in handy, because in most cases it will, like your power factor, like your circuit will be a series RLC circuit, so that is helpful actually. But remember your power factor angle changes, but this method will never change. Find out the angle between voltage and current, then take the cause of it, that will be your power factor. Okay, so for the other circuits, for for RC circuit I'm giving you as homework, you can do the same thing, right? And for RLC circuit also you can do the same thing. Okay, again there will be three cases. Once my in this case things will be a bit opposite actually. One more point I want to say actually here, that in a circuit, right, in a circuit, in a series circuit, let's say this is 1 ohm, this is 100 ohms. We know in a series circuit the higher value dominates. So the voltage drop across this, if this is let's say 101 volts, the voltage drop across this will be 100, this will be 1 volts. So this actually dominates in a series circuit. So higher value wins in a series circuit. In a parallel circuit actually things are quite different, right? Let's say this is 1 ohm, this is 100 ohms, right? And if I have a current source over here, 1 ampere or 101 ampere, then we know that 100 amperes of current will flow through the 1 ohm because it provides the least resistive path, and 1 ampere of current will flow through here. So I can actually neglect this, right? So that is what is happening over here as well. The lower value will dominate, right? So in case of a parallel RLC circuit, if my okay, have I mentioned it over here? Okay, I have not mentioned it. Should have mentioned it actually. So we have actually taken the current, we have compared the current, because if IC is more, that means the circuit will behave as capacitive. When will IC be more? IC will be more only if my reactance is lower, right? Whichever one is lower, that will take more current. So IC will be, because voltage is fixed. So if XC is less than XL, then only my circuit will behave as capacitive. Now this is just the opposite of a series RLC circuit, because series RLC circuit and parallel RLC circuits are dual of each other. Okay, just the opposite. So and here, like you can find out the condition, if your XL is less than XC, then circuit will behave as lagging this time, because more lagging current will flow, and here circuit will behave as capacitive in case A. Okay, just be careful regarding all these things. So that was a bit, like you can calculate the impedance, all those things you can do. This is the summary basically. What are the different angles, what happens in series RCRL, all have been summarized over here. Okay, so yeah, all these things I have already explained. So let's now do few questions. With this we will end our first chapter. So I will show you the like pictures of all the questions, right? 5, 6, there are many questions here, many, we will do many questions actually. Then okay, this is another question, this is another question, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, that's it. So these are the questions. You can try these questions out after all this, and we will solve them one by one. Okay, so let me solve this one. The current in the RL circuit shown is given to me. This is a simple RL circuit. The value of the inductor, what will be the value of the inductor? Okay, there are many ways to solve this, right? One way to solve this will be to find out the impedance. What is the impedance? Impedance will be V upon I, right? And if, remember, if here we have used 10, right, I can convert this into phasor format. What will the phasor format? 10 angle minus 5 by 4. If I am writing the peak here, so the voltage also should have the peak. If I am writing the peak over here, right, current as peak, then the voltage magnitude should also be the peak. Okay, I hope that is clear. So what will be the conversion of voltage in phasor format? So I have assumed that my cos 5t to be my reference, right? Cos 5t to be my reference. Okay. So with respect to cos 5t, I am minus pi by 4 and the amplitude is 10. With respect to 5t, this angle is 0, amplitude is 200, because I have assumed that the peak value is the magnitude here, right? That is my assumption. Now I can simply do this phasor, right? V upon I. So this will be 200 angle 0 upon 10 angle minus pi by 4. Okay, 10 angle minus pi by 4. So this will be 20 angle plus pi by 4. So this is the impedance basically. What have they asked? They have asked the value of the inductor. How can I calculate the value of the inductor? For a series circuit, right, we have derived this. The magnitude of the inductor, right, magnitude of the impedance will be R square plus XL square, because it is only a purely inductive network. So this will come out to magnitude, I already know, that is 20. I can square it. 20 whole square will be R square. R is given to me. R is given to, no, R is also not given to me. Okay. R is not given to me. So I know the impedance angle. It is coming out to be positive. It has to be positive. For an inductive circuit, the impedance angle will be positive. So I know this, right? If I draw the impedance triangle, this will be R, this will be JXL, and this will be my impedance, and this will be my phi, right? So I know tan of phi will be like altitude upon the base, and tan phi is pi by 4. So what is pi by 4? 45. What is tan 45? 1. So simply from here I can say that tan 45 will be 1. So R will be equals to magnitude of R will be equals to magnitude of XL. So R will be equals to XL. Okay. So simply I can convert this, right, into XL whole square plus XL whole square, because both are same. R and XL are same. So from here I can directly say that 2XL, right, will be 20. Sorry, yeah. 2XL whole square will be 20 whole square. If I take the under root on both sides, this will be 20 upon root 2. So this will be, I will only take the positive solution because inductive reactance will be positive. This will be 10 root 2, and 10 root 2 will be the answer. No, they have asked me the value of the inductor in Henry, in H Henry, right? What is inductance value? What is XL? XL is omega into L, right? What is omega? 2 pi into F, and omega is given to me actually from the waveform current. If either you see current or the voltage, both have same omega 5. So omega is 5 into L. L I don't know, but XL I definitely know. XL is 10 root 2, or your L will be 2 root 2. L will be 2 root 2. So it will be 1.414, or I can say 1.414 into 2. So 2.828 Henry. This will be your answer. So this is not even an old question. This is a recent question, and they have actually asked you all the concept almost. Question is simple, but they have almost asked you all the concept, right? Omega, L, everything they have asked you. So just be careful regarding these things. Now we have to calculate this we have to solve this question. The RMS value of the phasor current I. What will be the RMS value of the current? Remember, what is the RMS? RMS is the peak upon root 2. For a sinusoid or cosinusoid, it is the peak upon root 2. So I will calculate my phasor current, and from there I can write down my RMS value of the phasor current, right? This is a series RLC circuit. Okay. So one thing I can notice, because they're asking me to find out the RMS, let me convert this into phasor and let me put the RMS value. Let me not put the peak value, because that will be directly my solution, right? So if I convert this phasor into, if I convert this cosinusoid into its phasor, let us assume, what is my reference? Reference is cos 1000t. Okay. Reference is cos 1000t. What will be the equivalent, phasor equivalent? This will be 100 angle 0. Why 100? Why not 100 root 2? Because I am writing the RMS. I am not writing the peak value, I am writing the RMS. If I convert this back into my cosinusoid, I will multiply this value by root 2. Okay, because they have asked me RMS, so that's why I am converting my phasors into RMS. So ultimately, when I will solve the answer, whatever will come in the magnitude, that will be directly my RMS and not the peak value. Here the value was peak. So you have to be smart whether you want to choose RMS or peak value. Because they have asked me RMS, so I will convert this into RMS. If they would have asked me peak, so I would have written here 100 into root 2. Okay, I hope that part is clear. Now the voltage I know. What about the current? How will I find out the current? So what is the equivalent impedance for a series circuit? It will be R plus J into XL. Okay, the inductive reactance minus XC, the capacitive reactance. Okay, inductive reactance minus capacitive reactance, right? So R, I already know R is 100 ohms. What is the inductive reactance? Inductive reactance will be omega into L. Omega is 1000. L is 100 millihenry. So milli into 1000 will be cancelled. This will be only 100. Okay. What about XC? XC is 1 by omega C, right? XC is already negative sign I have taken into consideration. XC is 1 by omega C. So omega is 1000. Omega is 1000 and C is 10 into 10 raised to the power minus 6. 10 raised to the power 6 will come at the top here. Right. So this will be 10 raised to the power 100. This will be 100, right? 100. So this will be again 100. Actually, like interestingly, both are cancelling each other out. Okay, things are becoming simple. So my impedance is only a real quantity that is 100, right? So what will be your current? Phasor current. Phasor current will be voltage, phasor voltage upon the impedance. That is this phasor voltage was 100 angle 0 upon 100. It is only real. So this will be 1 angle 0. What is this one? This one is the RMS value of the current, not the peak, because initially I had assumed my magnitude will be the RMS component, not the peak. So this will be RMS. So 1 actually is the answer only. So RMS value of current will be 1. That is the answer for this particular question. It is the condition of resonance where XL is equals to XC, right? And most cases in EC as well, you will see the condition of resonance will get applied, that XL will be equals to XC. Let's solve the next one. In the given circuit, the value of capacitance that makes the current 0. What will make the current 0? Okay, current I0, this current 0. How can I make this current 0? Okay, now one thing you remember, that if let's say I have two impedance over here, right? And if this is plus Z, this is minus Z in series together. What is the overall impedance? In series, impedance gets added. So what is the overall impedance? 0. So what will be the voltage drop? It does not matter whatever is the current. I pump in some current here, right? I will pump in some current I. What will be the voltage drop? Voltage drop I, overall voltage drop here, right? V will be what? I into Z, overall impedance, Z equivalent, and Z equivalent is 0. So it will be 0. So I can make the voltage 0 in a series combination by connecting an impedance of negative sign. How will I make it negative? Capacitance and inductive, right? So capacitor and inductive are both opposite, right? They cancel each other out. That's how I can make it negative. Not I cannot connect obviously minus R because I don't have active components, but with XL and XC I can do it, right? So that is for a series circuit. For a parallel circuit, what happens is if I have a Z over here and minus Z over here, can you tell me what is the impedance seen from here? It is infinity actually. How? So equivalent impedance will be Z into Z1 into Z2 divided by Z1 plus Z2, that is Z into minus Z divided by Z minus Z. So it is actually constant upon 0, right? So which is actually infinity. So impedance seen is infinite. What does it mean actually? It means nothing, but if I have a voltage here, right? If I put a voltage source V, the current will always be 0 because the higher the impedance, there will not be any current flow, right? So if I provide some voltage V, there will not be any current flow. What is happening? Actually, what is happening? Whatever current that is flowing here, this, like it is just flowing in this loop basically. This voltage, right? This is V upon Z. This current is flowing, and the same current is actually flowing V upon Z here. No current is coming from this node actually. Although there is some current, that current is flowing in this loop itself. It is not coming from this supply side. Okay. So overall current is 0. So now let's come back to the question. They are asking us, how can I make this current 0? So I can make this current 0 if I somehow make this impedance infinity. How can I make this impedance infinity? This one is providing plus J5. I need this combination to provide minus J5, right? Minus Z. So I need this combination to provide minus J5. So what is this combination? It is a combination of an inductor plus J and a capacitor, right? Minus JXC, and overall the reactance should be minus J5. Overall impedance should be minus J5. So from here I can get the value of XC. What will be the value of XC? XC will come out to be 10. Value of XC will come out to be 10. Then only this impedance will be overall infinity. No current will flow. Even for a finite voltage, no current will flow. Okay. So XC comes out to be 10. What is XC actually equals to? It is 1 upon omega C. Omega is given to me, that is 5 kiloradians. 5 kiloradians, 10 cube into C, that is equals to 10. So from here I can get my value of C. C will be what? C will be 10 raised to the minus 4 divided by 5. So this will be 100 into 10 raised to the minus 6, which is known as microfarad, divided by 5. So it comes out to be 20 microfarad. 20 microfarad. Okay. So you can, I hope you know how to convert units. Like these things are known to you. How can I convert this into units? Okay, I'm just converting this into units. So this will be 20 microfarad. 20 microfarad will be the answer for this question. Okay. Yeah, let's move to the next question. So this question is again interesting. This question came in GATE EE. So a signal generator having a source resistance of 50 ohms is set to generate a 1 kilohertz sine wave. Okay. So a signal generator, I have a signal generator. Source impedance means this source resistance. Okay. It generates a sine wave of 1 kilohertz and it has a source resistance of 50 ohms. The open circuit peak to peak voltage is 10 volts. What do I mean by open circuit? If the load is like if the source is open circuited, right? The peak to peak voltage is 10 volts. That basically means there is no current flow, there is no drop. When there is no drop, the peak to peak voltage is 10 volts. That basically means its peak value is 10 sinusoid, right? So peak to peak 10 volt, peak to peak. Okay, sorry, that does not mean like, okay, one more thing I forgot to tell you. What do we mean by peak to peak, right? So peak to peak means this is one peak and this is the other peak, right? So the peak to peak value they have given me as 10. What is the amplitude? It will be half, right? Peak to peak is 2 Vm actually, plus Vm minus Vm. So peak to peak is 2 Vm. What is the amplitude? Vm. So this will be half, basically half of 10. So amplitude will be 5. And I already know the frequency 1 kilohertz. So I will just write here omega Later on I will write what is omega equals to. Omega is equals to 2 pi f. Okay, so the source voltage is 5 sin omega t. Indirectly they had not given you the source voltage, they wanted you to find it out. They wanted you to find the source voltage out. Okay, now connecting a capacitor across the terminals reduces the voltage to 8 volt peak to peak. So if I am connecting a capacitor across the terminals, it reduces the voltage to 8 volt peak to peak, or we can say the voltage across the terminals of the signal generator goes to 5, like 4 sin omega t plus theta, because of course phase will change, there will be some phase shift, right? Peak to peak value is 8, but peak value will become 4 because it will be just the half. Okay, they're asking me the value of this capacitor. What will be the value of this capacitor? How can I find out the value? So previously, basically magnitude of Vs is 5. Now magnitude of this uh, like terminal potential, let me write it as Vt, has now become 4, the peak value. Okay, so again everything is peak, right? So I can take the ratio. So what is magnitude of Vt upon magnitude of Vs? It is nothing, the terminal voltage is nothing but the voltage across the capacitor. So it is magnitude of Vc upon magnitude of Vs. It is simply a series RC circuit. So for a series RC circuit, the voltage is along the current reference, इसमें current, and the capacitor voltage will lag the resistive voltage, correct? Or the lag the current, because capacitor current leads the voltage, that's why it will lag. So what will be this ratio Vc upon Vs? It will be nothing but, what is Vc? Like this is simply a series RC circuit, right? What is Vc? Vc is simply the current into the capacitive reactance magnitude divided by the current into R. Okay, current into R, current into capacitive reactance. Okay, so now what will happen is, current are same in a series circuit, current is same, so it ultimately becomes Xc upon R. Sorry, not R, sorry, current into Z. The source voltage is basically whatever is the impedance that I am seeing from the source, it is Z, right? Z. So what is magnitude of Z? Magnitude of Z will be simply R square plus Xc square, correct? Magnitude of Z will be R square plus Xc square. So this will come out to be, Xc is what? Xc I don't know. Yeah, Xc is what I have to find out. Okay, I already know the voltage Vc and Vs. So it is 4 by 5, that is 0.8 equals to Xc. I can take this square, right? I can take this square, Xc whole square plus R square. What is R? R is 50 ohm. So this will be 2500 plus Xc square. And this also will be squared basically. I am squaring both sides. So this will be 0.64 and plus 1. So 0.36 Xc square equals to 0.64 into 2500, 1600, right? So this divided by 0.36, I'm just doing the calculation, under root comes out to be, Xc comes out to be 66.67. Now they have not asked me this value, they have not asked me the capacitive reactance, they have actually asked me the capacitance value. What will be the capacitance value, right? So what is the capacitance value? So the capacitance value will be simply 1 by, Xc is 1 by omega c equals to 66.67, where c will be equals to 1 by omega, omega is 2 pi into f, f is 1 kilohertz, so it will be 10 cube into 66.67. Now you have to check, go back and see in what units they have asked. They have asked me in microfarads, so I'll convert this into micro, so I'll multiply by 10 raised to power 6, so this will be 10 cube divided by 2 pi into 66.67. Okay, so this into 2 into pi into 10 cube, so 2.38. So 2.38 microfarad will be your answer for this question. This will be answer for this question. Okay, I hope it is clear. Now let's move on to the next one. Okay, so here we have to like consider the circuit shown in the figure below with input Vt in volts. The sinusoidal steady state current It flowing through the circuit is shown graphically. Okay, the steady state current It flowing through the circuit is shown graphically. Okay, and the input is sin t, right? So if the input is sin t, this is at time at t equals to pi by 4. At t equals to pi by 4, what I am saying, I'm observing a zero crossing point. But actually, what is my original sine wave? Original sine wave at t equals to pi by 4, what we should have observed? We should have observed 1 by root 2, right? So zero crossing point, like at t equal to 0, right? It should have been 0. My voltage, I'm talking about the voltage, because my voltage is simply sin t. So voltage will start somewhere from here, correct? Not this far ahead. Yeah, voltage will start somewhere from here. Yeah. Okay. So what is like why voltage will start earlier? Because at t equals to pi by 4 there is a zero crossing point, right? It is also a sine wave, but at t equals to pi by 4 there is a zero crossing point. If I want to write this expression, right, in terms of sinusoid, what will be it? It will be sine omega t. In this case, like frequency should be same, sine t minus pi by 4. Because at t equals to pi by 4 the waveform is 0. So at t equals to pi by 4 the waveform is 0. So it is correct. So what is happening? Our current, like this is the waveform of the current, and the peak values are also shown actually. The peak values are 1 by root 2 to minus 1 by root 2. So the amplitude will be 1 by root 2. Okay. So the current amplitude has changed obviously, and the current lags. So overall this has to be a lagging circuit. This cannot be a leading circuit because current is lagging. So they're asking me the current flowing is shown. The element Z can be, it can be a capacitor, inductor. No, it cannot be a capacitor. It cannot be a capacitor because current lags the voltage. I see that current is lagging, right? Current is coming later, voltage is coming earlier. So current lags the voltage. So there is no possibility of capacitor, only inductor. Now out of this, which one will be correct? For that we have to solve. How can I solve? Again, I know the, like what is the phasor format. If I assume my sin t to be my reference, this will be 1 angle 0. Again I have assumed the peak value to be the magnitude. So here also the peak value will come. So what is the peak value? Peak value is 1 by root 2. And what is the phase? Phase is minus pi by 4. Phase is minus pi by 4. Okay, this is the phase basically. So I hope it is clear. And now, yeah, this is 1 by root 2 minus pi by 4. Now, what we will do is, yeah, so what is the impedance seen by this source, like Z equivalent? It will be magnitude of, like it will be magnitude of V upon magnitude of I, right? Or I can write this in phasor as well. The impedance also will come out to be in phasor, no problem. Just give me a bit of time. What is happening, man? It is lagging too much nowadays. This thing is lagging too much. It's not usable at all. Okay, V is 1 angle 0, right? V is 1 angle 0 and I is 1 by root 2 angle minus pi by 4. Okay, so these are all phasor quantities. Remember, these are all phasor quantities. So this will come out to be root 2 angle plus pi by 4. Okay, root 2 angle plus pi by 4. Okay, so what I can do is I can start So this is my impedance, right? I can, an impedance, it is a series circuit, right? And it is inductive circuit. So this will be R plus jXL. So I can convert this into rectangular format. So root 2 cos pi by 4, cos pi by 4 is 1 by root 2 plus sin pi by 4, it is also 1 by root 2. Like, I hope you know how to convert polar to rectangular. That I have not explained because it is a crash course, right? Crash course kind of thing. So R plus jXL, right? This will be, R will be equals to like if I compare the real terms, 1, XL also will be equals to 1, right? But they have not asked me the inductance, they have asked me the, sorry, they have not asked me the inductive reactance, they have asked me the inductance. So XL is equals to omega into L, right? Omega into L. Omega in our case is what? Sin t. What is the coefficient of t? 1. So it will be 1. So L will be equals to 1 divided by 1, that is 1 Henry. L will be 1 Henry, that will be the answer for this question. Option B will be the correct answer for this question. Let's now solve the next one. Okay, let's solve the next one. It is a iron question. The voltage Vs is given, has an internal resistance of 50 ohms. Okay, although they have not shown it, but it has an internal resistance of 50 ohms, so we have to redraw the circuit. They have not shown it, right? They have just given me this R and R value, but they have not shown me the internal resistance value of the source. So I have to convert this, like convert this voltage source into its equivalent circuit. The RMS value of the current through the R will be, so basically they are asking me the RMS value of the current. So if I redraw the circuit, right? So if I redraw the circuit, this will be the voltage and it has an internal resistance of 50 ohms. And here I have the resistance 25. Then I have this uh, inductance and capacitance. So let me check whether these are cancelling each other out or not. Let me check it, right? So what is the inductive reactance XL? It will be omega into L, right? So L is this 1 by 20 into like 1 by 20 pi millihenry. So omega is 20,000 pi, right? 20,000 pi or 20 kilo pi, and kilo and milli will be cancelled. So this will be 20 into 20 pi into 1 by 20 pi. So this will be 1. What about XC? So XC, like in most cases, right? In most cases, what will happen? Your XL and XC will get cancelled. That is the 90% chance that will happen in your examination. But sometimes they might not get cancelled. Then you have to solve rigorously. And XC will be what? XC will be 1 by omega C. Omega again is 20 pi kilo. Again, this is milli. So kilo and milli will be cancelled into 1 by 20 pi. Right? Again 20 pi, 1 by 20 pi will be cancelled. Okay. So this will be 1 ohm. So again I am observing XL and XC are equal, but obviously they will cancel each other out because this is plus J1, it is minus J1, right? Plus J1 minus J1 will get cancelled. So ultimately it will be 0. Ultimately it will be 0. Okay. So XL and XC will be 0. So these will be 0 basically, right? So ultimately this circuit is gone. Plus Z minus Z, it is short circuit. So ultimately your circuit is behaving as a purely resistive circuit, right? It is gone. So here I have R, pardon my drawing, 25. Okay. So now can I find out easily, now can I find out the current easily? Yes. It is 10 root 2 whatever sine omega t, I don't care. So what will be the current? Current will be voltage upon the overall impedance, that is 100 in this case. So 10 root 2 sine omega t divided by 100, because 50 plus 25 plus 25 is 100. So it comes out to be root 2 by 10, and remember they have asked me in milliamperes. So this is in amperes. If I want to convert this in milli, what do I need to do? Multiply by 1000. So I will multiply by 1000. Okay. So if I multiply by 1000, this will be in milliamperes. So this will be 100 root 2 sine of omega t. Now what have they asked? They have asked me the RMS value of the current. What will be the RMS? RMS will be peak divided by root 2. So this will be 100 root 2 divided by root 2, 100. So 100 will be your 100 milliamperes will be the answer, because they have asked me the RMS value of the current. 100 milliamperes will be the answer for this question. Okay, in 90% of the cases your XL will be equals to XC and both of them will get cancelled. Okay, let's now solve the next question. This is a BM question, gate BM question. Okay, for the circuit given below, choose the angular frequency omega naught at which the voltage across the capacitor has maximum amplitude. Okay, for the circuit, choose the angular frequency omega naught for which the voltage across the capacitor will have maximum amplitude. When will the voltage across the capacitor will have maximum amplitude? How can I calculate it? So we can write down what is the voltage across the capacitor. Voltage across the capacitor VC will be equals to I into XC. Okay, and all of them are frequency dependent quantities. What is I? I is nothing but supply voltage divided by the impedance. What is impedance? Impedance is V upon, as it is a series circuit, right? Series RC circuit, R square plus XC square. Okay, so this will be basically, because magnitude of voltage is constant, your supply is constant, right? Only your omega naught is varying. Your omega naught is varying. Okay, so this will be magnitude of V into XC divided by under root of R square plus XC whole square. Correct? And what is your XC? XC is 1 by omega C. Correct? So this will be 1 by omega C, right? If I convert this into 1 by omega C, this will be under root R square plus omega square C square plus 1. Because what will happen, this will be 1 by, like I hope we can do, this will be 1 by omega C, right? And this also will be 1 by omega square C square. So automatically this omega C, right, will come inside this under root. So this will get squared. This will be omega square C square and this will get cancelled. So this will be 1. Now tell me when my capacitor voltage is maximum. When is it maximum? When the numerator, because the denominator, the numerator is fixed. The denominator, whenever the denominator will be minima, the capacitor voltage will be maxima, right? When the denominator is the minima, capacitor voltage will be maxima. Okay. So now for what value of omega square, this will be minima, right? Omega square, this has to be lowest. What can be the lowest value? Omega cannot be negative, right? Lowest value will be 0. So omega has to be 0. At DC, basically, the voltage across the capacitor will be maximum. Intuitively, can you understand this? Of course you can. At DC, this will provide the highest impedance. We know in a series circuit, right, the higher impedance will dominate the voltage drop. So I want the voltage across the capacitor to be highest. So for that, the impedance provided by the capacitance should be highest. When does it provide highest impedance? At DC, because what is the impedance? 1 by omega C. When omega is 0 at DC, it will provide me the highest impedance, highest voltage drop. So intuitively also you can say that at DC, the voltage across the capacitor will be maximum. Okay, let's solve the next one. Again a BM question, like similar question only, same question only, but few things are different over here. Now they are asking the amplitudes of the voltage across the resistor and the capacitor are equal. Like I can solve it using lengthy, but easier way, how can I solve it? So amplitude of the voltage of the capacitor and the resistor will be equal. So magnitude of VC and magnitude of VR will be equal. This will be 1, right? These are equal basically. When does it happen? So what is VC? VC is I into XC. What is VR? It is I into R. It is a series circuit, right? Current will be same. So basically XC by R will be equals to 1, or your XC will be equals to R, or your impedance angle will be pi by 4. Then only the voltage across the capacitor and, sorry, minus pi by 4 actually, because it is a capacitive network. Then only the voltage across the capacitor and the resistor will be same, minus pi by 4. Okay. So XC has to be equals to R. I know R. So XC has to be equals to 1 kilo ohm. And what is my XC? XC is 1 by omega C. or 1 by omega naught into C, and C value is given 100 microfarad. Okay, so 100 microfarad, this will be 10 raised to power minus 4, and this will be 10 cube, right? So omega naught will be equals to 1 kilo, so this omega naught will come out to be 10, simply 10, right? This, because this is 10 cube, 1 kilo means 10 cube, and this is 10 raised to power 4, so 10 cube will get cancelled, only 10 will be left, omega naught will be 10. So 10 radian per second will be your answer for the question. Okay, that's how simple the questions are. I hope now you are feeling confident. Okay, with the revision series, I hope now you are feeling the confidence that what will be the answer. Omega naught will be 10 radian per second. Okay, so yeah, if you are feeling confident, make sure to drop a comment below. Okay, you are feeling confident. The source in the figure is a current source, and the circuit is in steady state. Okay, circuit is in steady state at t equals to 0.5 pi seconds, the value of V in the circuit. How will I find out the value of V in the circuit at t equals to 0.5 pi? How will I solve it? So first of all, you convert everything into phasor. So assumption is, this is my current source and my sine 2t is my reference, right? Sorry, not sine 2t, sorry, sine t. Sine t is my reference. So this will be 1 angle 0. This will be the resistance. Okay, I have the inductance. So what is the inductive reactance? 1 Henry is the inductance. What is the inductive reactance? 1 ohm, right? Inductive reactance is 1 ohm. What is the capacitive reactance? 1 by omega c. Omega is 1 in this case, right? Omega is 1. So this will be plus j, right? Plus j. This will be minus j, and this will be 2 ohms. So in most of the cases you will see these will cancel. Now I have plus z plus j over here, minus j plus z minus z. This means this is providing infinite impedance. This is providing infinite impedance. All of the current will flow through the resistance. All of the current will flow through the resistance. It is nothing but the condition of resonance, which we'll study obviously in the next to next chapter. But this is plus z minus z, so of course this will get cancelled. All of the current will flow through the resistance, right? So what are they asking? They are asking me the voltage. So what is the voltage here? Voltage will be 1 angle 0 into 2, right? This is frequency independent. So voltage is 2 angle 0. Now if I convert it back into sinusoidal format, remember this was peak actually, because here the peak was 1. So this will be 2. There is no phase shift, sine of t. Now I will solve. Now what they are asking? They are asking me the value of the voltage at t equals to 0.5 pi. So I will replace t equals to 0.5 pi. This will be 2 sine of 0.5 pi, that is nothing but pi by 2. What is pi by 2? Pi by 2 is 1. Sine pi by 2 is 1. So it is 2. So simply your answer is 2. In most cases you will see something like this, right? Either it will be plus z minus z, or in parallel or in series. Okay, in maximum most cases, because your calculation will be even simpler. Okay, but conceptually you have to understand that actually. So that was the answer for this question. 2 is the answer for this question. Let's now solve the next one. In an experiment to measure the active power, okay, active power is there, right? So we cannot take this question because they are asking us to measure the active power. So we will skip this for now because we have not discussed what is active power, right? So let's solve this question. This question actually came in GATE 2025 EC paper. So like again, very simple question. Very simple question. What are they asking? The current IC, IL, IR are the currents to the capacitor, inductor, and the resistor respectively. Remember here, right? One interesting thing that they have done, they have given the admittance. They have not given the impedance. What is admittance? Admittance is inverse of impedance, right? This is the, that's why this is plus J, because it is inverse. Actually, originally what should be the capacitive reactance? It should be inverse of this, that is minus J4, right? Inverse of this is minus J4, and inverse of this is plus J10, and inverse of this is 5. Okay, that's why students will get confused, because they have given the admittance. So I have taught you every single thing, right, that is required. I have not skipped any concept. So here, what are they asking? The AC admittances are given in Siemens. Which of the following is true? The current IC is this, IL is this, IC, all these are, they are telling us. Okay. So what I can do is, okay. So I have to actually use the current division simply. I have no other option. I can use the current division. Or if they have given you the admittance, right, what I can do is, if I know this voltage is constant, same voltage is same across throughout, it is a parallel circuit, voltage is same throughout. So I know what will be the voltage, VC will be IC into XC, right, or IC into impedance provided by the capacitance, that is XC, I know internally. Now the voltage is simply V, right, voltage is simply V, constant throughout. I can say what is my IC, IC will be V divided by ZC, or it is V into YC, admittance provided by the capacitance, and what is YC, what is the angle of YC, plus J. So it will lead the voltage. Okay, that is one thing, that is one factor that you have to take care of. So V is constant, so V into J 0.25. What is your IL? IL is V by ZL, or same as V into YL, right, which is negative. So it will lag the voltage, current lags the voltage, so it will be minus J 0.1, and your IR finally, it will not have any phase difference, it will be 0.2 into V. So if I just take the ratio, right, if I just take the ratio of these two, let's say IC and IL, what will I get? IC by IL, right, IC by IL, V is constant, it will be J 0.25, because V is same, right, it is parallel circuit, minus J 0.1. So this J in the top, if it goes, it will be plus J. So this will be J square into 0.25 divided by 0.1, that is 2.5 basically, or minus 2.5. Okay. So the phase shift between IC and IL, or the ratio is minus 2.5. Is it coming here? Yes, it is coming minus 2.5. Yes, because the phase shift is 180, right? And if I take the ratio of the magnitude, it is minus 2.5. Yes. Now here, is it coming minus 2.5? No, it is like magnitude is 0.4, right? The ratio of IC and IL is coming out to be 0.4. No, it has to be 2.5. Magnitude has to be 2.5. Here, is it coming 2.5? Yes. The phase is also 180, correct. So this is also a possible answer. This is also a possible answer. Here 4 and 10, again no, incorrect. So these two are gone automatically. Let me, what do I observe? I observe that the ratio between the current of the inductor and the resistor again are same. Okay, these are same. So I have to compare the angles actually. I have to compare the angles. Okay. So what do I know is the current across the resistor will be same as the voltage. Same will be in phase as the voltage. Okay, will be in the same phase as the voltage, and this is nothing but a voltage source, right? It is 1 angle 90 volts. Remember, this is nothing but a voltage source, right? They have given me the voltage actually. They have given you the voltage. So actually you don't have to do all this, right? Without this also you can do, but if somewhat they would have given you current, then also you could have done this, but they've given you the voltage source. Okay, so what will be the current here? IR will be simply 0.2 into this voltage, that is 1 angle 90. So this will be 0.2 angle 90. So in both the cases the IR is 0.2 angle 90. So how will I find out IC? IC will be nothing but V upon ZC, or the admittance, or V into YC, right? V is given to me, that is 1 angle 90. YC, actually I did not have to do all this, right? Without this also I would have directly done it, but just in case, let's say if this was not voltage source, this was current source, then this is how you will solve. Take out the ratio and solve. Okay, because I don't know the voltage, but here I did not observe, actually the voltage is given to you, so you can directly find out IC. IC will be voltage into the admittance, so 1 angle 90, that is J into J 0.25, so which is coming out to be J square 0.25, which is minus 0.25, right? So 0.25 angle minus 180. So answer will be option A. The angle is not 270, angle is 180 because there is a negative sign. Okay, so option A will be the correct answer for this question. Okay, this will not be the correct. So option A will be the correct answer. Let's now solve the next question. So in this question, what they are telling us, that consider the circuit below. M1 is an ideal voltmeter and M2 is an ideal AC ammeter. One thing you have to remember, that M1 generally, if nothing is mentioned, right, you will assume that my ammeter and voltmeter both will read the RMS values. Ammeter and voltmeter both will read the RMS values by default. So M1 is a voltmeter, M2 is a ammeter. Okay, the source voltage is given to me 100 cos 200t. What will be the value of the variable capacitor such that the RMS readings of M1 is 25 and 5 ampere respectively? So if the voltage is 25 and the current is 5, what is the impedance? It will be the voltage, like this voltage is 25 RMS value and the current is 5. Okay, so this will be 25 by 5, which is 5 ohms. So overall impedance is said to be 5 ohms. So overall impedance is 5 ohms, which is equals to R plus J XL minus XC. It is nothing but a RLC circuit. So R is what? R is 5, right? R is 5. So R is 5. So XL minus XC has to be 0. So XL has to be XC. So what is XL? XL is omega into L. Omega is 200. L is 1. So 200 into 1 must be equals to XC. XC is what? XC is omega, that is 200 into C. So C will be equals to 1 by 200 whole square. Okay, 1 by 200 whole square. So it will be 10 raised to power 4 or 10 raised to power minus 4 divided by 4, or in microfarad I will multiply this by 100, 25 microfarad, right? 25 microfarad. Okay, I hope you can convert this into microfarad. I don't have to explain it to you. So 25 microfarad is option A. Option A will be the correct answer for this question. Let's now move on to the next one. So next one is this one. So 3 parallel admittances are given, YA, YB, YC, okay, connected in parallel with a voltage source as shown. Okay, so okay, 3 admittances, okay, they are not shown actually. 3 admittances are connected in parallel, like it is similar question, and a voltage source is given, YA, YB and YC. Again, if you see, like this is negative, this is positive, this is real, right? So that means this is resistance, this is capacitance, this is inductance. Okay, so I will have a capacitance, I will have a inductance, and I will have a resistance whose admittances are, like it is a parallel circuit because they have told me that 3 parallel admittances. So this will be 0.3 Siemens, and inductance will have negative susceptance, so minus J 0.2. Siemens, and capacitance will have positive susceptance, so plus J 0.4. Plus J 0.4 Siemens. Okay, and Vs Vs will be 10 angle 45. Okay, draw a current Is. So they could draw, all of them draw a current Is. The currents flowing through each of the admittance is IA, IB, IC. So IA, so okay, YA is what? It is the inductance, right? It is the inductance. So this will be IA, this will be IB, current flowing through the resistance, current flowing through the capacitance is IC. So IB plus IC is actually I. So I is equals to IB plus IC. Okay, so they are asking me to find out the phase relationship between I and IS. What is IC? IC is equals to your YC into Vs, right? In the previous question only we have done this. So what is YC? YC is plus j 0.4. Okay, let me keep it as it is. Let me keep it as it is. What is IB? IB is YB into VS. Voltage is same, right? What is IC? Sorry, IA. IA is YA into VS. So what will be your I? I will be IB plus IC, or YB into VS plus YC into VS. So I can take VS common. It will be nothing but YB plus YC. So YB plus YC. So it will be, what is YB? YB is this value, YC is this. So it is 0.3 plus j 0.4. Okay. What about IS? IS is the sum of all the currents, right? So IB plus IC is already 0.3 plus j 0.4, and IA is minus j 0.25. So it comes out to be 0.3 plus j 0.15. Okay. Now they are just asking you the relation between I and IS. So I can take the ratio. If I take the ratio IS upon I, or because I upon IS, I will do I upon IS because I has more reactive component than the IS, so it will lead basically. Okay, that is my assumption, because the real component is same, right? So it will lead. So I upon IS will be like if I convert this in phasor, right? Oh, can I convert this in phasor? So if I convert this in phasor, what is 0.3 plus j 0.15, right? If I convert this in phasor, so 0.15 divided by 0.3 tan inverse. So the angle is 26.56 degrees. That is the angle of IS. That is the angle of IS, correct? Yeah. And what about the angle of I? Okay. One small mistake. Okay. This is 0.2. Sorry. This is 0.2, right? This is 0.2 Siemens minus 0.2. Sorry. This will be actually 0.2 Siemens. So this will come out to be, if I subtract 0.2, this will be 0.2 only. Okay, sorry. So 0.2 upon 0.3 tan inverse. So it is 33.7. 33.69 degrees. Okay, that is the angle of IS. What is the angle of I? What is the angle of I? Angle of I is 0.3, 0.4. 0.3, 0.4. So 0.3, 0.4, right? So 0.4 divided by 0.3 tan inverse. So it comes out to be 53.13. Okay. So what will be the angle difference? What have they have just asked me the angle difference, right? Between I and I. So between I and IS. So I see I has more angle than IS. So I will lead IS, right? I will lead IS. I don't need to take care of magnitude because they are just asking me leading lagging. So first of all, I will lead IS. So either this is possible or this is possible. These are not possible. I will not lag IS. I will lead. Okay, because I has more angle, right? I has more angle. So I will just simply subtract 53.13 to 33.69. That will yield me 19.44, right? 19.44. Because why? Because if I take the ratio, the angles will be just subtracted. That's it. Magnitudes will be divided by the ratio, but the angles will be subtracted. So the angle difference, phase difference between I and IS is 19.44, and I will lead the IS. I will lead the IS. Okay. So option A will be correct. Option A will be the correct answer for this question. Let's solve the next one. So next one is this one. This is the last question actually. This is actually pretty interesting question. So a signal Vm of t is applied at the circuit shown. We have a switch as well, like it is a mixture of transient across the capacitor, and the voltage Vx is fed to an ADC having input impedance of 10 mega ohms resistance in parallel with zero point 0.1 microfarad capacitor. If the switch S is opened at t equals to 0.5 seconds, the value of the Vx at 1.5 seconds will be, what will be the value of the Vx at 1.5 seconds? So this question is actually pretty interesting. So we are applying this voltage at t equal to 0. This voltage is getting up before this, we will assume that it is 0. We are applying this voltage at t equal to 0 Vm, and they're asking me the value of the Vx at t equals to 1.5 seconds if I open this switch at 0.5 seconds. Okay, pretty interesting transient question. So let us try to tackle this question. So I can actually change this ADC because they have given me the ADC has an impedance of 10 mega ohms, right? So I can convert this circuit like this. This will be the AC source, this will be the capacitor, and this will be the resistance of the ADC. Now I will compare, it is 10 mega ohms, right? 10 mega ohms, so 10 raised to power 7 ohms. I will compare the reactance of the capacitance. How much reactance is the capacitance providing when the source was active? So have they provided me the, yeah, they have provided me the frequency, right? What is omega? Omega is pi by 3. Omega is pi by 3, right? Because I know the voltage source, from there I can find out the omega. So what is xc? Xc will be 1 by omega c. So 1 by pi by 3 into c. C is 0.1 microfarad. So 10 raised to power minus 6. So this will be 10 raised to power 7. So 10, like 3 into 10 raised to power, so almost like pi, almost similar, right? Like these impedances are almost same. Okay, these impedances are almost equal to each other, right? Okay, question is kind of, I feel the question is kind of incomplete, but let's try to solve it. Okay, so at 0.5, because I'm applying it like this is a like the impedance by the resistor is 0.5, but as I'm applying the voltage directly across the capacitor, right? I'm applying this voltage is getting applied directly across the capacitor. So as soon as the switch, like as I'm applying it directly across the capacitor, right, what is happening? So the voltage of the capacitor is same as the input voltage because I'm directly applying it across the capacitor, correct? Which is what? Which is simply 5 sine of pi t by 3. This is the voltage across the capacitor. Now at t equals to 0.5 seconds, I'm actually opening the switch. Now as soon as I will open the switch, right, capacitor will still hold its voltage. So what was the voltage at t equals to 0.5 seconds? So Vc at of t at t equals to 0.5 seconds, five sine pi by 6. Okay, pi by 6. So that is the voltage at 0.5 seconds when I'm opening the switch. So the voltage will be this value, whatever is this value, right? Sine pi by 6. Sine pi by 6 is sine 30 basically. So sine 30 is half. So the voltage across the capacitor is 2.5 volts. So this value will be what? This will be 2.5. Now if I read the question again, okay, just one small mistake I have made. We have to replace, if you see the ADC having an input impedance consisting of 10 mega ohm resistance in parallel with 0.1 microfarad. So overall the ADC can be replaced with a 10 mega ohm impedance and also a 0.1 microfarad capacitance. So it is not just the 10 mega ohm impedance. I missed this point. Okay, this one I missed. Okay, so now what is happening? The voltage at t equal to 0.5 is this. So now what I will do, I will just replace the circuit, right? I'll open the switch. If I open the switch, what will happen? This switch is open. So this capacitor is still there, right? This 0.1 micro is still there. This 0.1 microfarad is still there. Okay. This is the resistor 10 mega ohm, and another 0.1 micro is there, right? Because they have mentioned that the EDC can be replaced with a 10 mega ohm resistor and a 0.1 microfarad capacitor. So this will be another 0.1 microfarad capacitor. Okay, and initially the capacitor, this capacitor has a voltage of 2.5 volts, right? This capacitor has a voltage of 2.5 volts, right? That is the initial capacitance. Okay, now what will happen? Basically this 2.5 volts, right? At that instant, because this also has the same voltage, 2.5 volts, both of them has the same voltage, because it is just a parallel circuit, right? This Vx is same, but as soon as the switch will be closed, now what will happen? I can combine these two capacitors, right? These two are in parallel, so this will become, capacitance in parallel are simply added, 0.2 microfarad, and the voltage are same, that's why I can simply add them, right? Because the voltages are same, that's why I can simply add them, because all of the circuits are in parallel combination, because the voltage is connected directly across this C and another R and another C. Okay, so all of them are in parallel. So this will be 0.2 microfarad and the voltage will be 2.5 volts, and here I have the resistor, that is 10 mega ohms. Okay, now it is nothing but a simply RC discharging circuit. So the equation will be 2.5 e raised to power minus t minus 0.5 upon tau. So t, why 0.5? Because I'm opening the switch at 0.5, right? So all this has been taught to you in transient. I am not explaining here why this will be t minus 0.5. Okay, so t minus 0.5 upon tau. So tau is what? R into C. R is 0.2 microfarad. Sorry, C is 0.2 micro. So 10 raised to power minus 6 into R. R is 10 into 10 raised to power 6, right? Mega. So this will be actually 2. Tau is 2. Okay. So this will be 2.5 minus 1. Now t is 1.5. They are asking me to find out the value of voltage at 1.5. So 1.5 minus 0.5, that is 1 divided by 2. So e raised to power minus half. So e raised to power minus half, right? So 0.5 exponential into 2.5. So 1.52 volts, because they have asked me to round off to two decimal places. So 1.52 volts will be the answer for this particular question. Okay, this was a good question actually, both combining transient and AC. Okay, so with this we end our phasor. Now we will start with locus diagram. Let's start with locus diagram. So what does locus diagram basically means? Locus means it is basically the plot, graphical representation of multiple points in the graph. So a locus diagram is a graphical representation of how the impedance, admittance, current, or any quantity, any phasor quantity, either in terms of omega, okay, if omega is the variable, or if any other variable, right? How does my voltage, current, impedance, any of this vary with respect to a variable, plotting it on the imaginary and the real axis of that particular quantity is known as locus diagram. That's it. It is nothing but plot. It is nothing but a plot. One example is root locus. In control theory, we plot root locus, where we plot the locus of the closed loop poles by varying what? By varying the DC gain K, DC gain of the open loop transfer function. By varying the value of K, we see how are my closed loop poles varying. I hope if you have studied control systems, you can relate with this. Okay, so here we will not go into that complications. We will just simply see how my voltage, current, impedance, or any other quantity is varying with respect to frequency or with respect to any other parameter. Let's take a very simple example, 10 upon s plus 2. So whenever there is some s, right, s is known as the Laplace operator. You will learn more about this in signals and system. For network theory purpose, you will replace your S with j omega. S with j omega, that's it. You replace with S with purely imaginary quantum, that is j omega. Omega is the frequency. So we have to plot the locus of this Vs voltage V of j omega for the range omega varying from 0 to infinity. Okay. So what will be the locus? So in locus, right, there are two ways to solve. Either you directly solve it using rectangular format, you break it down into rectangular format and then solve, or you can directly solve using the polar format. Okay, so I will solve using both formats, polar and rectangular. So let's start with polar. In polar, what do I have? I need a magnitude and I need a phase. As we can see, I have a magnitude and phase. That is the polar format. So if I write my voltage, right, properly, V of j omega, this will be 10 upon j omega plus 2. Okay, so the magnitude of voltage V of j omega will be 10 upon omega square plus 4 whole under root. Okay, that is the magnitude. What about the phase? Phase, I hope you know how to calculate the phase. Phase will be, this will be like this, provides a phase shift of what tan inverse omega upon 2, but it is in the denominator. So in the numerator it will be minus tan inverse omega upon 2. Why omega upon 2? Tan inverse y upon x. Y is omega and x is 2, real part is 2. So this will be tan inverse omega upon x. So minus, because this is in the denominator, if I take it in the numerator angle, the sign will flip. So this will be minus tan inverse omega upon 2. Okay, I have to plot from 0 to infinity. Let me see at omega equal to 0, what is the magnitude? Magnitude is 10 upon under root 4, that is 10 upon 2, that is 5. What is the phase? Phase is nothing but 0, because like this will be 0, right? Tan inverse 0 is 0. Or you can see, if you put here 0 directly, this will be 10 upon 2, that is simply 5. So it is simply 5, phase is 0 degrees. Okay, so in the this V of j omega plane, where am I lying? Angle is 0, that is positive x-axis. The magnitude is 5. So at a distance of 5 from the origin, angle is 0, that is on the positive x-axis. So this will be 5. This will be the point at omega equals to 0. Okay. Now at omega equals to, I can choose any value. Let me choose a simple value. Let me choose omega equals to 2. At omega equals to 2, this will be what? This will be 2 square, that is 4 plus 4, that is 8. So 10 upon under root 8. Into 8. So 2.828. 2.828. So this will be 2.828. Okay. Yeah, 10 upon this, right? Sorry, this one mistake I made. So 10 upon, sorry, under root of 8. So this is not under root of 8, 8 inverse of this into 10. So this comes out to be, sorry, not this comes out to be 3.53, approximately 3.53. And what about the phase? So phase will be, how much phase is this providing? Tan inverse 2 upon 2. So that is tan inverse 1. What is tan inverse 1? 45. Minus 45, right? This is 145. So this will be minus 45. So phase is minus 45. Okay. So where I will lie? So I will lie at a distance of 3.53 from the origin. Angle will be minus 45. So somewhere here, right? The point will be somewhere here. Okay. This will be the point at omega equals to 2. Minus 45 will be somewhere here. Omega equals to 2. Now what else is happening? Now what I can say is, omega infinity, what is happening? At omega equals to infinity, this will go to 0. At omega goes to infinity, this will go to 0. At omega goes to infinity, how much phase will this provide? Tan inverse infinity. Tan inverse infinity is 90. Negative sign is there, so minus 90. So minus 90 is somewhere here. I am lying somewhere here. The angle is minus 90, but the magnitude is 0. So I am at a distance of 0 from the origin. So I am lying somewhere around here. This is omega equals to infinity. Almost in the minus 90 degrees, but magnitude is 0. So it is exactly almost equals to origin or exactly equals to origin. So if I complete the locus, locus will be somewhat like this. Okay, although it is not perfect here, it will be somewhat like this. This will be a semicircle. I will not prove in my full course. I have proven that how it is a semicircle, right? Actually, we will get a circle for a second order circuit. For a first order circuit, we will get a semicircle. Okay, for a first order circuit, we will get a semicircle. All this I have proved in my full course. So here I am not explaining this. Okay, so this will be the roughly the locus. So that is how you plot using the polar format. Using rectangular format also you can do. What you can do is, this is my voltage transfer function, right? So I can write this, I can rationalize this. This will be j omega 2 minus, I can multiply and divide by 2 minus j omega, correct? So 2 minus j omega okay, and of course I have to multiply and divide. This will be 2 minus j omega. So this will be 10. So okay, I need another, do I need another page? Yeah, I'll do it over here itself. So the equivalent will be 10 2 minus j omega. The denominator becomes completely real, right? This will be 2 square plus omega square. So 4 plus omega square, right? So I can divide this. This will be 10 upon 4 plus omega square. So sorry, 20 upon 4 plus omega square minus j 10 omega upon 4 plus omega square. Okay, so now what will be happening over here? So I can say that okay, so now you can simply see, right, how my, if I vary my omega, what will be the x coordinate, x value? This is my x coordinate, real part of, this is the real of v of j omega, and this is simply the imaginary of v of j omega, which is negative. So from here you can solve. Okay, so there are two ways to solve the locus diagram, that's it. Okay, these are written how to plot the locus. So we can plot the locus of impedance as well. I will plot the locus of impedance. Admittance also they can ask anything what they would like. Okay, I will do few examples and then we will directly move on to a single question. Only like 1-2 question has came in, like 3 questions has came in locus. Okay, so let's do this actually. So we have to draw the current locus diagram for the circuit given below. The current under the given circumstances, that when my omega is varying, in the second case when my r is varying. So this time my omega is not varying, r is varying. Okay, so if my omega is varying, okay, omega is varying, in this case what will happen, they are asking me to plot the current, right? So what is the current? Actually current will be the voltage upon the impedance. Okay, voltage is fixed, it is some phasor, voltage is fixed, right? It will not change basically. And what about the impedance? Impedance is r minus jxc, right? It will provide minus jxc, and jxc is 1 by omega c. Okay, I will sort that out. I will sort that one out, don't worry. So this will be what will be the magnitude? Magnitude will be v, magnitude of v upon r square plus xc whole square whole under root. okay, and your angle of I will be what? Angle of I, remember this is negative sign, y coordinate is negative, right? So this, what angle does it provide? This provides angle of minus tan inverse of xc upon r, right? And if I take this, like that is the angle of the denominator. So if I am talking about the numerator, right, I have to subtract from 0, I have to subtract this angle, right? Then only I will get my actual angle of I. So minus into minus will be plus, because I am taking it into the numerator, angle sign will be flipped. So this will be plus tan inverse xc upon r, okay. Now what is xc? The reactance is actually magnitude of the reactance. I have already taken the j portion, the angle portion I have already taken, is 1 by omega c, right? So if I replace here x equal to 1 by omega c, the equation, right, this will be changed actually. This will become v omega c upon under root r square omega square c square plus 1, and this will be tan inverse 1 by omega rc, okay. Tan inverse 1 by omega rc. Now we can simply vary our omega. So when our omega is 0, what is the magnitude? When omega is 0, the magnitude current, right, this will be simply 0 upon under root of 1, that is 0. So current magnitude also will be 0. So I don't have to calculate the angle. Still, if you want to, you can calculate the angle. What will be the angle? It will be tan inverse of infinity, 1 by 0 is infinity, which is plus 90. Okay, so I will start off from somewhere here. This will be my omega equal to 0 point, and at omega equals to, you can take any other value. So generally what I do is I take the basically cutoff frequency. Like I assume that my omega will be 1 by rc. So if omega is 1 by rc, then this will be under root 2, okay. So I can choose 1 by rc because I choose it just the inverse of these component, right? So this will become 1 by rc. So this will be under root 2, the denominator will be under root 2, the numerator will be what? Omega is 1 by rc. So cc will get cancelled. This will be v by under root 2r. Is it under root 2r? Yes, v by under root 2r. Yes, correct. Yeah. V by under root 2r, that will be the magnitude. So the magnitude of the current will be v by under root 2r, okay. What about the phase? Phase will be nothing but, if I put here 1 by rc, the phase will be simply tan inverse 1, that is plus 45. So phase will be plus 45, okay. So this phase will be plus 45. So I will be lying somewhere around here, where the magnitude will be, this magnitude will be, distance will be 1 by v by root 2, okay. That is the distance, v by root 2, okay. For now I don't care about the distance. This is the point is v by root 2 r angle 45 degrees, or I can say this is the point of omega equals to 1 by rc. Now at omega equals to infinity, what is happening? If I put omega equals to infinity, simply what will happen, this term will dominate, like 1 I can neglect because omega is very high. So what will happen, this will I can neglect, this will be simply under root r square omega square c square, which is r omega c. So omega will be cancelled, and c will be cancelled. So this will be v by r. And what will be the angle? If I put omega equals to infinity, this will be tan inverse 0. Tan inverse 0 is 0. So simply the distance from the origin will be v by r, and this point will be, angle will be 0. So this point will be omega equals to infinity. Again, as it is a first order circuit, like it is first order. How is it first order? Because if you solve this, right, like although I have not mentioned, what happens is, we this actually is replaced by 1 by s actually, like in Laplace domain this is replaced by 1 by s c, okay, because j omega is 1 by s c. Then what we say is, if I solve this circuit, right, in Laplace domain, in frequency domain, this will be basically your I current, right, will be this will be v of s, right, whatever is the s domain transfer function upon r plus 1 by sc, or this will be I can multiply sc on both sides, this will be v of s into sc divided by src plus 1, okay, src plus 1. So here the order or the power of s is 1, right, so that's why it is a first order circuit, as the coefficient of s is 1, so that's why it is a first order circuit. I hope it is clear. So it will be src plus 1, okay, and for a first order circuit the Locus diagram will always be a semicircle. Now the purpose of plotting this one, right, had to see whether the semicircle will be in the negative angle or in the positive angle, and we saw that at 1 by rc the angle is positive, so the Locus diagram will be covering the first quadrant in the semicircle. That was the purpose of doing this analysis 1 by rc, okay. What will be the diameter of the semicircle? V by r. What will be the radius of the semicircle? V by 2r. Now it depends whether this phasor is peak or RMS, then this will be Vm by r, or if it is RMS this will be Vm by root 2r. It all depends how you assume your phasor quantity to be, whether it is peak or RMS, okay. Now what you can do, like without doing all this, right, approximately you can do some approximations that your current, right, when omega is very low, when omega is 0, approximately what will be the value of current if omega is very low? If omega is very low, that is omega equal to 0, this will provide infinite impedance. So approximately the current will be 0. Approximately the current will be 0, right? As this is providing infinite impedance, I can actually neglect this value r. I can neglect this value. Only capacitor is present, and in capacitor, what happens? The current always leads the voltage. This is my voltage. So current will lead. That's why the current angle was coming plus 90, because it is a series circuit. So voltage is reference. So current will lead the voltage. For very high value of omega, what is happening? If omega is very high, right, this will provide 0 impedance, approximately short circuit. So approximately only resistance will be present. So this will be I will be equals to Vm sin omega t by r, okay, because like this will behave almost like a short circuit, only resistance will be present here. So this will be Vm sin omega t by r, okay. I will be Vm sin omega t by r. So approximately it will be like Vm by r. So that's why this is V by r at infinity. It is along the real axis because current will not have any imaginary component, okay. That's also how you can plot this current, and you know that it is a capacitive circuit. So in a capacitive circuit, the current will always lead the voltage. So angle will always be positive, it cannot be negative. Angle will always be positive, it cannot be negative. So it has to be in the first quadrant, okay. That's how intuitively you can solve this without doing all this analysis, right? Intuitively that is how you can solve, because it is a leading circuit. Let's now solve this one, okay. Here we have our resistor, like now what we are doing, we are varying our resistance. Now let's first try intuitively, and then I will solve using the equations. So intuitively, when r is 0, like I am varying my r to 0 to infinity. So when r is 0, the circuit will behave as purely capacitive, and when the circuit behaves as purely capacitive, omega is some constant value, then what will happen? What will be the current value? Current value will be current value will be simply V upon reactance, that is 1 by j omega c, purely leading. So it will be j omega c into V, right? So current will not be 0, it will be some constant value, because omega this time is not 0, omega is some constant, omega is not varying. You can only vary one parameter at a time, you cannot vary two parameters together. So previously I was varying omega, so other things were fixed. Now I am varying r, so omega and other things will be fixed. So this is some fixed value, so and this is plus j omega c. Plus j omega c means, plus j means it will be plus 90, so I will be lying somewhere around here. Okay, and when my r is very high, again when my r is very high, r will dominate. I can neglect the capacitance, right? I can neglect the capacitance because r will dominate. In series, higher value dominates. So the current will be V by R. And if R is very high, this will be approximately 0. Angle will also be 0 because it will behave as a purely real circuit. So I will be lying somewhere around here. And again I have told you that the current, right? Current angle, angle of current, because I am plotting the current actually, it cannot be like, it has to be plus 90 because current will always lead the voltage, because nothing is mentioned. So we will assume the voltage to be my reference. So it has to be a positive angle. So there is only one way of the locus diagram. This is the way. Okay, I have forgotten to mark the arrows actually. So always your arrows will start from omega equal to 0 to omega equals to infinity. Here also omega equal to 0 to omega equal to infinity. I forgot to mark down the arrows. So this is the graph intuitively. This is the point at r equals to infinity. This is the point at r equals to 0. And what is the diameter? Diameter is this one, right? C omega V. C omega into V. This is the diameter basically. Okay. That's how simple it is. The radius of the circle, semicircle, is C omega by 2. Now if this V, they have told you, they are assuming Vm, peak value, you write Vm. If they are assuming RMS value, you write RMS. So it depends what they assume. Okay, I'm just writing here V can be Vm, V can be RMS. Okay, it depends on the question. Now let's solve it actually without intuition. So I know my current, right, is this value, right? Current and yeah, angle of current is this. This time the advantage is my xc is fixed. What is xc? Xc is 1 by omega c, and I know omega is not varying this time, so xc is fixed, only r is varying. Now it becomes simpler. So if r is 0, this will be v upon xc. Xc is 1 by omega c, so this will be v into omega c. So that is what we have written over here, right? But with the j sign, because if I put here r equal to 0, this will be tan inverse of infinity, and tan inverse of infinity is plus 90. That's why j. What about r equals to infinity? At r equals to infinity, this will be very high value, right? So some constant upon very high is approximately 0, and at r equals to infinity, this will be tan inverse of 0, angle is 0. That's why I'm lying here. And you can choose another point, r equals to 1 by omega c, right? 1 by omega c, you can choose r equals to 1 by omega c. At that point, you will see the angle will come out to be something positive, that is plus 45. Okay, so these are the 3 points. This is the homework for you. R equals to 0, r equals to 1 by omega c, r equals to infinity. You will get back the values. The magnitude of I will be here, will be omega c into v. This infinity will be r equals to infinity will be r equals to infinity will be 0, magnitude of current will be 0, and r equals to 1 by omega c, this will be v upon under root 2, right? Sorry. And like you can solve this, c omega v upon under root 2. This will be 90, this will be 45, this will be 0 degrees. Okay, so these are the this is the way which you can plot the locus diagram. Now the homework for is to plot the admittance, locus of admittance as a function of omega, overall admittance seen from this point, right? Overall admittance seen from this point as a function of omega and as a function of r. Okay, with that you will be done with locus diagram. Let me drink a bit of water. If I have bit of water, no, I don't have a bit of water. Okay. Let's solve few questions. This is the first one that actually came in GATE 2022 EC paper, and yeah, we have only a single question, so we'll solve only this question. So here we have to plot the locus of the impedance with increasing in omega. That is already plotted actually. The values of R1, R2 are. So they are asking me the values of R1 and R2. So I observe at omega equal to 0, the impedance, like I'm plotting the impedance, right, is purely real, that is 5. So at omega equal to 0, this will behave as what? Open circuit, right? Because what is the reactance? Reactance is 1 by xc, 1 by omega c. Omega 0 means infinity. So this will behave as open circuit. So the circuit will be replaced with this R2, R1, okay. So your Z, right, j omega will be R1 plus R2, okay. That is equals to R1 is what? So R1 plus R2, right, at omega equal to 0 is equals to 5 kilo ohm actually, that is given to me. So it is equals to 5 kilo ohm. Now at infinity, when omega is infinity, this will behave as short circuit. Capacitor will behave as short circuit. Just give me 1 second. Okay. So I don't care what is this R2 value. It is short circuit, so in parallel lower impedance will dominate. So roughly this will be R1. So R1 actually is given to me, the equivalent impedance, right? R1 impedance is given to me actually as 2. So R1 I got the value as 2 kilo ohms. So R1 is 2 kilo ohms and your R2 will be, so R1 plus R2 is 5. So R1 is 2. So R2 will be 3 kilo ohms. Okay. So do we require any knowledge of locus? No, but still it is a topic, so I have to teach it. So that's my task. Okay, that's my job. So we have to do it, right? So R2 will be 3 kilo ohms, R1 will be 2 kilo ohms. So R1 is 2, R2 is 3 kilo ohms. Option A will be the correct answer for this particular question. Now we will start with complex power. Let's start with complex power. So first of all, discuss what is power. What is power? Power is nothing but the product of voltage and the current, right? Power is nothing but the product of voltage and current. Now there are multiple definitions of power. First one is the simple one, instantaneous power, the power at any point of time. From this we will derive the other kinds of power known as average power or active power. Then we have another name known as reactive power, that is a different thing. We have apparent power. So we will understand each and all of them one by one. In DC circuit, because the voltage and current both were actually constant values, right? Or if they would have changed, like they would have changed in a simple manner, then the power definition was very simple. Power definition was very simple. It is voltage into current. But here, as the voltage and currents both are changing, and in case of voltage and current, there is a phase shift, right? Let's assume that the current lags the voltage by phi. Current lags the voltage by phi, right? Then what will be the power? What will be the expression for instantaneous power? So if voltage, let's assume that voltage is Vm sin omega t theta v, okay, and the current is Im sin omega t theta I, and theta I is with respect to reference. In this case, what is theta I? Minus phi. In our case, what is theta I? Minus phi. Why minus phi? Because current is lagging, right? The zero crossing point is coming after 0. right? So it is lagging. So phi is a positive number, so it will be minus phi. And voltage, what is theta v? Theta v is 0 because we are exactly starting from 0 itself. Omega t equal to 0 itself. So theta v is 0 and theta I is minus of phi. Okay. So now Pt is Vm Im sin omega t plus theta v, and this is sin omega t plus theta I. Okay. Now what we can do is we can do we can see instantaneously what is happening. So omega t between 0 to phi, my current is actually negative, right? 0 to phi, voltage is positive. So positive times negative will be overall negative, power will be negative. So from 0 to phi, power is actually negative, right? And then again from phi to pi, right? The voltage is still positive, but the current is also positive now. Till pi, right? Till pi, this is the pi point, current is still positive. So both are positive, so power will also be positive. Now what does negative power mean? Do you understand what does negative power mean? So if I assume load, right, or source, for a source, what does negative power means? Negative power means nothing but it is absorbing the power, right? This you have studied in DC part of network. Negative power means we are absorbing the power, and positive power means we are delivering the power in case of a source. In case of a source, because we are assuming this is a voltage source and the current across the source, we are measuring the current across the source. So from phi to pi, the power is positive. From pi to pi plus phi, from pi to pi plus phi, what is the sign of the power? So pi to phi plus phi, right? The power is again negative because the current is still positive in this region, right? Pi to phi plus pi, because it is lagging, but the voltage is negative in this region. So that's why the power is negative. And again, after pi plus phi, both the currents and the voltage both are negative. So overall the power becomes positive. Okay. So instantaneous power can be positive or negative depending on the phase difference and the time in certain time periods. Okay. It can become negative in complex networks due to presence of inductance and capacitance, because inductance and capacitance have the ability to store some energy and then again deliver the energy. That's why for a purely resistive circuit, the instantaneous power is positive. Why? Because there will not be any phase difference. If there is no phase difference, like simply it will be just another sine wave, right? So always the product will be always positive. You will see the power product will be always positive no matter what. Okay. Inductor stores energy in the form of magnetic flux. Capacitor stores energy in the form of charge or electric flux. Okay. Now I want to discuss a few things about definition of average value. So what do I mean by average? Average mathematically for discrete number of samples is basically, if I have, let's say, x of n 135, what will be the average? Average will be 1 plus 3 plus 5, that is 9, upon the number of samples, that is 3. So average is 3. This is the definition for discrete samples. For a continuous sample, right, average will be for a signal which is periodic in nature, the average will be integration of the signal throughout its time period and dividing by the time period. That will be the mean or average. For a sine wave, the average value is simply 0. You will see that whatever the positive area I have, same negative area, so average value will be simply 0. Okay. Now, yeah, what about the average power? So what will be the average power? Average power will be nothing but the integration of the instantaneous power, and your power also will be periodic in nature. It will be integration of the instantaneous power over a time period divided by the time period of the power or of the signal, of the input signal. Okay, of the input signal. So like here I have derived the value of instantaneous power. In my full course, I have written all these things down. I have derived slowly, but this is like a rank improvement badge, right? So I cannot just write down these values then solve in front of you. That will take us so much of time. So we are directly skipping into the final result. So our final result of power will come out to be this. Okay, if you multiply the voltage signal and the current signal, you use this formula, the final result will come out to be this, which is Vm Im by 2 cos theta v minus theta I minus Vm Im by 2 cos 2 omega t plus theta I plus theta v. Okay. It will have two components. One will be the constant component. Here it will not have any time domain component because I had a minus b, and in both a and b omega t was present, so omega t automatically got cancelled here, constant term, and in the second term it is a time varying term. So if I integrate this, right, and take the average, the integration of cos omega t, I don't care what is the theta and all those things, the integration of over a period of cos will always be 0. So as it is time varying with 2 omega, so this will be 0. The integration of this, right, this time varying portion will be 0. Only the constant part, part is the interesting thing over here, right? So constant part will always be there. This will vary. Actually what is happening, for certain period the inductor or capacitor is delivering power to the source, and for this period the source is delivering power to the inductor or capacitor. So in this region the inductor is storing the energy, in this region the inductor is delivering the energy. Okay, so if I take the average, only this one will be left out, this one will be gone, right? It is a time varying term, this will be 0. Okay, so this will be gone, basically this average portion will be gone, only this constant term will be there, that is Vm Im by 2 cos theta b minus theta I. Okay, this cos theta b minus theta I is actually known as a very important term as power factor. Okay, and we know what is RMS, Vrms is Vm by root 2, right? Vm Im by 2, so Vrms is Vm by root 2. What is IRMS? Im by root 2. So this product is same as Vm Im by 2. So this can be directly replaced with Vrms, this can be directly replaced with IRMS, and here in this chapter only I will explain what is the physical meaning of RMS, what is the actual meaning of RMS. Okay, so this will be Vrms, this will be IRMS into cos of phi. Okay, into cos of phi, and remember your phi will be lying between minus 90 to 90 for passive networks, passive networks. Okay, so this is the formula for average power. Now your power is actually always changing, it is not constant. We had just derived the average power. Okay, we had just derived the average power, but actually your power is always changing, right? It is not constant, but we are interested in the average power because this power, right, is nothing but utilized for storing energy in the inductor and then again delivering it back to the source. So actually we are not getting any real power. The real power is only due to the average power. So that's why this power is also sometimes called as the real power, that is actually getting delivered to the load. This remaining power, sometimes it is getting delivered to the load, sometimes the load is delivering the power. So net this power is 0. So only this term is of interest to us, that is the average power. Okay, now let's actually understand the physical significance of RMS value. What is the physical significance of RMS? Let's say I have a constant DC source, okay, whose voltage is Vm. What is the power dissipated? It is Vm square by R. Now similarly, if I have a AC source, whose voltage is Vm sin omega t, what is the average power dissipated, right? Average power dissipated will be V square t by R, like this is the instantaneous power. Average I will integrate this over 2 pi because the time period is 2 pi. Okay, divided by 2 pi. Okay, and if I do this, right, the average will come out to be Vm square by 2R. You can calculate the average, like average P2 power will come out to Vm square by 2R. Now the actual meaning of RMS is, if I want to replace this voltage, sinusoidal voltage source with a equivalent DC source whose voltage will be Vrms, I want the value of Vrms such that the power does not change across the load. Load still receives the same amount of power as it was receiving previously with respect to the sinusoidal input voltage source. What was it? Vm square by 2R. So what is the power dissipated here? As I have discussed here, right? If I have voltage source, it will be V square by R for a DC voltage source. So it will be Vrms square by R. VRMS square by R. Okay. So yeah. So what will be the value of this VRMS? The power should remain same. So I will equate this. So from here I get my VRMS, right, to be equals to Vm by root 2. Okay. You can equate these two, you will get Vm by root 2. So that is the actual meaning. So if you have finally understood the actual meaning of RMS, you'll put it in the comments. Sir, I have understood the actual meaning of RMS, root mean square. What does root mean square mean actually, physically, right? So by what amplitude RMS I will replace the AC source so that the power remains same in the previous circuit. Okay, with replace the AC source with a DC source. Okay. Now also if I have an AC source, I replace it with a DC source with magnitude equals to the RMS voltage source, that will keep the power as same. Like these two are the same, saying the same things. Basically it is talking about the RMS value. So this is the actual meaning of RMS. Okay. So RMS, how do I calculate the RMS mathematically? Like that was the just the physical significance. How do I calculate the RMS mathematically? So mathematically the RMS of any periodic signal will be simply root mean square. The full form of RMS is root mean square value. Okay. So first you have to square, then you have to take the mean of the square, then you have to take the under root, and that will yield you the RMS value. That will yield you the RMS value. Okay. So first I will square. So if I have a signal here, let's say x of t, I will square the signal, then I will take the mean. Mean means average. So I will divide it by its time period. I will integrate it from 0 to t, and then finally I will take the under root, that is root, right? So that's how we calculate the RMS. For a sinusoidal, RMS value is Vm by root 2, peak by root 2. Okay. For different signals, don't worry, I will calculate the RMS value for different signals. From there also we will understand this thing. Okay. Now I want to explain one more thing, property of orthogonal signals. What do I mean by orthogonal signals? Okay. So let me zoom in a bit. Give me 1 second. So what do I mean by orthogonal signals, right? So orthogonal signals are those kind of signals whose inner product is 0. Now you will say, sir, I don't understand, what do you mean by inner product? So they follow this property. The area integration or the area of the product of these two with one conjugated will be 0. Okay. But that is the actual definition of orthogonal signal that Himanshu sir will teach you in signals. But for network theory, you don't have to worry, because we know in network theory we only are concerned with real signals. Our input source will always be real, right? If it is a real signal, then we know for a real quantity the conjugate is same as the actual value, right? Because it does not have any imaginary component, it only has real component. Okay, x only has real component, it does not have any imaginary component. Okay, so that is what my x conjugate of t is, that is equals to x of t, right? Now yeah, so we will write this x2 conjugate will become x of t. So basically in network theory the property will be x1 of t into x2 of t dt over its whole time period will be equals to 0. If the two signals follow this property, then the two signals are said to be orthogonal. Basically, in other words, the product of the two signals, area under the product of the two signals will be 0. What is the simplest example? Simplest example is sin omega t and cos omega t. So this is my sin omega t. What is my cos omega t? So the cos omega t will be like this. right? So if I multiply sine with cos for the first pi by 2, both of them will be positive. Then in the next, after pi by 2 onwards, cos is going to negative, right? But this is positive, so this will be negative. So what will happen? The roughly, approximately, the graph will be, now this is starting from 0, right? This is increasing from 0. So we will also start from 0 actually. Obviously you can solve. Sine is sine A, sin omega t into cos omega t. It is nothing but half sine 2 omega t, right? Sine A cos b is property of sine 2 sine A cos b, right? But I'm just solving it intuitively here. Okay, the frequency will be doubled. Here what will happen? This will be very low value because sine is starting from low value. It will reach some peak value. Okay, and then again it will go to 0 because cos is going towards 0, right? At what time? Pi by 2. This will be at pi by 2, and then again after pi by 2 cos is negative, sine is still positive. So overall it will be negative, and then again it will go to 0 because at pi sine will go to 0, right? And now after pi both sine and cos both are negative, so negative times negative will be positive again. And then after 3 pi by 2 what will happen? After 3 pi by 2 your cos will be positive. This is the point of 3 pi by 2, right? I'm doing it in a hurry. So cos will be positive, but sine is still negative, right? After 3 pi by 2. So overall this will be again negative. So in a complete period 0 to 2 pi, I am actually following 2 cycles. So the frequency has been increased by 2. That's why you see this term 2 omega t, right? Mathematically I have shown you. Intuitively this is how you can understand. Now what is the area? 0. Area in a period is 0, right? So cos omega t and sin omega t are actually orthogonal signals. And why am I stressing over this? Actually we will use this property. We will use the property of orthogonality. This will be of huge help to us. Also one more thing, any sinusoids with different frequency are always orthogonal. This is the property. They will always be orthogonal no matter what. Why? Let's say I have sin omega t and cos 3 omega t, right? I am multiplying these two signals, right? Again it is 2 cos sin b, 2 cos sin b, and you can solve 2 cos sin b. One term will be like 1 sin a plus b, sin a minus b, right? So sin a plus b will be 4 omega t, sin a minus b will be 2 omega t. So again if I integrate, still the omega t is there. So the average value of both those signals, right? If I break this down in the trigonometric format, will be still 0. So again these two signals will be orthogonal, okay, simply. So any sinusoids whose frequencies are different, whose frequencies are not same, they will always be orthogonal. The sinusoids with same frequency, if their phase shift is 90 degrees, then also they will be orthogonal. If their phase shift is odd multiple of 90, if their phase shift is odd multiple of 90, like cos and sin, what is the phase shift? 90. This signal also will be orthogonal, sin of omega t and sin of omega t plus 270. You can verify. This also will be orthogonal. Sin of omega t, what do you call? Sin of omega t minus 270 and sin omega t, that also will be orthogonal. So if the signals are different, I don't care what is the phase shift, they will always be orthogonal. If the frequencies are same, I will be aware. I will be bit stressed. I will check the phase shift between those two signals. If it is 90 or odd multiples of 90, like 3 times 90, 5 times 90, okay, 7 times 90, not even multiple, then also the signal will be orthogonal, and we will use the property of orthogonality to calculate RMS value. Okay, make sure to understand this point. So in network theory, our signals will always be real, so conjugate will be same as the actual signal x of t. So for any like aperiodic signal, if it is aperiodic, the orthogonality condition is defined over the whole time period from minus infinity to infinity. For periodic, that this is what we are mainly concerned about. For periodic signals, the orthogonality condition will be evaluated over a complete time period. So if I integrate over a complete time period from 0 to t, the integration will be from x1 to x2, it will be 0. From 0 to t, the integration of x1 into x2 will be equals to 0. Okay. If a signal xt can be expressed as the sum of multiple orthogonal components, right? x1 plus x2, x1 of t plus x2 of t plus x3 of 3, right? So they are mutually like, if I assume okay, if a signal xt can be, yeah, now we will use this property actually. If let's say my signal, right, is sin omega t plus cos omega t. Now these are orthogonal, so I can directly say what is the RMS value of the signal. That is the property that we will use. Like there is a proof, I have proven it to you. You can go through the proof. Like we don't have time here, so I will not be able to show you the proof, but you can do the proof. Okay, so RMS of x, right? What will be x RMS? It will be basically individual, like RMS of this whole square. What is the RMS of sin omega t? Peak value is 1, RMS will be 1 by root 2. I will square the RMS, then I will add with the RMS squared of this one. So what is the RMS of cos omega t? 1 by root 2. I will square it. I will add these two quantities and overall I will take the under root. Let's say I had a third quantity, cos of 3 omega t. So, or 2 cos of 3 omega t. Then what I will do? I will write down the RMS of this value. That is, what is RMS? Peak is 2. RMS will be 2 upon root 2, right? Peak upon root 2 whole square. And I will add, and then I will take the whole square root. So that is the convenience. I can easily calculate the RMS value if I know the overall RMS value of the signal, if I know the individual RMS values, if I know that these three signals are orthogonal. This property can only be applied if the three signals are orthogonal, and we will use this property everywhere. Okay, so this will be under root. So here in this case, what will be the answer? 1 by 2 plus 1 by 2, that is 1, plus 2, that is 3. So under root 3. So the overall RMS value will be 3. If you go by the definition of RMS, if you solve it using the lengthy method, you will get the same value. Okay, that is the advantage of orthogonality. So you can check here, I have proven it here, but I will not obviously solve it because we don't have time. So now let's find out the average and RMS value for few waveforms. Okay, so try to derive the average value of a square waveform. Okay, and try to derive the RMS value of the square waveform. Don't see the solution. I know you will see the solution, but try it by yourself, because trust me, in case examination something like this will come. And try to find out the average value of a triangular waveform, and try to find out the average value of a RMS value of a triangular waveform. This is the, like, pause the video and try it out now. So let us see for the average value of a square waveform. So square waveform, let's say is like, this is known as the duty cycle, T1 upon T, right? Is known as the duty cycle. The period for which the square waveform is high and the period for which it is low is known as T off, or it is capital T minus T on, which is the off period basically. Okay, capital T is the time period of the waveform, right? So what will be the average? Average is the overall integration from 0 to T. In our case, this area is 0, only this area is there, that is capital A into T1, right? That's why I have written here capital A into T1 divided by the time period. Time period is T, so this is capital A into T1 divided by time period. Okay, and this T1 upon T is actually known as duty cycle, that actually is used in power electronics. Okay, so that was the average. So average value will never be a problem for you. Average value will be always very easy for you to calculate. Average value will always be very easy for you to calculate. Okay, what about the RMS? So RMS will be not that simple. So for RMS, you had to square your waveform first, square, mean, and then root, right? So first of all, I have to square. So if I square this waveform, what will be the square value? Squared waveform. So the squared waveform would be somewhat like this, right? This will be a square when it is not 0, then it will be 0, right? Because 0 squared is 0 for T on. From T on to T, it will be always 0, right? Okay. From from T on to T, it will always be 0. Okay, right? And then again it will be a square, and then again it will be 0. Okay, right? So yeah, now what I can say is, what will be the average of this waveform? Because first I will square the waveform, then I calculate the average. So what is the average? Average will be a square into t on upon t. Right? Similarly, like you can calculate the average, a square to t on upon t. Now ultimately I have to take the under root of this. That will be the RMS value. So this will be a into t on divided by t under root, right? So that is what we have calculated over here. Mathematically, how can I calculate? Mathematically, I will integrate, because from 0 to t on, the waveform will be like, the waveform is a, from t on to t, the waveform is 0. So anyways, the integration of 0 will be 0. So only this much amount of part will be left out. So mathematically also you can solve. I'm not solving it mathematically, I'm just solving it using area. Okay. What about the triangular waveform? So in the triangular waveform, I actually had made a mess up in the full course. So what is the average value? Average value is very simple. Again, area upon the time period, right? So what is the area? Area is half into base into height. So what is the base? Base is capital T and height is A, right? Half into capital T into A, right? Then divided by the overall time period, right? That comes out to be A by 2. In this case, it comes out to be A by 2. Okay, it is always A by 2. No matter what, it will always be A by 2. Okay, luckily, so it will just be exactly at the half. Okay. Now, what about the RMS value? Now, RMS value is interesting. So, RMS value for a symmetrical triangular waveform, you can calculate mathematically. If you calculate, it will come out to be A by root 3. If you remember it, it will be good. Otherwise, you have to mathematically calculate. That will take you time. For a symmetrical triangular waveform, the RMS value will be A. A is the peak value upon the root 3. Okay. For a square waveform, for a symmetrical square waveform, if the t on period is half, for 50% of the time the waveform is high, for 50% of the time the waveform is low. For a symmetrical square waveform, the RMS value will be A upon root 2. This value will be lower compared to the square waveform. So this is in the lower side compared to the square waveform. So if you remember these neat tricks, this will be this will be massively helpful in the actual examination. Okay. So yeah, these are the things. Now let's understand more about complex power. Okay. So I have already discussed that my power equation is this: Vm Im by 2 cos theta v minus theta I. So this, right, cos theta v minus theta I is the real power that is actually getting dissipated in the circuit. Okay. Which is written as Vi cos phi, where V is the RMS value of the voltage, I is the RMS value of the current, cos phi is the power factor. Don't worry, I will tell you the definition of power factor just in the next few slides. Okay. Now remember, this average value of the power, this expression is only valid, actually this expression will always be valid. Actually this Vi cos phi will always be valid, but this expression is only valid for single frequency. So because we have only discussed what the voltage is also frequency of omega, current is also frequency of omega. We had not discussed multi-tone signals. Okay. So this is valid for single tone signal. Like this equation, this is always valid. How this is always valid, I'll explain, don't worry. But this equation is only valid for single tone signal, because I will have only because theta v is what? Theta v is the angle of the voltage of the omega quantity, right? Omega t, where voltage is varying with omega t. If let's say my voltage also has 2 omega t, now what is the angle? Let's say my voltage is a combination of 2 sine omega t plus 30 plus 3 sine 2 omega t plus 60. Okay. Now these frequencies are different. So what is theta v? Can you say theta v? No. Theta v is always with respect to a single frequency quantity. So this formula, right, theta v minus theta I, it is defined for a single frequency signal, as I have mentioned over here. Okay. We will see what will happen to multi-tone signals, don't worry. So I have a definition of power, complex power. What is complex power? Complex power is combination of both the active power and the reactive component of the power. This power, right, which is constantly varying, I wanted to show this power. Where did it go? Here. This power is constantly varying. I wanted a mechanism to actually show that how much of my power is actually constantly varying and how much of it is actually that is getting utilized in the circuit. I wanted a mechanism to show this. To show this, we had to define complex power. So what is complex power? Complex power is a combination of the actual real power and the reactive power. Reactive power shows the variation, how it is the storing capability of the circuit, and the active power tells me how much power, real power, the circuit actually requires. So it is nothing but VRMS. Remember, VRMS is a phasor quantity. Okay, voltage is a phasor quantity. VRMS is Vm by root 2 angle theta V. Okay, reference is sin omega t, and IRM is Im by root 2 angle theta I. So it is VRMS into IRMS conjugate. Now why do I had to do a conjugate over here? Because in the real power formulae it was theta V minus theta I. So I had to take the difference of the angles, and the theta I will come with a negative sign only if I take the conjugate, and then I multiply these two complex numbers, right? Then only it will come with a negative sign. So that's why that was the reason why we had to take the conjugate. Okay, now I hope ultimately it is clear how this formula of apparent power came. This is actually known as apparent power, which is combination of both the real and the reactive power. So if it is clear, comments may let you know what to say. Okay, so VRMS IRMS also can be written as Vm by 2, because VRMS is what? Vm by root 2. IRMS is Im by root 2. So Vm by root 2 into Im by root 2 is Im by 2. Root 2 into root 2 is 2. Okay. So that is what my apparent power is equals to. The magnitude of the apparent power is simply VRMS into IRMS. This will be very, very helpful in defining the power factor. Remember, the magnitude of apparent power is VRMS into IRMS. That is it basically. So VRMS into IRMS, like S, right? If I want to say in complex number, it will be VRMS into IRMS, like magnitude of VRMS into magnitude of IRMS into theta V minus theta I. So if I break it down into rectangular format, this will be VRMS, magnitude of VRMS into magnitude of IRMS into cos of phi plus j sine of phi. Cos of phi plus j sine of phi. Now this term cos phi, VRMS, IRMS, cos phi, or theta V minus theta I, this theta V minus theta I is actually called as phi. This term is called as the real power, right, which we already have derived here. This term is known as the real power, and this term is called as the reactive power. This term is called as a reactive power. Okay, again, all these are defined for a single frequency term. Okay, so S is P plus JQ, where P is the active power or real power, Q is the reactive power. Okay, in polar format we can write it a VRMS IRMS into e raised to power j phi. Okay, these are all phasor quantities as I have shown it over here. So S is the apparent power. Now apparent power is actually called, it is not actually a complex quantity, it is just a number. Apparent power is just number, just a numerical value. Actually it does not have any physical significance. Okay, just give me 1 second. Yeah, it does not have any physical significance. It is just the magnitude of S, magnitude of complex power. Apparent power is magnitude of complex power. That's it. It is just a number, does not have any physical significance. It is just a number. The unit is volt ampere, because it is voltage into ampere current. Kilovolt ampere, kVA, MVA, or GVA, whatever you want to say, right? Now real power is actually the power that is getting utilized in the circuit, like mechanical power, which is apparent power into the cos of phi. Apparent power into cos of phi or cos theta, but apparent power, like this is called as the power factor. I will come to this, don't worry. That is what my real power. The unit of real power is watts. The unit of reactive power, because I cannot simply add these, right? I want to separate this, like this is the amount of power that is actually getting stored, and reactive power is the amount of power that is magnetically getting stored in the inductor and capacitor. Now you might ask, so what is the importance of reactive power? Because it is not that helpful, right? It is storing some energy, then again delivering some energy. What is the need of it? So you see the fan, right? The fan that is like running, or any motor, it requires some magnetic energy to operate, and that magnetic energy can only be delivered with the help of reactive power, because reactive power actually helps in the conversion of the energy. So the electrical energy converts into magnetic energy converts into mechanical. So reactive power is actually very, very important. You cannot just simply neglect the reactive power. Okay, and your sorry, your power factor is theta v cos into theta v minus theta I, which is the ratio of the real power upon the apparent power. So the definition of the power factor is real power or active power upon the apparent power. Definition of power factor is whatever is the total active power consumed in the circuit divided by the apparent power. That is the simplest definition of power factor, and this is I will show you this definition of power factor will only be valid for a like this, right? This, okay, this will be only valid for single frequency component, because I know what is my theta v for a single frequency component. I know theta v, I know theta I. But this, right, power factor equals to P upon magnitude of S, always valid. Always valid. Cos of theta v minus theta I equals to P upon magnitude of S, not always valid. Not always valid, only valid for a single frequency component. I will come to this. I'll come to this in the next few slides. Okay. So till now we have understood 4 kinds of power: instantaneous power, active power, reactive power, apparent power. So you can go and have a read about this. So here also I had tried to explain like what will be the active power component and the reactive power component. Okay. So I'm not telling you, active power component is the in phase component of the power. Okay, and the reactive power will be the 90-degree out of phase component of the power. So there are few derivations. I'm skipping it because it is not important for right now, because you mainly have to solve the questions. But for significance point of view, if you want to see the significance, I have taught this in the full course. You can go and see this. Okay, it is anyways free. Network theory is free, so you can go and have a look at this. I'm not explaining this. Okay, there I had actually derived the expression for reactive power. The expression for reactive power actually comes out to be this. Reactive power actually is the amplitude of the 2 omega term. Reactive power is not a constant value here, right? If you see reactive power, right, it's not a constant value. This reactive, is it constant? Is the reactive power constant here? Oh, why did it go, man? Yeah, the reactive power is not a constant. I had to show the variations, right? Because I had to show the variations, so reactive power will always vary. I just have shown the amplitude of the reactive power. I have just shown the amplitude, like the peak, this amplitude of the reactive power. That's it. So here if you see the reactive power, like I have derived it in my full course. We don't have much time here to explain this. So after derivation, the reactive power, the active power will come out to be this, no problem. Whatever we have derived active power, that will come out to be this. But the reactive power actually comes out to be the amplitude of the 2 omega term. Okay, it is not a like constant value. Here active power actually comes out to be constant. If you derive it, active power will come out to be constant, but reactive power actually is not constant, because that is the basic meaning of reactive power. It is always varying, right? But I wanted to show, I wanted to represent what is the storing capability of the circuit, or what is the maximum variation of power that the circuit can take. So that's why we had to define a term reactive power. So reactive power is nothing but the amplitude of the 2 omega term. Okay, so it is just a physical significance. This will not be asked in GATE. Okay, but for the students who are actually curious, now they know like actually what is the meaning of reactive power. In everywhere else, in every other coaching, you will see they will just simply mug the things up. They will never derive this. In my full course I have derived. Of course it is a rank improvement batch. I cannot derive it, right? It will take us more time. Okay, so no one will say all this. They will directly say what is my reactive power. Only this much slide will be there. This slide will be there. That's it. No one will derive it. I have told you what is the physical significance, because in GATE examination, the professors from IIT, they expect something better actually, but we are not able to teach that concept to you. That's why the ranks are not coming. So, but in PrepFusion, you will always get something different. Okay. So yeah, that was about the reactive power. So remember this reactive power actually, right? I cannot calculate the reactive power for a multi-tone signal if the voltage and current has multiple tones, because I will not have 2 omega t term. Then I cannot write the phasor term here. It will have multiple components, right? I cannot calculate it. So reactive power is only valid for single frequency. Okay, valid for single frequency. It will be Vm Im by 2 sine of theta v minus theta I. Okay, sine of theta v minus theta I. I hope it is clear. Like here also I've said the same thing. If the current has multiple tones, what will be my theta I? I don't know. like theta V minus theta I is the phase difference between the voltage and current. If it's a single component, right, I can directly say what is the phase difference, 30. But what is the phase difference here? Yeah, this has phase difference 30. But what about this one? How can I say what is the phase difference? No, I cannot say the phase shift because the frequencies are different, right? So that is a problem. Okay, active and reactive power mostly are defined for a single frequency. Active power can be calculated for multi-tone signals, but reactive power mostly is defined for a single frequency only. Okay. Now one more term is there known as the power triangle. What is the power triangle? So I have told you, right, your complex power S equals to P plus JQ, right? P and Q are both real numbers. So P will be along the reference in watts, Q plus J plus JQ will be 90-degree upwards, and this will be simply your power triangle, right? Now, if your Q is positive, what does Q positive means? So Q means, Q is what? Q is proportional to sine of, like it is VMIM, that is anyways positive, sine of theta V minus theta I. So Q positive means that my theta V will be greater than theta I. Theta V will be greater than theta I. So if theta V is greater than theta I, what does it mean? If theta V is greater than theta I, that basically means voltage leads the current or current lags the voltage. Current lags the voltage, meaning it is an inductive circuit. So if the reactive power for a load is positive, that means it is a inductive circuit. It is a inductive circuit. If the reactive power is negative, that means your theta I will be greater than theta V. So when does current leads the voltage? Current leads the voltage when the circuit is capacitive. When the circuit is capacitive. So your Q will be negative then. Okay. That is also another significance that I have told over here. Same thing I have told over here, right? So yeah. So you can do the calculations, like how can you calculate the power in different circuits. Okay. So like remember this thing. Let's say if I have simply a R and this reactive component, what is the active power dissipated? This is a reactive component, right? So a reactance can never dissipate active power. Only the resistance will dissipate the active power. So what will be the power? Power will be IRMS whole square into R. I square R. So IRMS whole square into R. That is the active power dissipated. The reactive power in this case, as the current is same, right? The reactive power dissipated will be IRMS whole square into X equivalent. That is the value of reactive power. From here also you can find out the P and Q. Like I have derived it over here. You can go through this once. So we can write like from here also you can see the derivation, how this active power comes, how this reactive power comes. I have derived this. Okay, I am not deriving it because it will again waste our time. So you can pause the video and see how I have derived this, right? So basically what we do is we say that our power, right, is V into I conjugate. Now what is my I keep my I is simply I angle theta I, right? I is simply I angle theta I. What will be I conjugate? I conjugate will be nothing but I angle minus theta I, because magnitude will not change. What about voltage though? Voltage will be I into Z. So I is I angle theta I, Z is R plus Jx. Now this X can be positive or negative depending on whether your circuit is inductive or capacitive. So this simply I have replaced it over here, and if you do some calculation, you will see that your active power, the real component, is coming out magnitude of I square R. That is what I have derived over here, and your reactive component will come out to be magnitude of I square into X. If X is negative, this will be negative. That means circuit will be capacitive. If X is positive, circuit will be inductive. Similarly, you can derive it for a parallel RX circuit. Okay, here you will take the voltage, because voltage is fixed, current is not fixed. Okay, you solve it, you will find out the active and reactive powers. Okay, you can see, you can try, you can derive the expressions for power, active and reactive power in parallel and series circuits. Okay, from this you can simply find out the power. Now let's come to the actual definition of the power factor. So the actual definition of the power factor is nothing but active power upon apparent power. Now what is apparent power? Apparent power is simply a number. It is just a number. What is apparent power? It is simply VRMS into IRMS. Now in VRMS into IRMS, do I have any theta or phase term? No. So do I have to worry whether it is a single tone signal or a multi-tone signal? No. I don't have to worry whether it is a single tone signal or a multi-tone signal. I don't have to worry. Why? Because what is VRMS? Let's say my V, right? V contains sine t plus 30 and my it contains cos t plus 30, right? Or cos t plus 60. Give me 1 second. T plus 60, right? So to calculate RMS, do I have to worry about the phase? No, because I've told you if signals are orthogonal. Okay, here actually, okay. I don't know whether the signals will be orthogonal or not. This will be difficult. Okay, let me take this as sine multitone signal sine of 2t plus 60. This is much simpler. So here the signals will be simply orthogonal because the frequencies are different. So I can simply find out the VRMS and I will put here, right? What about active power? You might have the doubt, sir, how will you calculate the active power? Yes, active power also we can calculate. Okay, even if the frequency components are different, active power also we can calculate. How? Let's say current is also a multitone signal cos of, or let's say sine of t plus 60 plus 4 sine of 2t plus 30. Okay, now you might have a doubt, sir, how will you calculate the active power? What is active power? Active power is the average over a time period of the signal, okay, v of t into I of t. Interestingly, if you multiply these two signals, right, these two will have some phase difference, these two will have some phase difference because they are same frequency signals. If I multiply these two signals, what are these two signals? Orthogonal. The frequency is different, these two signals are orthogonal. So what will be the integration? 0. These two signals are orthogonal, what will be the integration? 0. So simply the active power will be the active power contributed by these two signals, active power contributed by these two signals, that's it. So interestingly, for a multitone signal, I can calculate the active power, I can calculate the apparent power, but I will not be able to calculate the reactive power because reactive power is defined for a single frequency. Got it? Reactive power is defined for a single frequency. So I'm telling this in shortcut because in my full course I have taught this, right? Taught this thing. So, but here I'm just telling you in a quicker manner how can I find out the active power for a multitone signal. What will be the active power here? It will be simply VRMS, like for the this omega equals to 1 component into IRMS. So it will be Vm into Im divided by 2 into the cos of the angle between these two signals, right? What is the cos? Theta v minus theta I, that is 30 minus 60. 30 minus 60 plus the power due to the omega equals to 2 component, right? These powers are cancelled. I have to consider only these two and these two. So this will be again Vm into Im divided by 2 into cos of theta v minus theta I. Okay, theta v is 60, theta I is 30. Okay, so this will be theta v will be 60, theta I will be 30. Okay, so this will be cos minus of 30, cos of 30. So this will be 1 by 2 cos 30, 8, so 8 cos, so whatever the value is. So you can calculate the active power, right? So I got my active power, I know what is the apparent power. I can calculate the VRMS. I've told you, multi-tone signal. I can calculate the IRMS, right? You can multiply those two, that will be my apparent power. I know my active power, so I can tell my power factor. So power factor is valid for any component, right? Multi-tone signal. But this term, right, power factor equals to cos phi, that is theta v minus theta I, is only valid for a single frequency component because I cannot always write theta v minus theta I because here I don't know what is my theta v and what is my theta I because it is a multi-tone signal, right? So I wanted to do some emphasis in this point actually. Okay, I hope now finally it is clear what do I mean by power factor and all those things. So if you are enjoying, please put a comment below. Please put a comment below. So this is the summary. right? For a resistive load, the power factor will be unity because you will not have any reactive power. Power will always be positive, so Q will be 0, P will be positive. So theta V will be equal to theta I. So cos of theta V minus theta I, that is cos of 0 will be 1. That's why power factor is 1. For inductive load, power factor will be lagging. Okay, P will be positive, Q will be positive. Our reference is we have assumed that Q is positive, right? For inductive load. For capacitive, Q will be negative, power factor will be leading, P will be positive. Okay, so now let's solve few questions. Okay, like this is some like theory, you can read this. Let's solve few questions. So this is the first one. Okay, try out these questions by yourself, and I will come back with all the solutions. Okay, we have multi-tone signals as well, don't worry, we have multiple multi-tone signals. So whatever I have discussed, that will be done here actually. So this is the one, this is the one, I think, yeah, that's it. After this we will do resonance. Let's solve this question. This is a question from GATE IN 2021. So a household fan consumes 60 watt and draws a current of 0.3125 ampere in RMS. So the fan active power consumed by the fan is 60 watt, okay, and it draws a current IRMS of 0.3125. Now remember this thing, that a fan will always be a inductive load. Electrical guys will understand that we make a fan with the help of a inductance, right? So that's why fan will always be a inductive load, because there are coils inside the fan where the electrical energy gets converted into magnetic energy, then it gets converted into rotational energy. So fan will always be a inductive load when connected to a 230 volt RMS voltage. So the voltage is 230 volt RMS, okay, that is my VRMS. The reactive power drawn by the fan in VAR. So they are asking me what is the reactive power. How can I calculate the reactive power? So what is my apparent power? Apparent power is P plus JQ, or magnitude of apparent power is what? Magnitude of apparent power is P square plus Q square whole under root, right? Now what is the magnitude of apparent power? Do you remember what is the magnitude of apparent power? It is simply magnitude of apparent power, if you remember, it is VRMS into IRMS, right? That is what my magnitude of apparent power is. P value is known to me, right? So I can get the Q value. So magnitude of apparent power will be VRMS, that is 230 into IRMS, that is 0.3125. Okay, sometimes my tablet does not work. 0.3125, this will be equals to 60 square plus Q square, right? Now one more thing, they should have actually asked you the magnitude of the reactive power, because reactive power here, right, will come with two signs. I will show you. So here if I solve, my reactive power Q square will be equals to, now what is this value, 230 into 0.3125, okay, so 71 whole square minus 60 whole square whole under root. So this will be plus minus, because I'm taking the under root, right? So plus minus 39.57. okay, now which one shall I choose? Actually because it is an inductive reactive power, right? Because fan is an inductive load, so it will be plus, so it will be plus. Now actually, to be honest, they should have actually asked, to stay away from the controversy, they should have asked magnitude of reactive power. But here our answer will be plus 39.57, because we know it is an inductive load, and inductive, in case of inductance, the reactive power is positive. Okay, 39.57. This will be your answer. Let's solve this one. Again, this is a IN question, GATE IN 2022. So here in the circuit shown below, the load is driven by a sinusoidal AC voltage source, and whose like phasor format is given, and the frequency is given. Now I don't know whether this is the RMS or the peak value, but it will not hamper our solution of the question. You will see, given R1 is given, C1 is given, L1 is given, R2 is given, right? C1, L1, everything is given. They are asking me the power factor. So what I can do is, I have a source over here, right? I can calculate the impedance seen from the source, and the angle theta z will be the power factor angle phi, and cos of phi will be my power factor, right? So that is my target. The target is to find the impedance angle, right? So what will be the impedance angle? So this combination are in parallel. So how much reactance are they providing? So R1, what is R1? R1 is given to me. Just give me 1 second. R1 is 20 ohms. R1 is 20 ohms, okay, and your C1 is so it is like 1 by pi millifarad, right? C1 is 1 by pi millifarad, so 1 by pi millifarad, right? 10 raised to the minus 3 into 1 by pi millifarad into, like, now what will be omega into C. 1 by omega C will be my reactance, capacitive reactance. Omega is what? F is given 50 hertz, right? Frequency is 50 hertz, so omega will be 2 pi f, so it will be 100 pi, right? So this will be 1 by 0.1, so this will be 10 ohms, right? And it is minus j because capacitive reactance is negative, so this will be minus j10, okay, minus j10 and minus j10, and here I will have inductance. So what will be the inductive reactance? Again it will be omega, that is 100 pi into L. L is 20 by pi millihenry, so minus 10, 10 raised to the minus 3, so pi will be cancelled, this will go away, so it will be 2 plus j2, right? Then I have R2. R2 is 4 ohms, this will be 4 ohms. So again I can simplify these two components, right? I can actually write a simple impedance here. These two are in parallel, so the parallel combination, this will be 20 into minus j10 divided by 20 minus j10, like just the simple parallel formula, r1 into r z1 into z2 divided by z1 plus z2. So this will be, I can rationalize this value, this will be 20 minus j 200 into 20 plus j10. I'm rationalizing it, this will be 20 square plus 10 square, so 400 plus 100, so 500, okay. $500, so this will be 2000 by 500, right? So 4, so this will be 4, actually 2000 by 500 is 4, and this will be okay, minus j8, minus j8, so this is the 4 minus j8, so this will be basically 4 ohms. 4 is the real part and imaginary part will be equivalent. I can convert this in equivalent, minus j8, okay. Actually this is not series just the equivalent z is 4 minus j8, and here what is the equivalent? This equivalent is 4 plus j2, right? 4, this equivalent impedance is 4 plus j2, okay. So what is the equivalent z seen from the source? It will be z equivalent, right, will be like these real components will be added, 4 plus 4 will be 8, and this will be subtract, right, minus j8 plus j2, so this will be minus j6. So what is the angle? What is theta z? It will be minus of y upon x, so 6 upon 4, I think it is 36.86, yeah, minus 36 because negative, because it is minus j, 36.86 degree. So this is the impedance angle. Now what I need to do is I have to find out the power factor. What will be the power factor? Cos of this, right? The power factor, we just have to calculate the power factor. The power factor will be cos of this. So cos of 36.86, or minus 36.86. This will be, I think this is 0.8, cos of this is 0.8, yeah, 0.8. So 0.8 will be the answer for this particular question. Let's now solve the next one. This is the next question. A series RLC circuit, okay? So I have a R, I have a L, I have a C. Is connected, R, L, C values are given, okay? So this is 10 ohms, this is 50 millihenry, and this is 100 microfarad. Is connected to 200 volts, 50 hertz supply. Okay, consumes power P. The value of L is changed such that this circuit consumes same power P but operates with a lagging power factor. Okay, the new value of L will be, so previously it was consuming some power, right? What is the value of the power? It will be IRMS whole square into R, right? Previously it was some L1, now it is some L2, and still the power is same. Power is same. If power is same, like R will not change according to L. If I change the value of L, right? Power is same, so IRMS has to be same. The current has to be same. So what is IRMS equals to? IRMS equals to voltage upon the R square plus X square. Magnitude of current is voltage upon overall reactance whole square plus the resistance whole square. So this will still remain same. So basically this value will be still same, right? So R and V are not changing, only X is changing. So actually X square previously is same as the new X square. And what is actually X equals to? So previously my X would have been equals to X, like previously, if now they are saying that the circuit is operating at lagging power factor, so previously it might be operating in leading power factor. So XC, like previously, in previous case, my XC will be greater than XL because it is operating in leading power factor. Now it is operating in lagging power factor, so the inductive reactance will be higher than the capacitive reactance. So basically your XL minus XC minus XL whole square will be same as, like this was the old value, sorry, yeah, uh, uh, yeah, this, right? What is X previous? Previously my Xc is greater, so Xc minus XL will be positive number, and here it will be XL minus Xc, this will be positive. But it does not matter because ultimately I am squaring it, right? Ultimately I am just squaring it, okay? I am just squaring it, so it will not change anything. Now if I am changing the value of L, okay, keeping the omega constant. So previously have they told me, okay, omega is also given to me, right? So I can easily calculate what is the power that it consumes previously. What was the power that it consumes previously? What is the value of IRMS? IRMS will be voltage RMS. Remember, if nothing is mentioned here, right, then you assume this is RMS value. If it is not given in sinusoid format, by default you will always assume this as the RMS value. By default you will always assume this as the RMS value, okay, by default. So this will be 200, I will assume the voltage to be reference, upon R square. R is 10, right? R square is 10, that is 100, plus XL minus XC, or whatever square, right? So what is XC? XC is 1 by omega C. Omega is 2 into 50 into pi into, basically it is 100 pi into 10 raised to minus 4, or it is simply 100 divided by pi. So it is, I think, 31.83, something like that, right? 100 , Yeah, 31.83. What about the XL? What will be XL? So XL will be, L is 50 millihenry, right? So 50 into 10 raised to power minus 3 into 2 pi f, that is 100 pi, because f is 50. So this will be 5 pi. So 5 pi is nothing, 5 into pi is nothing but 15.7. So now what they are telling me, actually I don't need to calculate all this, right? They are just telling me that, so what is my XC old minus XL old? This is equals to plus 31.83. This is equals to 16.12, right? Now what needs to happen? The whole square, right? Overall reactance should not change. Now the nature of the reactance will be inductive, because I am increasing the inductance. The value of L is changed. So previously you see XC was larger. XC was larger than XL. So of course the circuit will behave capacitive. Now I am increasing the inductance, so the circuit will operate in lagging power factor. So, but one thing will be constant. Still, what is the new reactance? X new is XL minus XC. This still shall not change. This still shall not change, right? Now XL is higher than XC, but the difference between these two shall not change, because the power shall not change. Power is same, right? The reasons have been explained. So XC is what? XC will not change because I am not touching the capacitor value. Capacitor value is same, so it will be same. Frequency also I am not touching, so it will be 31.83. So XL will be equals to 16.12 plus 31.83. So it comes out to be 48, approximately 48 ohms. And what is XL? XL is 2 pi f, or 100 pi into L, that is equals to 48, or my L value, new L value will be this divided by 100 divided by pi. So it is 0.1526. Okay, and they have told me to round off to 2 decimal places in millihenry, right? So if I multiply by, so I need to put more points actually, 36. So if I multiply by 1000, this will be 152, like this is in henry, right? 152.63, or I can round off 152.64 millihenry. So this will be your answer for the question, 152.64 millihenry. Okay, question was actually not that difficult, but it's important to understand conceptually what is happening. If you just mug up the formula like in every other place where you have done it, I know this, okay, then you will not be able to solve this simple questions, right? Even simple question if you just mug up the formulas. Okay, let's now come back to this point which I was stressing about previously. This came recently in GATE IN 2024. So here I have two signals, two voltage signals, sorry, two like a voltage and a current signal with multi-tone. Like there are multiples of frequency, right? It's not a single tone signal or single frequency signal. It is a multi-tone signal. Okay, they are asking the average power absorbed. What will be the average power absorbed? Remember, if I multiply this term, right, with this and integrate, so I will show you now. So if I like what is the average power? P average is nothing but 1 by T integration of V of t into I of t, right, into d of t. Now the interesting fact is, if you multiply 95 into this 4 cos t, if I integrate this over a cycle, right, the integration of cos is 0 over a cycle. So this will be 0. Same thing, if I multiply these two, the integration of cos is 0 over a cycle. Again this will be 0. If I multiply these two components though, integration will not be 0. This and this, what is the phase difference? Minus 60. The phase difference between this and this is minus 60, right? So what will be the power consumed? The power consumed will be the Vrms into IR. Vrms is what? 200 by root 2. What is IRMS? 4 by root 2 into cos of the angle between the voltage and the current. So theta V is 0 degree in our case. Theta I is minus of 60, right? Now this is the power consumed due to this 120 pi t component. Do I have any other 120 pi t? No. Let's check for this 360 pi t. So this frequency is 360 pi t, 360 pi omega, and this is 240 pi. Again, the frequencies are different, and whenever the frequencies are different, signals are orthogonal, the area of these two will be 0, so I don't have to worry about power. Here also, the frequencies are different, area of these two will be 0, I don't have to worry, only this will be the power consumed. So actually, only these two terms are used in consumption of the power. Okay, so this will be active power, that is, so 200 into 4 divided by root 2 is 2 into cos 60 is half, so this comes out to be 200 watts, and this is your answer of the question. Very simple, very elegant, but you have to understand the power is getting absorbed due to only these two components. All these are not actually, yes, there is some variation of power, instantaneous power is there, reactive power is there, but the active power is only getting consumed due to these two components, that is the average value of power. Otherwise the power is just oscillating for due to the other components. Okay, I hope this point is clear. Again, it's a very simple question in gate ion, exact ditto same similar question. They are asking you the RMS value of this signal I of t. What will be the RMS? I have told you, if signals are orthogonal, then I can simply add the RMS, right? If you remember. So is 4 and cos t orthogonal? Are these two signals orthogonal of each other? Yes. If I multiply these two, right, what will be it? It will be 4 cos t. If I integrate this over a cycle, time period, right, what is the integration of cos t? 4 is just a constant, 0. So yes, a DC signal and any cos signal is orthogonal, because what is the frequency of DC signal? Do you know what is the frequency of DC signal? 0. The frequency of a DC signal is 0, and the frequency of this signal is 1 radian per second. So frequencies are different, they will be orthogonal with each other. Okay. So the root mean square, right, IRMS will be, first of all I will write this in whole under root. Okay, then I will calculate the RMS value of 4. What is the RMS value of 4? What is the RMS value of 4? It is simply 4, because there is no time period. If for any time you take, the signal is always 4, right? So what you will do, how will you find out the RMS value individually? So you will square the value, then you will multiply by the time period, and then again divide by the time period, and then again you will take the under root. So it is nothing but 4. So RMS value is for a constant signal is the same signal, right? 4. So this will be 4. RMS value is 4, but don't forget to square it. It was x1 RMS whole square plus x2 RMS whole square. What is x2 RMS? 30 upon root 2. 30 upon root 2 whole square. What is x3 RMS? 20 upon root 2. You don't worry about this negative sign. Don't worry about this negative sign. Okay, sorry, one more thing. Okay. Now this is not that simple actually. Here, right? These signals are not orthogonal, right? These signals are not orthogonal, and these signals are also not orthogonal. So first of all, you actually have to simplify these signals. Okay, this question is actually not that simple as I was expecting. Are these signals orthogonal? No. Okay, so sorry, these are also orthogonal. Sorry, what am I talking about? This is cos t, this is sin t. So of course, cos and sin are orthogonal. Again, cos 3t and sin 3t. Again, it is simple actually. Like if there is a even multiple of 90, right, then the signals will be orthogonal. I told you, if they are same frequency and they are even multiple of 90, phase shift is even multiple of 90, then the then the signals will be orthogonal. Okay, so here there is even multiple of 90, so these signals also will be orthogonal. Again the question became simpler. So this will be 30 by root 2 whole square, then 20 by root 2 whole square plus 15 by root 2 whole square plus 10 by root 2 whole square. Everything is orthogonal, right? Okay, so this will be 16 plus this will be 450 plus 200 plus 225 by 2, 100 by 2. So 225 by 2 is 112.5 plus this is 50 whole under root. So I will add all these values of 50 plus 200 plus 450 plus 16 whole under root. It approximately comes out to be 28.78. Okay, and they are asking us to round off to one decimal place. Round off to one decimal place. So it will be 28.8 ampere. This will be the answer for this particular question. Okay, simple orthogonal property. So let's solve this one again. Like they are asking this similar question. This was asked in GATE BM actually. So in the below, the Fourier series, don't worry about this Fourier series, just the voltage signal is given. Okay, the capacitor is a short circuit for all AC signals. Capacitor behaves as short circuit for all AC signals. Why? Because they have assumed the capacitance to be of very high value. Okay, so it will behave as short circuit. The power is absorbed by the 1 ohm resistor. What will be the power absorbed by the 1 ohm resistor? That is what they are asking us. Okay, so this is actually a very elegant question. So capacitance has value of infinity. So for it has multi-tone signal, right? We have multi-tone signal. So how can I calculate the power absorbed? So what I can do is I can calculate the IRMS. So what will be the power absorbed? Power absorbed will be IRMS whole square into R. In our case it is 1 ohm, so it will be IRMS whole square. How will I find out the IRMS? For this, right, I have to draw the circuit for different signals. To calculate the IRMS, I can find out the value of I as superposition due to the DC, due to the omega component. Just give me 1 second. Due to the omega naught component, due to the 3 omega naught component, due to the 5 omega naught component. Okay, and then add. I can use superposition. Superposition is valid for different frequencies. So at DC, what will be the current? At DC, what is the what happens to the capacitor at DC? It behaves as open circuit at steady state. So if capacitor behaves as open circuit at steady state, your IDC will be simply 0 because there is no path for the current to flow. It will behave as open circuit, right? So there is no current flowing. So IDC is 0. So that part is shorted. I don't have to worry about this V0, even though they have not given me V0. V0 is actually not required to solve this question. What about the current due to the omega naught component? So they have told me capacitor behaves as short circuit in all AC signals. So for omega naught, it will behave as short circuit. So this whole voltage will be applied across the 1 ohm resistor. So VR is simply this 2 cos omega naught t, and for other components as well, capacitor will behave as short circuit. So VR will be simply the only the AC signal, 5 cos 3 omega naught t plus cos 5 omega naught t. Okay, so I can easily calculate the current. Current will be VR upon R, right? So voltage, the current across the resistor is voltage across it divided by the resistance. So it is nothing. Resistance is 1. So IR is same. IR is also same value. No difference, right? So this is my IR actually, right? So now it's much simpler. Now I can, like, what is the RMS value of this signal? It will be 2 upon root 2 whole square plus 5 upon root 2 whole square plus 1 upon root 2 whole square whole under root. So this will be 2 plus 12.5 plus 0.5. So this is actually under root of 15 actually. But what do I have to find out? I have to find out power. Power is what? Square of the RMS value of the current. So power will be IRMS, that is 15 under root whole square. So it is 15. So you don't have to even use the calculator. So be smart, don't always go and take help of the calculator, right? Without also calculator, I can actually simply solve this without any piece of calculator. Okay, so be smart where you have to use the calculator, and where you can avoid the use of calculator, avoid it. Okay, so this will be 15 words. So that's it, basically that is the answer for this particular question. Okay, let's solve the next one. So I guess uh, this is the after this we have few more questions, 1 2 questions we have, then I think we are done. Okay, so this is the question. So yeah, this question was actually in the phasor part. I had taken it in the this complex part. Okay, so we have to experiment is done to measure the active power drawn by a single phase RL load. Okay, so raised to ohm, voltmeters are connected here, here, and here. Okay, so the voltmeter readings are as follow: voltage of the source, right, is 200 volts, voltage of the ratio is 9 volts, voltage of the load is 199. You will say, sir, KVL is not satisfying. I have told this in the phasor that you cannot sum this algebraically. There is some phase difference here. But one thing is for sure, because it is a series RL circuit, if I assume the voltage across the resistor to be reference, then the voltage across the inductor will lead, because current lags the voltage for inductor, and current is same across the resistor and the inductor. So voltage across the inductor will lead. This I have told you, right? Current lags for inductor, voltage will lead. Okay, so plus JVL will be basically equals to my supply voltage Vs. Now it is correct. Okay, assuming perfect resistor and ideal voltmeters, the load active power measured in the experiment will be. So what is the, basically they are asking me what is the active power consumed. How will I find out the active power? So okay, what is the active power consumed? Active power they are asking me, right? So okay, this is not a sorry, this is wrong actually. This is wrong, right? Why this is wrong? So it is not just a inductive load, it is a RL load here. It is not like here what is happening. I am measuring the voltage across a RL load, right? It is not an inductive load. I am sorry, extremely sorry about that. Here I have a resistive load that is of 2 ohms, correct? 2 ohms, and the voltage across the 2 ohms is given to me, that is 9 volts. So I can actually say what is the current. What will be the current? Current will be voltage upon the resistance, that is 4.5 amperes. Okay, this is the 9 volts. Okay, and it is 4.5 amperes. Okay, okay, so now yeah, now what will be, so I don't know what is the RL value, but what I know is I know the voltage. Voltage is 199 volts, right? Voltage is 199 volts. So, and I know the current, because voltmeter is ideal, so there will be no current through the voltmeter, because voltmeter has infinite impedance, so there will be no current flow through the voltmeter. All of the current will flow through the this RL circuit. What is the current? 4.5 ampere. So what is the voltage drop for this RL? 199 volts, right? So so this voltage, right, VRL is magnitude of VRL is 199. I don't know the phase, and I know what will be this equals to. This will be equals to magnitude of the current into magnitude of the impedance seen. What is the magnitude of the impedance? It is simply a series RL circuit, right? It is a, they mentioned it is a single phase RL load. So this will be simple R and L. What is the impedance provided by this load? It will be R square plus XL whole square, right? So 199 is R square plus XL whole square. I know the magnitude of current, so I can actually find out the what is R square plus XL whole square, right? What have they asked actually? They are asking me the power consumed, right? Okay, so R square plus XL whole square will be equals to will this be of any help to me? Okay, magnitude of I is 4.5, so 199 divided by 4.5, and squaring it actually is 1955.6. Okay, so this much information I know, that is 1955.6. One more thing I know is the voltage of the source, right, is 200 volts. Voltage across this resistor is 9 volts. Okay, so if I redraw this circuit, right, if I properly redraw this circuit, so I know the voltage across this R, let me name this 2 ohms, that is 9 volts. And here I have an unknown R, and here I have an unknown inductance whose voltage I know 199 volts, and the overall voltage is 200 volts. Okay, now how can I solve it? That is what I'm trying to figure out. Okay, so what is the overall impedance seen? Z. Z will be the magnitude of Z will be magnitude of the voltage upon magnitude of the current. So I know the magnitude of voltage, that is 200, that is given to me in the question. Magnitude of current, I have found it out, that is 4.5, right? I have found it out, that is 4.5 ampere. So 200 upon 4.5 ampere. Okay, so 200 upon 4.5 ampere. So it is 44.44. Now this magnitude of Z is nothing but combination of this resistor in series, but that is 2 plus R whole square plus this XL whole square whole under root, right? That is what my impedance is. Here I had only XL whole square, right? So now I can actually, I have two equations now. If I square both sides, I will get, this will be equals to 2 plus R whole square plus XL whole square equals to 1975. 0.3, 1975.3. How can, yeah, this will be slightly more. So this is my equation 1, this is my equation 2. If I subtract my 1 from 2, right, what will I get? XL will be cancelled, only this will be left, that is 2 plus R whole square will be equals to 20, right? So this minus 1955.6 whole under root. So it is, so 2 plus R, right, will be plus minus, because I am taking the under root, plus minus 4.4. Now which one will I choose, minus or plus? So R cannot be negative, right? Here we have assumed like everything is normal, simple R load. So R cannot be negative. Of course I will not take the negative solution, because if I take negative solution, R will come out to be negative, that is not possible. So I will take the positive one. So R is 2.44. Okay, I got the value of R. So I just need to calculate the power consumed, right? What will be the power consumed? Overall power consumed will be only in across the resistors, right? So overall power consumed will be IRMS whole square, that is 4.5 whole square into the overall resistance. What is the overall resistance? Overall resistance is 2 plus R, right? So this will be 2 plus R. That's it. This will simply be 2 plus R. So 2 plus R is 4.44 basically. So 4.5 whole square into 4.44. So 4.5 whole square into 4.44, 89.91. So approximately 90 watts, right? So they have asked us to round off to 1 decimal places, right? So it will be, sorry, what they are asking me, assume the perfect resistors, ideal voltmeters, the load active power. Okay. So they are asking me the load active. Please don't make this mistake. They are not asking you to include this 2 ohm resistor, right? They are just like, this is just a resistor. They are asking me the load active power. What will be the active power consumed by the load? Active power consumed by the load will not be 2 plus R, because the load resistance is R, that is 2.44. So don't make this mistake. 4.5 whole square into 2.44. So 4.5 whole square into 2.44. So 49.41. Okay. May correct here, plus this is whole square. If I take this whole under root, yes, okay. Approximately 20. Let me just quickly verify these values. So just give me 1 second. Load across the R is 199 divided by 4.5. This whole square 190. Yeah, that is correct. This will be 4.5. That is also correct. And this will be 200 by 4.5 whole square. Yeah, this is also correct. So 20. If I subtract these two values, okay, sorry, I messed up one thing. Sorry. There will be minus r square here as well, right? So I'm subtracting 2 from 1. I forgot, like there is, sorry, if I'm subtracting, yeah, 1, right? This minus r square is also there. XL will get cancelled, but r square will still be there, right? Sorry. So if I, okay, sorry about that. So there are many errors from my end. So if I break this down, this will be 4 plus 4r plus r square minus r square equals to 20. Okay, so your simply your r will be 4 ohms. R will come out to be 4 ohms. So this will be actually 4. Okay, so 4.5 whole square into 4. So approximately it comes out to be 81 watts. 81 watts. This will be your answer for the question. 81 watts will be the answer for the question. Okay, let's now solve this one. This question is again pretty interesting. So here we have the circuit shown. The active power supplied by the source will be, what is the active power supplied by this source? That is what we have to calculate. So how can I calculate the active power supplied? So let me first convert this into equivalent Z impedance, right? Let me first find out the equivalent impedance here. So let me simplify. So I can simplify these two circuits, right? So this is 5 minus J5 in parallel with a J5 inductor, right? So it is Z1 Z2 divided by Z1 plus Z2. So this will be 5. This will be equals to J is getting multiplied. So this will be 5 plus J5. Simply 5 is getting cancelled. Yeah, 5 plus J5. So overall this is 5 plus J5, right? 5 plus J5, and these combination, and this is in series, right? So this 10 and 5 will be in series, minus J10 and plus J5. So 15 plus, sorry, not plus, sorry, I think minus, yeah, minus J5. These two are in series, minus J5. That is the overall impedance seen, right? So effectively, I have a voltage source here, which is 100, like I will assume it to be RMS, okay? And I have the impedance, I have this impedance that is 15 minus J5. So what I can do, there are many ways to solve this. Either you can find out the current, right, and your power will be I square IRMS whole square into the this real part, that is the resistance, or you can use the power factor formula. Power factor also can be used, but I will use the current. So power factor is simply find out this impedance angle theta z, and simply find out the magnitude of current, and your power will be magnitude of voltage, that is 100, magnitude of current into power factor angle, that is cos phi. Or what you can do, you can find out the magnitude of current RMS value, that will be 100 upon 15 minus J5 magnitude. So this will be 15 square plus 5 square whole under root into 100. So 6.324 amperes. Okay, now your yeah, that is my current. So what will be the power? Power will be I this whole squared into the resistance, that is 15, right? IRMS whole square into R, that is 15 basically. So this will be equals to 600. 600 watts will be the answer for this particular question. With this we have finished all our questions, right? Very basic question. You have to just find out the Z equivalent, and from there you can easily find out the power. Okay, so with this we have finished complex power. Now we will start with resonance. So let's begin with resonance. As you can see, I have removed my sweater jacket because it is getting warm, because this video is long, right? I am also getting tired right now. So we will start with resonance. So resonance is nothing like as you can see from the diagram, particular frequency, at a particular frequency, the either the voltage or current will be maximum. Okay, that is the resonance phenomena. What is resonance? So we know for a series RLC circuit, I have like the overall impedance is R XL minus XC. The resonance condition is nothing but the condition where my circuit will behave purely as a resistive network. There will not be any inductive or capacitive content, right? Resonance occurs in an electrical circuit when the energy like you can ignore the energy for now. You can assume that the circuit will be purely resistive when the load will be purely resistive, when my load only demands active power, or in other words, although there are reactive elements connected, what will happen, whatever energy the inductance is demanding, the same energy is getting delivered by the capacitor. Source is not supplying that energy. Okay, and when the capacitor requires any energy, the same energy will be delivered by the inductor. The source will not deliver any energy. Source will not deliver any energy. Source will only deliver energy to the resistor. So to the source, the circuit will behave as if it is purely resistive. How it will happen? When these two components cancel each other out, when the overall reactance is 0. So that means my XL minus XC has to be 0. If my XL minus XC has to be 0, that basically means omega L by will be equals to 1 by omega C, or omega will be equals to 1 by under root LC. So this is the special frequency known as omega naught or omega R, called as resonant frequency. At this frequency, the real component of the inductor and the capacitive component will be equal. So at this frequency, I will keep on varying my frequency, and at this special frequency, the reactance will be 0. Circuit will behave purely resistive, and many things will happen here. The current will be maximum. Why the current will be maximum? What is the value of the current? So I think here, where is it? So what is the, okay, I have not explained it over here. Yeah, here. So what is my current? Current is magnitude of V upon Z. I am not varying V. It is Vs upon under root of R square plus omega L minus 1 by omega C whole square. Now, for any other value of omega, when omega is not equal to my resonant frequency, this will be non-zero value. And what is the minimum value that this can take? 0, because it is something squared, right? Minimum value will be 0. So when the denominator is minimum, the function will be maximum. So at resonance, the current is maximum. These are the key points that I want to explain. Okay, so like I've already done this in my full course, so I'm just explaining you the key concepts. So at resonant, current for a series RLC circuit, for a series RLC circuit, at resonant, the current at resonant frequency, at resonance, the current will be maximum. The load will behave purely resistive. These are the conclusions. Okay. One more thing I have concluded there, that we know for a series RLC circuit, the voltage, right, across the inductor and the capacitor are in phase opposition. This we have discussed in Phasor diagram, right? Because voltage across the inductor will be plus J with respect to the reference, and voltage across the capacitor will be minus J. So both of them are in phase opposition. That's why here I have VL minus VC. At resonance, the magnitude of the voltage across the inductor and the capacitor will be same. Although the directions are different, magnitudes will be same. So what happens? Exactly, they cancel each other out. So this is the case 3 of the series RLC circuit, which we discussed in the Phasor diagram, case 3. Okay, so these two will cancel each other out. So ultimately what I will be left out with is simply VL minus VC. VL will be equals to VC. So at resonance condition, the voltage across the inductor and the capacitor will be same. Okay, voltage across the inductor and the capacitor will be same magnitude. They will be in phase opposition, that is correct, but the magnitudes will be same. Okay, this was another conclusion. Now let's come to the let's come to the third conclusion. So what is the third conclusion? Okay. Yeah, this is one of the conclusion. Also, what will be the power factor? As it is purely resistive network, and we know the power factor for a purely resistive network is 1. So it is unity power factor. Okay. So what do you have to do to find out the resonant condition? What you will do? You will find out the equivalent impedance, and you will make the imaginary of that equivalent impedance equal to 0. That's the summary. Your whole chapter is done. That is what we will do in this whole chapter. That is what we will do. we'll find out the impedance and we'll make the imaginary component of the impedance 0. Sometimes it is easier for us to calculate the admittance. For admittance as well, we'll make the imaginary component of admittance to be equals to 0. To identify the resonance condition, we have to make the imaginary component either of the impedance or the admittance to be 0, so that only the real component is present. If only the real component is present, circuit will behave purely as real, purely resistive, right? So my load will only demand active power. That is what we have to do in this whole resonance chapter. Nothing. This is what we have to do. Now, we also want to analyze what is happening before resonance and after resonance, right? So omega is equals to omega naught when this is 0. That we know. When my omega is less than omega naught, which will dominate? When my omega is less than omega naught, which will dominate? If my omega is less than omega naught, right? So omega is less than omega naught. That means omega value is lower. I'm reducing my omega. That means XL will be what? Because L is constant, XL will reduce, because for inductance, for inductive reactance, XL is directly proportional to omega. For capacitive reactance, XL is inversely proportional to omega. So if I reduce my omega, XC will increase. If I reduce my omega, XL will reduce. So that's why before resonance condition for a series RLC circuit, so remember whatever I am deriving here, these are the results of series RLC circuit. This will always be valid no matter what. This will be always valid no matter series RLC, parallel RLC, कुछ भी दो एक मतलब कबारा दे दो, कुछ भी दे दो, this will always be valid. Okay, but this, right, this whatever I am discussing here, this will not always be valid. In a series RLC circuit, if my omega is less than omega naught, circuit will behave as capacitive. If my omega is greater than omega naught, circuit will behave as inductive. Okay, and obviously at omega equals to omega naught, circuit will behave as resistive. Why it will behave as inductive? Because as I increase my omega, the XL will dominate and XC will reduce. So that's why XL will be greater than XC. That's why here the circuit will behave as inductive after omega naught, and before circuit will behave as capacitive. So after omega naught, circuit will have lagging power factor. As you can see, before omega naught, circuit will have leading power factor. These are the different impedances, and if I add these two impedance, like if my omega is very small, right, so this will be very large, XC, so XC will dominate. So that's why leading behavior. If my omega is very high, so XL will be dominating. So at high frequencies it will be almost linear. So it is, if you have seen the diagram in most of the cases and in most other places in other YouTube videos, you will see this is symmetric, but actually this is not symmetric. Okay, this is not symmetric. Actually before omega naught, the behavior is something like a rectangular hyperbola. Okay, after omega naught, the behavior is like a linear. Okay, and at omega naught it will be just the minima, because your impedance will be minimum, current will be maximum. So this is the proper diagram. If you finally understood like what is the actual diagram of resonance, right, drop a like and comment in the video. Okay, so what will be the current? Current will be just the inverse of this, right, because when the impedance will be minimum, current will be maximum, because the voltage is constant. So current will be maximum. Now there are few points which I want to note in current. So current will be peak. Current will reach its maximum value when circuit will behave purely as resistive. The value will be V upon R, because impedance will be R. Now there are 2 points here. When my current will be 3 dB down from the peak value. What do I mean by 3 dB down? So 3 dB is nothing but 1 by root 2 times. Like basically here, if this is V by R, this will be V by root 2 R, right? 1 by root 2. So if I take the log of 1 by root 2 and multiply it by 20, because I want to convert from decimal scale to decade scale, it comes out to be minus 3 dB. That's why it is called as 3 dB down points, because this is also very important point to us, because here what is the power? Power will be, power across the resistor will be what? That is my current, right? Current is V by R. So V square by R square into R, sorry, I square into R, right? So that is V square by R, correct? And what is the power here? Again, the power dissipated across the resistor is I square R. So this will be V square by 2R square into R. Into R. So this will be equals to V square by 2R. So power is half. So we actually want to identify when does my power become half. Okay, from the peak power, maximum power, when does my power across the resistor becomes half. That is actually an important point to us in filters and stuff. Okay, in filters and stuff, this is actually very important point to us. So when does my power become half? Power becomes half when the voltage is 1 by root 2 times the peak, let's say when the current is 1 by root 2 times the maximum value, right? So how do I calculate this value? So these are actually called as omega L, lower 3 dB frequency. Why lower? Because it is before omega naught, and omega H, higher 3 dB frequency. Why higher? Because it is greater than omega naught. So we will calculate this actually. So in this region, right, what is my impedance? So here what was the impedance? Here the impedance was Z was R. Here the impedance will be root 2R. Okay. So basically what I have to do, because the impedance has become increased by root 2, so I have to just calculate the value of frequency where the impedance becomes root 2R. That is what we will do basically here. Okay, and the difference between the higher 3 dB frequency and lower 3 dB frequency actually is called as the bandwidth, because in this range the signal will be passed, right? Before this the signal is attenuated, the amplitude of the signal will be very low. In this frequency range the amplitude of the signal is good enough, that is at least we are receiving half power. So these are sometimes also called as half power points, and this is the bandwidth, the range for which the power is greater than half power. Okay, so this is called as bandwidth. So if you solve this, right, if you find out the identify the condition, I think here I have solved it. Where is it? Yeah. Also your omega naught is 1 by root LC in radian per second. If you have to find out in hertz, it will be 1 by 2 pi under root LC. Remember, don't mess this one up. In hertz, if you have to find out the resonant frequency, it will be 1 by 2 pi under root LC. Okay. So here, right, I'll derive basically when my impedance is under root 2. So what is the impedance whole square? So 2R square will be equals to R square plus omega L minus 1 by omega C whole square, right, at half power points. Okay. So 2R square, R square. So this will be basically R square, right, R square omega L minus 1 by omega C. Okay, omega L minus 1 by omega C whole square. Okay, this I have to equate, right, because like impedance is what, under root 2R, and I am squaring it, so it becomes 2R square. That's why, like, I'm basically squaring it, right, because this is under root. So if I square it, this is the equation. I will solve this equation. Once you solve this equation, right, so few things are there, few formulas you need to remember. Yeah, this actually you have to remember. It's good if you are able to remember. If you, even if you are not able to remember, at least this one you have to remember. I will explain this, don't worry. But remember this point. Also this point, even if you tend to forget it, right, at least remember this, that this condition needs to satisfy at half power points, right? At least remember this. How am I coming to this equation? So you can go and have a watch. How am I deriving this? Okay, I will not explain. So after derivation, your omega H value will come out with this. Omega L lower value will come out with this. How am I eliminating? Because here there will be a plus minus sign. Our omega cannot be negative, right? And this value is somewhat greater than R by 12. So I have to eliminate the negative sign. I have to eliminate the negative sign. I only have to choose the positive sign because frequency cannot be negative. So if frequency is not negative, I am adding two quantities. So of course this will be higher. So this will be my omega H. I am subtracting two quantities. This will be lower. That's why this will be omega L. How do you remember? So what is the bandwidth basically? So bandwidth will be the difference between omega H and omega L. So what is the bandwidth? Bandwidth is R by L. If you see, the difference is R by L. This is my bandwidth basically. Okay. In radian per second. Remember, this is in radian per second, right? In hertz, because they will play, gate examiner will play with you. They will give you the bandwidth in hertz and you will mess up in the examination. This will be R by 2 pi L. In hertz, this will be R by 2 pi L. Please don't mess this one up. Okay. So omega H and omega L is this, right? R by 2 pi L. So now what I can say is, yeah, this is my omega H, this is my omega L. Yeah, bandwidth by 2. So bandwidth, so now, right, bandwidth is R by L. So this R by 2L, right, omega H, R by L is bandwidth. R by L is bandwidth. 1 by under root LC is omega naught. So this is bandwidth by 2 plus bandwidth by 2 whole square plus omega naught whole square. If you want to remember in this format, it will be very useful to you. This result is valid for a series resonance circuit, series RLC circuit. This result is not valid. Actually, this result is valid in a parallel RLC circuit as well. But this value, right, this result is only valid for a series RLC circuit. This is not valid for a parallel RLC circuit, but this result is always valid. This result is always valid for a series RLC circuit and for a parallel RLC circuit. Don't worry, once we will come to the derivation of the parallel RLC circuit, there also this will be same. So omega h will be what? So remember, close your eyes. Omega h is bandwidth by 2 because it is the higher value. So the constant term will be plus bandwidth by 2 plus under root bandwidth by 2 whole square, then plus omega naught whole square, because inside the under root term higher value is there, right, than this higher value. So that's why there will be plus omega naught square. So this is my omega h. What is my omega L? Omega L will be minus bandwidth by 2 because it is the lower 3 dB frequency. Okay, remember with me, plus under root bandwidth by 2 whole square plus omega naught whole square. Okay, that's how you will remember it. Okay, and what is and if I want to write this in hertz, I have to simply divide this by 2 pi. I have to simply divide this by 2 pi. Okay, what is bandwidth? Bandwidth is R by L. Bandwidth is R by L. So my bandwidth actually is a function of only, interesting fact, bandwidth is a function of only inductance and resistance. It is not a function of capacitance. For a series RLC circuit, bandwidth is only a function of inductance and resistance. It is not a function of capacitance. Okay. And what about the product of the two functions, omega h and omega L? This is also another important result. If you multiply these two, right, it is simply a plus b into minus a minus b. So it will be a square minus b square or b square minus a square. Automatically this will get cancelled. Only omega naught whole square will be there. So this is another interesting result. The product of higher 3 dB frequency and lower 3 dB frequency always will be resonant frequency whole square. Remember, the units must match. That's why if I am multiplying two frequencies, on the right hand side also I should have hertz square or radian square, right? That's why this is omega naught square and this is omega h into omega L. Okay, so which is 1 by LC. This is actually called as the geometric mean. So the geometric mean of the higher 3 dB frequency and the lower 3 dB frequency is omega naught whole square. Very interesting like term. Now if let's say my bandwidth is very higher than omega naught, right, what will happen for, okay, first case is if my omega naught is very higher than bandwidth, so bandwidth is very small, so omega h and omega L are very near to each other, right, and omega naught is very high. Basically bandwidth is very small, very close to 0, so it behaves like a notch filter. Why notch? Because the shape is notch, right? If you remember our phones, this, right, used to have a notch camera in front of it, right? So this was a notch. If you remember, they used to call, right now it is gone out of fashion, it is hole punch, it is called hole punch, but initially there used to be a notch, right, notch like shape. So this is, the shape is known as notch, that's why it is called as notch filter. It will pass only very selective frequencies because the bandwidth is very low. You see, if I go just beyond the resonant frequency, the current amplitude is reducing, so I am not able to pass my signal, right? So that's why it is called as a very band pass filter. It passes only particular frequencies, band pass filter. This you will study in analog electronics. So in this case, right, if my omega naught is much greater than bandwidth by 2, so what will happen? Okay, so approximately your omega naught will be much greater than bandwidth by 2, so approximately this you can ignore, this will be approximately omega naught. So your omega h, right, higher 3 dB frequency, this will be like, I can ignore this, will be bandwidth by 2 plus omega naught, and your lower 3 dB frequency will be minus bandwidth by 2 plus omega naught. Okay, approximately, if this condition is satisfied. If my omega naught is much less than bandwidth by 2, again I can neglect this, right, then automatically omega h will come out to be bandwidth, right, omega h will come out to be bandwidth and omega L will be 0. So omega L will be approximately 0, omega H will be bandwidth. So basically it will behave as a low pass filter. It only passes this much of frequencies. After this, the amplitude reduces by a large amount. So it behaves as a low pass filter. Okay. So yeah, that is the summary. You can go through this, right? That is a summary here. And also at half power frequencies, what is the power factor? At half power frequencies, my magnitude of the impedance is root 2R. That basically means that my this value, right, is also R. XL minus XC is R. Overall reactance is R, and the resistance is also R. So tan inverse, like what is the power factor angle? Phi or theta z? It is tan inverse X, that is XL minus XC upon R. So X is R, R is R. So tan inverse 1 is 45. So the power factor angle is either plus 45 or minus 45 depending on whether I am at the higher cutoff frequency or the lower cutoff frequency, or whether it is the higher 3 dB frequency or the lower 3 dB frequency. If it is higher 3 dB frequency, what have I told you? If my omega is greater than omega naught, circuit behaves as inductive. So the power factor angle will be plus 45. As you can see, it is plus 45 if it is higher 3 dB frequency. That's why the power factor is 0.707 lag. Cos 45 is 1 by root 2, 0.707 lag. If my power factor angle is minus 45, sorry, if my frequency is lower 3 dB frequency, that means it is capacitive. So the angle will be minus 45. You can see angle, impedance angle is minus 45. Circuit will behave as capacitive. So it will be 7, the cos power factor will be 0.707 lead. Okay, and at resonance, of course, circuit will behave as unity power factor. Okay, that was the summary of resonant frequency. Okay, impedance at omega naught is R, at omega H and omega L impedance is root 2R. This will be plus 45 omega H, and at omega L this will be minus 45. Okay, so how does the impedance angle varies? So for omega less than omega naught, the impedance angle will be negative. Omega greater than omega naught, impedance angle will be positive because it is inductive. Here it is leading power factor capacitive, and this is the impedance diagram. So these are the summary basically. Okay, now there are few conditions. Let's say you want to find out the voltage across the capacitor. Okay, what is the voltage across the capacitor and inductor at resonance? Because what we know is the voltages cancel each other out. That much we know. The voltages will cancel each other out, right? But still there will be some voltage, right? Although this will cancel each other out, the magnitude of the voltage will not be 0. So what is the magnitude of the voltage? So I can use the simple voltage division rule. VL will be equals to magnitude of V into JXL by R plus JXL minus XC, right? At resonance, XL is equals to XC, right? So this will get cancelled. So your V will be simply, sorry, it will, yeah, VL will be XL by R, right? Why have I complicated this much? So no, okay, okay, VL will be magnitude of V into XL divided by XL is omega naught at resonance divided by R, right? So this omega naught L divided by R is actually called as the quality factor. This term is called as the Q, quality factor. This quality factor is equals to omega naught L by R. This is valid for a series circuit. For a parallel circuit, this will change. For a parallel circuit, the value of the quality factor or the formula for the quality factor will change. Okay, we will see this, don't worry. So at resonance, actually the voltage across the inductance is magnified. It is not simply V, it is not just V, it is omega naught L by R into V. So it is Q times your VL is Q into magnitude of V. Now this Q, right, like either this can be plus J or minus J. For inductor this will be plus J because voltage will inductor voltage will lead the current by 90, and for capacitor this will be minus J. Capacitor voltage will lag the current by 90. Okay, that is what will happen. Okay. So yeah, that is my magnitude of VL max. Okay. Now I want to find out, actually I want to differentiate this. You can actually calculate for what value of omega the voltage across the inductor or capacitor will be maximum. So I had actually calculated. So you will differentiate this function, right? And like, this is not important. This is not important, but still, if someday it might get asked, that then you have to differentiate this function and find out when this will become minimum. So not this, right? Over now you have to differentiate this whole function, because numerator is also a function of omega. So after differentiating, I will get the maximum value of omega L at this frequency. Okay, 1 by under LC this. So at this frequency, the voltage across the inductor will be maximum. Same thing you do for capacitor. At this frequency, the voltage across the capacitor will be maximum. Okay, remember this. Like, don't need to remember, no need to remember. Just see how am I deriving it. That's it. So, what is quality factor? Quality factor, actual definition of quality factor is this. It is the energy stored, maximum energy stored in the capacitor or the inductor divided by the energy dissipated in the resistor per cycle into 2 pi. But no need to remember this. Just remember, quality factor for a series RLC circuit will be omega naught L by R. What is omega naught? Omega naught is 1 by under root LC, right? Omega naught is 1 by under root LC. So this will become, quality factor will become 1 by R under root L by C. So just if you remember this one is also enough. If you remember this also enough, it is better, like easier for you to remember this one, right? It is simply the inductive reactance upon the resistance. It is simply the inductive reactance upon the resistance. Also quality factor is also equals to omega naught by bandwidth. This will be always valid. This formula will always be valid. The quality factor is omega naught by bandwidth. So if my bandwidth is very low compared to omega naught, right? So it only will pass certain band of frequency. So it is called as a high quality filter, because we only pass certain frequencies. We reject all the other frequencies. So that's why it is called as high quality filter. That is also another physical significance of quality factor. Okay, remember this. What is quality factor? Omega naught upon bandwidth, because here, right, omega naught, what is R by L? R by L is nothing but bandwidth. R by L is nothing but bandwidth, right? So that is also another way to remember your quality factor, omega naught upon bandwidth. Okay, remember bandwidth. So what things do you need to remember? You need to remember bandwidth. You need to remember omega each, that is plus bandwidth by 2 plus whole under root bandwidth by 2 whole square plus omega naught whole square. You need to remember omega naught, of course, for a resonance. You need to remember omega L. Remembering omega L is easy. You need to remember Q. Q is what? Q is omega naught upon bandwidth. Lower the bandwidth, higher quality factor, right? Higher the quality factor, because it is a high quality filter. That's how you remember that bandwidth will come in the denominator. That's how you will remember that bandwidth will come in the denominator and omega naught will be in the numerator. Okay. Also, it is equals to omega naught into L by R. Okay. Or it is equals to VL upon VR, because the current is same. Current will get cancelled. So voltage across the inductor divided by the voltage across the resistor, because current will get cancelled, right, is also known as the quality factor. So there are many ways to remember. So in a series RLC circuit, these are the things that you need to remember. Okay, so like there are a few derivations about the quality factor. We don't want to go into that. That is not required. Okay, this is all what you have to remember. So one more thing is there actually about quality factor in terms of zeta. So if you remember bit of control systems, great. If you don't remember, ignore this discussion. So for a, this is a second order circuit, right? If I solve this in Laplace domain, this will be s square plus r by L s plus 1 by LC, where this will be omega naught whole square and this is actually 2 zeta omega naught, right? If you remember our standard second order circuit, standard characteristics equation of a second order system, s square plus 2 zeta omega n s plus, actually this should be s, I forgot to write the s over there, plus omega n whole square. Okay, this is the standard circuit, right? Standard equation. So here what will happen, is I will compare. So what is omega n? Omega n is nothing but omega naught, that is 1 by under root LC. 2 zeta omega n in our case is R by L, that is bandwidth, right? So from here my zeta will come out to be, zeta comes out to be R by 2L, R by 2 into under root C by L. It is nothing but the inverse of quality factor, right? And extra 2 term will be there. So this will always be valid actually. The relation between zeta in control systems and quality factor will be 1 by 2 zeta. So Q series will be 1 by 2 zeta. This relation also will be always valid. We will see this relation will always be valid. Okay. So few things are written here regarding quality factor, not that important for us. Okay. Yeah. So if I vary my quality factor, right? If the quality factor is higher, that means this field like the current characteristics with respect to frequency will be narrow. So I will pass narrow band of frequencies. Higher the quality factor, bandwidth will be lower. Okay, and I will pass lower band of frequencies. Lower quality factor, bandwidth will be higher. I will pass more frequencies. So if there is some noise, right, noise also will get passed. Let's say I want to only pass 10 megahertz frequency signal. I don't want to pass 11 megahertz. I don't want to pass 9 megahertz. So I will use a filter which has high quality factor, high Q. Okay, that is the purpose. That is the reason why we calculate quality factor, to understand which components I can pass. Same thing is written over here. Let's say I have a signal, low frequency signal or some frequency signal, and it is a combination of some high frequency noise. So if I have a high quality factor filter, we will only pass the original signal. This noise will not get passed. That is the advantage of a high Q filter. And already I have mentioned that your inductor voltage will be plus JQ into magnitude of VR. Capacitor voltage will be minus JQ into magnitude of VR. Okay, minus J because it will lag the current, plus J because it will lead the current. Okay. Now one more thing is there. What is the quality factor for a combination of coils? If I have combination of coils, what will be the quality factor? So let's say the quality factor of coil 1 is Q1. So it will be omega into L1 divided by R1. So L1, okay. So this is the quality factor of coil 1, and quality factor of coil 2 is omega into L2 divided by R2. So quality factor actually can be calculated at any frequency, not only at resonant frequency. Okay, it is simply omega into L by R. That is what my quality factor is. So from here, I can actually find out the combined quality factor. What will be the combined quality factor? Combined quality factor. So from here, right, I can find out L1. What is L1? L1 in terms of Q1 will be Q1 R1 divided by omega. L2 in terms of Q2 will be L2 will be equals to Q2 R2 divided by omega. L2 will be equals to Q2 R2 divided by omega. Okay. So yeah. So R is equals to R1 plus R2. R is equals to R1 plus R2. Okay. Like overall resistance of the circuit is R1 plus R2, and overall inductance of the circuit is L1 plus L2. Overall inductance of the circuit is L1 plus L2, right? So Q will be omega into L1 plus L2 divided by R1 plus R2. Q will be omega into L1 plus L2 divided by R1 plus R2. So L1 plus L2, L1 is this, L2 is this. If I add these values, right, omega is common. Omega will get cancelled. It will be Q1 into R1 plus Q2 into R2 divided by R1 plus R2. So for a series combination, quality factor as a combination of Q1 and R1, I can find it out. So sometimes what will happen is they will not actually, it is very simple. Quality factor is very simple. This value only, omega into overall inductance divided by the overall resistance. But what they will do, they will not give you this L1 and L2 value. They will not give you this L1 and L2 value. So they will only give you the quality factor of coil 1. They will give you the quality factor of coil 2. They will give you the resistance of coil 1. They will give you the resistance of coil 2. So with those values, you have to find out the quality factor of the combination. So that is how you will solve. Don't worry. Even if you don't remember the formula, now you know how to derive it, right? Now you know how to derive the quality factor of the overall coil. So individually you will find out L1, individually you will find out L2 from quality factor given, and from there you can solve without any frequency. Without any frequency. This is frequency independent. Frequency independent. Okay. Okay. So the key points about series resonant is that at resonance the voltage also gets amplified. Current is maximum. Voltage is maximum where voltage is maximum across the inductor and the, not maximum actually, voltage is amplified. like the maximum voltage is happening at this frequency, right, that we have derived here. But at resonance also it is amplified, so it is q times the source voltage. So q, if q is greater than 1, then it will be amplification, right, and generally q is greater than 1, so there will be amplification. So that's why it is also called as a voltage amplification circuit. It is also called as an acceptor circuit because the current becomes maximum. Okay, so these are the applications. You can go through the key points. Yeah, now we will discuss about the parallel resonance circuit. In parallel resonance, what happens? I've already told you that in series, higher impedance dominates. In parallel, lower impedance will dominate, or higher admittance will dominate, because admittance is inverse of impedance. So higher admittance will dominate in parallel, or lower impedance will dominate in parallel, because most of the current will flow through here. None of the current will flow through the higher resistive path, so I can neglect it. So again, in parallel circuit we will calculate the admittance. What will be the admittance? All of them are in parallel, so admittance of this is 1 by R and admittance of this is 1 by XL, 1 by XC. This time the capacitance provides positive admittance, right? So this will be plus 1 by XC, this will be plus 1 by XL. Okay, so overall, yeah, that is what will happen. And at resonance, what will happen? At resonance, what will happen? At resonance, XC will be cancelling out XL. At resonance, XC will simply cancel out the XL. Okay, so same condition again, XL will be equals to XC, so omega naught will be like, because 1 by XC is equals to 1 by XL, that means XL will be equals to XC, that means omega naught will be 1 by under root LC. Omega naught will be 1 by under root LC. Okay, so your current is IR plus J IC minus IL. Current is IR plus J IC minus IL. Okay, so imaginary component of I is 0. Imaginary component of I is simply 0. Okay, so like either you can make the imaginary component of I 0, because again your circuit will behave purely resistive. Again your circuit will behave purely resistive. Now one more thing is the current 0 here? No. Current is actually flowing, but it is flowing in this loop. No current is coming from here. How? So this is providing plus Z of impedance, this is providing minus Z. So overall the impedance seen from here is infinity. So that's why no current is coming here, but through this, right, some current is flowing in the loop. What is the value of the current? We can actually calculate. What will be the voltage? Voltage is V, right? V is what? V is I into R. So what will be the value of the current here? It will be voltage upon the reactance, that is XL, JXL, right? So that is the value of the current flowing through here. The current flowing through the other side is IR into minus JXL and minus JXC basically. And we know at resonance XL will be equals to XC, but these are of opposite sign, so that's why the currents are cancelling each other out. Okay, you can see the currents are cancelling each other out, only the real component of current is left out. Same derivation, nothing difference, but one difference is there. Now for lower values of omega, how will my circuit behave? For lower values of omega, inductive reactance will be low because XL is proportional to omega naught. So in parallel circuit, the lower impedance dominates. So for lower values of omega, circuit will behave as inductive. If omega is high, XC is inversely proportional to omega. So XC will be low when omega is increasing. So this XC will be lower, and in parallel circuit, the lower reactance dominates. So this will dominate now for higher values of omega. So circuit will behave as capacitive for higher values of omega. For lower values of omega, circuit will behave as inductive. Just the opposite of series RLC circuit. Okay. So same thing if you plot. Now I will not plot the impedance, I will plot the admittance. If you plot the admittance, you will see the admittance will be okay, admittance will be equals to, admittance will be minimum. Is it correct? What is the admittance value? Yeah, for any other frequency this will be non-zero, right? Yeah, this will not non-zero. For any other frequency this will be non-zero. This admittance will be non-zero for any other frequency. Admittance will be minimum at resonant frequency, or impedance will be maximum, because admittance is nothing but the inverse of impedance. Okay, if you plot the admittance now, for lower value of omega, that is omega less than omega naught, circuit will behave as lagging. For higher value of omega, circuit will behave as leading. That's it. So the, if you remember, impedance angle is theta v minus theta I, right? Because it will behave as lagging, so angle will be positive, impedance angle will be positive, but admittance angle will be negative, because admittance angle is theta I minus theta v. Okay, intuitively how we can understand? Intuitively you say omega equals to 0. If omega 0, capacitor will behave as open circuit, so no current will flow, all of the current will flow through the inductor, so inductance dominates, because this is simply 0 impedance, right? So for lower values, inductance dominates. When omega is infinity, what is happening? I will open circuit the inductor, because it is very high impedance. This will be short circuited. So in higher values of omega, capacitance dominates. So it will behave as capacitive. That's why omega greater than omega naught, the circuit will be leading. Omega less than omega naught, circuit will be lagging. So that's also how intuitively you can understand that whether my circuit will be leading or lagging. Okay, same thing I have explained over here, right? Like what are the angles, voltages, all these things. And again the half power points, again if you calculate, this time your voltage will be maximum here, right? And here it will be 1 by root 2 times the voltage. This time we are plotting the voltage, we are not plotting the current, we are plotting the voltage. So again half power points you will calculate. If you calculate the half power points, you will see that this result will be same, although your bandwidth will not change. Okay, your bandwidth will not change, but the result, this, right, ultimate result is same. So you don't have to remember anything separately. What do you need to remember? Omega naught is same, omega h, omega l are same in terms of bandwidth and omega naught. What do you need to remember? Bandwidth. Bandwidth has changed. Bandwidth is 1 by RC. This is not a function of inductor anymore. 1 by RC. How do you remember bandwidth? So for a series circuit, bandwidth is 1 by time constant. Okay, shortcut. It is not like, it is not literally 1 by time constant. Okay, just how to remember. What is time constant for a circuit? Time constant is L by R, right? For a series RL circuit, right? Time constant is L by R. So it will be simply R by L. And go back to the page and you will see the bandwidth is R by L. Now for a parallel RLC circuit, you will say that again bandwidth is 1 by tau and your time constant is 1 by RC. Sorry, your bandwidth is 1 by tau of a RC network, so it will be 1 by RC. Time constant of RC network is R into C. So this is a short trick to remember the bandwidth. So I have given you all the tools to remember the formulas. Okay, so that's how you remember. Again you will see that this omega h into omega l will come out to be omega naught square. So you don't need to remember omega h, omega l, omega naught separately. Only these things you have to remember. Okay, so yeah, again the table if you do, you will see like the same results. At half power points, the angles will be plus 45 or minus 45 depending whether it is lagging or leading. Okay, now what is the uh, formula for quality factor? Formula for quality factor will not change. It will be q upon, sorry, omega naught upon bandwidth. This will be always true. Now here omega naught is same 1 by under root LC, but the bandwidth has changed, right? For a parallel circuit, bandwidth is 1 by RC. So that's why you see that the quality factor also for a parallel circuit has changed. Okay, it is nothing but the inverse of the series circuit. Inverse of the series circuit. Okay, so how do you remember? You remember this quality factor formula, omega naught upon bandwidth. This will be always valid. Series RLC, parallel RLC, no matter what, this will always be valid. Okay, so yeah, that's how you remember. Again, if you compare the zeta, right, this relation will be again same. Q is equals to 1 by 2 zeta. In series circuit as well, if you remember, in series circuit as well, we derive that my quality factor was equals to 1 by zeta. Have I derived it? Have I written it? Where is it? Quality factor was equals to 1 by 2 zeta. If you see, where has it gone? here quality factor is equals to 1 by 2 zeta, and in parallel circuit as well quality factor will be equals to 1 by 2 zeta. So that formula is same, that will not change. Here also I have derived quality factor is equals to 1 by 2 zeta. Okay, zeta of a parallel circuit. So this will not change actually, this will always remain same no matter what. Okay, so I hope it is clear. These are the summary, you can have a look at this. And it is called as a rejector circuit because what happens, it is at resonance, right? As at resonance, uh, basically the current, it blocks the current because the impedance is, admittance is minimum. At resonance admittance is minimum but impedance is maximum, so higher the impedance it will block more current, right? So as it is a blocking, like it blocks current, that's why it is called as a rejector circuit. There the current was maximum, that's why it was called a acceptor circuit. Now I will show you the questions, you try out these questions and I will come back with the solutions. Okay, this is one question, this is one question, all of them are like, this will be very cakewalk for you, very easy. This is another question, this is another question, another question. I think this is, yeah, this is the last question. Okay, let's solve this question. So here let's solve this first one. Most of the cases, if some coil is given, right, it is a RL load, series RL load. A coil is a series RL load. Okay, an air core coil having winding resistance R is equals to 10 ohms connected in series with a variable capacitor Cx. Okay, now what are they asking? They are asking me in series by a 10 volt sinusoidal source. So if nothing is mentioned, I will assume this to be the RMS value. So 10 volt is the RMS value. Angular frequency 1000 radians. As the value of the capacitor is varied, a maximum voltage of 30 volts is observed across it, neglecting the skin effect, the value of the inductance of the coil in millihenry. So the maximum voltage across the capacitor is 30 volts. Okay, maximum voltage across the, if I vary the C, maximum voltage across the capacitor is 30 volts. What will be the value of the inductance? Okay, so when does the voltage is maximum across any like series RLC circuit? At resonance, right? We know the voltage across the capacitor will be minus jq times magnitude of the voltage across the supply. So the magnitude of the voltage across the capacitor will be q into v, right? The magnitude of v is given to me as 10, magnitude of vc is given 30. So from here I can easily find out what is my q. Q is simply 30 by 10, that is 3, right? And I know q is equals to omega L by R, quality factor of a coil. I know q is equals to omega L by R, right? This will always be valid, and this also is always valid, right? So Vc will be q into v. So I get the value of q at this particular frequency 1000. Okay, and from there I know q quality factor is omega L by R. I know what is my R, but I know what is my omega. Omega is 1000. I know what is my q, so I can easily find out what is my L. So L will be 30 millihenry. This will be the answer of this question. Pretty simple, but the wording of the question could have been better actually. But yeah, this will be the answer. L equals to 30 millihenry will be the answer for this question. So let's solve this next question. So we have, and this is a gate BM question, okay. We have an ideal inductor with inductance 1 by 3. So inductance is given, it is ideal, and it is connected across a sinusoidal voltage source, right? we're connecting it across a sinusoidal voltage source, and the energy stored in the inductor, actually the wording should have been correct, the maximum energy stored in the inductor is 6 joule. Okay, they should have properly worded this. So maximum energy stored across the inductor is 6 joule. That means basically E max, right? EL max. One second. EL max is 1 by 2 half L I L max whole square. Basically the peak value of current whole square, right? So what will be my peak value of the inductor current? It will be, I know the inductance, that is 1 by 3. So it will be like EL max is 6 joule, right? 6 joules is the energy stored, and multiplied by 1 by 2 into 3, that is 6. So IL max, the peak value of the inductor current, right, is 6 amperes. That is what my peak value of inductor current is equals to. Okay. Now I have to find out the maximum power delivered to the inductor. What is the maximum power delivered to the inductor, right? How will I calculate this? They are just asking me the instantaneous value, because average power is 0, because it is an ideal inductor, it will not absorb any power. So whatever power it absorbs, it delivers in the second half cycle, right? So maximum value of the current is 6 ampere. So if I assume the current to be a sinusoidal function, right, IL of t, it will be IL max, that is 6 sine omega t. So what will be the voltage VL of t? It will be L DIL by dt. So L is 1 by 3, and what is the differentiation of this? It is 6 into omega into cos omega t, right? So it is simply 2 into omega, and omega is simply 100 pi, because f is 50 hertz. So it will be 2 into 100 pi, so 200 pi cos omega t. Now what is the power function? Power function is I of t into V of t, right? V of t into I of t, that is equals to 6 into 200, so 1200 pi sine of omega t into cos of omega t. So I can actually convert this, right, to sine AB. I can convert this. So this will be 600 pi sine of 2 omega t, right? I can convert this. Yes, this can be converted. So the power function will be this 600 pi sine of 2 omega t. Now they are asking us what is the peak value of power delivered. What will be the peak value of power when 2 omega t, at what value of omega t? When my omega t is pi by 4. When 2 omega t is pi by 2, that means omega t will be pi by 4. That means this will be 1. The maximum value is 1. This is 600 pi. So 600 pi is the maximum value of the power that will be delivered. Now in the answer key they have given option A, but I think option A is incorrect. I think option B will be the correct answer for this particular question. Okay, according to me, option B will be the correct answer for this question, because they are asking us the maximum value of power. Average power is 0, right? If I integrate this, average power is 0. Ultimately they are just asking me the instantaneous value of the power. Maximum value means instantaneous value of the power. Let's solve the next question. An inductor having Q factor, quality factor as 60, okay, is connected in series with a capacitor whose quality factor is 240. What will be the overall quality factor of the circuit? This question came actually in during my time, and I just assumed a formula. 1 by q will be equals to 1 by q1 plus 1 by q2, and I solved and I got the correct answer. But I did not knew what is the concept behind this. Okay, so basically, right, we have a series RL circuit, right, and then we have a with a capacitor having a quality factor of this, right. So if the capacitor has a quality factor of this, for capacitor, right, we will assume it as a parallel RC circuit. So now they are asking me what is the overall quality factor. So overall quality factor, how do I calculate the overall quality factor? Okay, just give me 1 second. capacitor quality factor. Okay. So this also, if I assume as a capacitive reactance, series capacitive reactance, and let me assume this as RL, this as RC. Okay. So what is Q1? Q1 will be equals to omega into L or XL divided by R. What will be Q2? Q2 will be XC divided by this will be RL, RC, right? And one more thing we know, that at resonance my XL is equals to XC, right? So my RL actually is equals to Q1 by X. I will assume this to be X, right? So Q1 by X and RC is equals to Q2 by X for a series RLC circuit, right? Q2 by X. So here, right, what is the overall quality factor? Overall quality factor will be overall reactance, any of, you can choose any reactance, upon the overall resistance RL plus RC, right? So this will be X upon RL is Q1 upon X and RC is Q2 upon X, right? So am I correct? Just give me 1 second. Omega naught L by R, yeah, omega naught L by R, yes, this is correct. So overall quality factor will be, yeah, X by R, okay, X by R, RL, sorry, I've written this inverted, right? XL by Q, and this will be XC by Q, right? Q2, okay, sorry. So this will be, because XL is equals to XC, this will be Q1, this will be X by Q2. So here this will be X by Q1 plus X by Q2, okay, at resonance condition. So this will be simply X will get cancelled. So your Q, right, will be 1 by 1 upon Q1 plus 1 upon Q2. That's it. Q will be 1 upon Q1 plus 1 upon Q2. Now you will say, sir, how is this like a formula? Now we can go to the derivation, but that will take huge amount of time. Just know how to solve this kind of questions, okay? And this will not come in easy. In electrical, this will come, and you have to just know, like, you have to put the resonance condition. XL will be equals to XC, and you have to find out the individual coil resistances, okay? And from there you can solve. So your overall Q will be 1 by Q1, like Q1 is how much? Q1 is 60. So 1 by 60 plus 1 by Q2. Q2 is 240. Okay. So this will be, I can solve this value. This will come out to be basically 1 by 48, right? Yeah, this will come out to be 1 divided by 4. So 5 divided by 240, which is simply 48. So your answer will be 48 for this particular question. Let's now solve the next one. So for the network shown below, the resonant frequency is 150 kilohertz and the bandwidth is 600 hertz. What is the Q factor? So whenever resonant frequency and bandwidth is given, you will not solve the circuit, okay? You know this very basic formula. Your quality factor is always equals to resonant frequency omega naught upon bandwidth. The lower the bandwidth, the higher the quality factor. Lower the bandwidth, higher the quality factor. So this resonant frequency is given to me, that is 150 kilohertz. Bandwidth is also given to me, that is, okay, just that is 600 hertz, right? So this is 4. So this will come out to be 250. So quality factor will be 250 for this nearest answer. This will be the answer for this question. Simple formula based. Electrical mostly formula based question comes. The band pass filter, okay, simple RLC filter sometimes is also called as a band pass filter. Values are given. The Q factor, again, for a series RLC circuit, it is either you can write omega naught into L by R. Quality factor is omega naught into L by R. What is omega naught? It is 1 by R under root L by C. Okay, because omega naught is 1 by under root LC. So your quality factor, right, have they given me the, yeah, they have given me the values of L naught. So 1 by R is 1 by 50 into L. L is 1 millihenry C is 10 nano. So 10 into 10 raised to the power minus 9. Okay. So this will be equals to 10 raised to the power minus 8, 10 raised to the power minus 5. Okay. Some like decimal place value will come. I'll quickly calculate this. So 10 raised to power 6, 10 raised to power 5, 10 raised to power 5 whole under root divided by 50, 6.32. Okay. Yeah, that is what your quality factor is, 6.32 divided by 50. Yeah. Under root L by C, L is 10 raised to power minus nano, 10 nano, 10 raised to minus 10 raised to 5. 6.32 is the quality factor basically. Okay, this is the answer for this particular question. Yeah, let's now solve the next one. So here we have been given a RLC circuit and the value of R and C are fixed. L is valid to deliver the maximum current. Okay, we want to deliver the maximum current. This value is 0.4 ampere and the corresponding potential drop across the capacitor is 330 volt. What will be the value of the inductor? Simple, right? When is the current maximum in a series RLC circuit? When the reactance, capacitive reactance is equals to the inductive reactance. So XL will be equals to XC. So omega into L for a certain value of L, right? I am varying my L, will be equals to 1 by omega C. So C value is not given to me. Omega value is known to me, right? Okay. All these things are not known to me. So this is not of any use to me. But I know the maximum value of current, I max. Like this is the value of the current, maximum current. Basically, peak value of, not the peak actually, the RMS maximum value of current. So the current becomes maximum, that is 0.4 ampere, and the voltage is what is the VRMS? If nothing is mentioned, you will assume that all these values are RMS values. Okay, if nothing is mentioned, you will assume all these values are RMS. So VRMS equals to 220 volt. So your R will be equals to VRMS upon IRMS. So 220 upon IRMS, that is 0.4. So 220 upon 0.4, right, is 550. So R is 550 ohms, but have they asked us that? No, they have not asked us that. So they are interested in the value of L. What will be the value of L? Okay, one more thing I know, that they have given me the potential drop across the capacitor, and I know at resonance what used to happen, the VC, magnitude of VC is equals to Q times magnitude of V. So VC is given to me 330, Q I don't know, magnitude of V I know, that is 220, right? So your Q will be 3 upon 2. Okay, so it is 1.5. Q is 3 upon 2, that is 1.5. Okay, and this Q is what? This Q is nothing but omega into L by R. I know the value of R, I know the value of omega. Omega is 100 pi, right? 100 pi. So I can easily calculate the value of L. L will be 1.5 into R. R is 550 divided by 100 pi. So this value into 1.5 divided by 100 divided by pi, 2.62. Okay, 2.62 Henry. This will be the answer for this question. This will be the answer for this question. Okay, yeah. Let's now solve the next one. So next one, we have a series RLC circuit. Q factor is given. Center frequency. Center frequency is also called as the resonant frequency, right? Remember, this is in radian per second. This is also Q is given in Q is 1000. So they're asking me the possible values of R, L, and C. Like simple, what you can do is Q is given, right? So Q is what? Q is omega not L by R. Okay, only Q is given. Okay. So what will be the Q is what? Q is bandwidth. sorry, omega naught upon bandwidth, right? So what is my bandwidth? Bandwidth will be omega naught by q. So omega naught is 10 raised to the power 6, q is 1000, right? So bandwidth will be 10 q. And what is bandwidth in series RLC circuit? It is R by L, inverse of time constant. So I will just see the ratio of R and L. Okay, I will just see the ratio of R and L. So if I see the ratio of R and L here in this case, right, this is simply 10 raised to the power 6, which is not possible. It has to be 10 cube. This again is not possible. This, right, again not possible. Only this combination is possible, right? Bandwidth has to be 10 cube. So R by L is 10 cube only in this option. In the other options it is not 10 cube. So option D will be the correct answer for this question. So here we have been given the frequency of this supply. R1, R2 values are same. L value is given, right? And they are asking us the value of the capacitance for which your admittance will be purely real. When does my admittance becomes purely real? When I get the resonance condition, right? Either admittance or your impedance will be purely real. Basically, you will not have any imaginary component. Now, if you try to solve this, right, using basic calculating the impedance and then solve it, it will be very lengthy for you. The shortcut is, I have taught this in my full course. I have proven as well the expression for omega naught for these circuit. Okay, the expression for resonant frequency for this circuit, I have derived this. This will be very helpful. So I will tell you to remember this. Very easy to remember. The omega naught for this circuit will be this 1 by under root LC that is already present in normal series RLC or parallel RLC circuit into whole under root. In the top I will have RL whole square. Why? Now why will this be square? I will explain. In the top I will have RL, in the bottom I will have RC, because in the top always, if you remember the characteristics impedance, the formula for it was under root L by C. If you have studied power systems, you will know the formula of characteristics impedance, right? Or somewhere you must have seen this term, right? So at the top always L will be there, at the denominator C will be there. So numerator RL will be there, denominator RC will be there, minus L by C. Why? It will be minus L by C. Now what is the unit of L by C? The unit of under root L by C is ohms. If I square it, this will be L by C. So I am squaring ohms. So the unit of L by C is ohm squared. So here also I should have ohm squared. So this will be RL whole squared, not only RL, because I'm subtracting two quantities. Both of them must be of same units. Otherwise I cannot subtract them. So that's why this will be squared. So now I hope it is clear. How can you remember this formula? Okay. Now they are telling me that your admittance is purely real. Basically that means your circuit is operating in the condition of resonance. So basically whatever frequency they have given me, that frequency is actually the resonance condition. So in place of omega naught I will place here 100 pi. Okay, I will place here 100 pi, and your RL, that is the resistance connected with inductor, and RC, resistance connected with capacitor, both are same value. So if both of them are same value, right, RL equals to RC, this will simply get cancelled. So my omega naught, simplified formula of omega naught will be 1 by under root LC. That's how simple it became, right? Simply it is the normal series RLC result. Okay, so it becomes 1 by under root LC. Now you can simply solve it, right? I know L value is given to me, right? So I can easily get the value of C. So C will be 1 by L into omega naught whole square. Okay, if you solve this, it will come out to be 1.44 millifarad. You can solve this. Omega naught is what? Omega naught given, like the resonant frequency they have given me, that is 100 pi, right? L is given to me, that is 7 millihenry. You solve all this, right? You will get the value of your omega naught as, capacitance value as 1.44 millifarad. Okay, now let's solve the next question. So next question is this one, that this is a GATE BM 2025 question. The following frequency response are given. Which one is a frequency response of a notch filter? So a notch filter, I had told you in today's lecture itself that a notch filter behavior is something like this, whose bandwidth is very, very low. Okay, so this is a notch filter, but this is a band pass filter, because it passes particular band of frequency, because for other frequencies the gain is very low. Here, so these are not notch filters, because here I see bandwidth is very high. These are anyways gone. Bandwidth is very high, right? Bandwidth is very high, but here the bandwidth is very low. So, but here the special thing is it is rejecting particular frequencies, it is passing all other frequencies. So this is also a notch kind of filter, because the shape is like a notch filter, right? But this is a band stop filter, okay, because it rejects particular band of frequencies, that's why band stop. It passes all the other frequencies, because for all other frequencies the gain is very high. So this is also a notch filter, but it is a band stop filter, okay. This is also a notch filter, but this is a band pass filter. So option D will be the correct answer for this question, okay. Now let's quickly discuss bit about network theorems in AC circuits. Like, there is no difference in network theorems in AC and DC, both are same only. But if you still have some theoretical doubts, right, you can go and have a watch at these two videos. Make sure you watch these two videos. This video is the theoretical portion, the like 1.1 hour 1.5 hours videos, okay. You can have a quick watch on this. So I have covered everything, the Thevenin's theorem, Norton's theorem, the superposition theorem, maximum power transfer theorem, and the assignment solutions. So make sure you watch these two videos. If you feel like I'm weak in the network theorems in AC circuits, okay, I will solve few questions, don't worry. But from this lecture, right, I have just taken the most important topic, that is the maximum power transfer. Okay, other topics are similar, you will be able to figure it out, but maximum power transfer is the topic where questions mostly gets asked generally, okay, in AC circuits, okay. So what happens basically in maximum power transfer, right, you will have a source, you will have a load, okay. And this time, right, in DC systems your source was purely resistive and your load was also purely resistive. But in AC circuits your source can be like can contain imaginary terms, imaginary impedance, that is it can contain reactance, and your load can also contain reactance. In that condition, what will be the value of the load resistance so that maximum power is delivered, okay. There are many conditions, so I have already taught this in my full course, so I'm just going through in a quick manner. So if the source impedance is Rs plus jXs, basically source impedance contains everything, both the reactive component and the resistive component. And if in case of load, the reactance is fixed, I cannot vary the reactance, only I can vary the load resistance. Then your load resistance must be this value. What is this value? It is Rs whole square plus Xs plus XL. How do I remember it? Simply, it is the overall impedance except the RL, right? What is the overall impedance? Like, here I have this Rs, here I have this reactance. Now this can be plus J or minus J, depending, this can be positive or negative, I don't know, okay. So for now this is plus Jx, it can be negative as well. If it is negative, you will put here negative, right? You will put here in place of Xs, you will put the negative value. Let's say it is minus J1, you will put here minus J1, because assumption is if it is plus, that means it is inductive load, if it is negative, it is capacitive, okay. And here also plus means it is inductive load, but they might give you capacitive load, then here you will put negative value, here you will put negative value, okay. So this will be Rs, and here also I will have RL, that is varying, and here I will have plus J XL. As it is plus, assumption is it is inductive, but it can be capacitive. If it is capacitive, this will be minus J XL, okay. So your overall RL, right, will be basically the impedance, magnitude of the impedance except RL. What is the overall magnitude of the impedance except RL? This value, right? That's it. That is what we have done. It is simply the magnitude of the impedance except RL. And from this, right, you can derive all these values. Like if okay, let me come here. If XL is not present, right? If XL is not present, then you will just make XL 0. This formula will come up. Okay. If XS is not present, only RS is present, then you will make XS also 0. Then this formula will come up. Okay. And if XL is present but XS is not present, then again you will make XS 0 in this formula. This formula will come up, right? This formula, RS whole square plus XL whole square. That's it. So you remember this one, other things will be automatically sorted. You remember this one, other things will be automatically sorted. Now there comes another case where my RL is fixed. I cannot change my RL, but my XL is varying. So how can the maximum power be transferred to RL, right? In that case, what we do, we make the circuit purely resistive. Then only the maximum power will be transferred to RL. So I make this combination, right, XL plus XS equal to 0. Basically, there will not be any imaginary part in the circuit, only real resistances will be present. So this is the case where my load reactance varies only. Okay. And in the case where both varies, both load resistance and load reactance varies, is variable, then how can the maximum power be transferred? I will simply apply this condition. I will make the imaginary part 0 and I will make the real part equal, right? Once I make the imaginary part 0, right, then it simply becomes a maximum power transfer problem in DC circuits, because the circuit will behave as purely real, right? And in purely real, what was the condition for maximum power transfer? My load resistance must be equals to my Thevenin resistance seen from the load side, right? So first of all, if both of them are varying, first you will make the reactive component of the whole circuit 0, then you will make the load resistance value equals to my Thevenin resistance seen from the load side. Okay, that is what we have done here. Basically, ZL will be equals to ZS conjugate. ZS conjugate means it conjugates this source side. It it takes a negative sign of this source reactance, right? So this gets cancelled. Only the source resistance is present. Okay. So yeah, these are the conditions basically. Now if my RL is varying, XL is varying, and on the source side I only have a reactive component, I don't have any RS, source resistance, then RL can take any value, but XL must be equals to minus XS, because for any value of RL, load will always get the maximum power, right? Because there is no source resistance. So my first task will be, when XL is varying, I will first nullify my reactive component, then RL can be any value. RL can take any value for maximum power transfer. Okay, let's solve few questions. In the circuit given below, uh, for maximum power to be delivered to RL, its value should be, what shall be the value of RL for maximum power transfer? So again, what is this condition? This condition is the case where I only have RL, I don't have any XL. So RL should be equals to the RS whole square plus XS whole square. Now first of all, I will convert this whole circuit into its Thevenin equivalent, right? I'll convert this whole circuit into its Thevenin equivalent, then only I will solve. So this what is this reactance? X1 will be plus j, omega is given 1 kilo, right? 1 kilo is given, so this will be plus j4. What will be this? This will be minus j2, right? 1 by omega c, 1 kilo is there, so minus j2. So yeah, if I convert this circuit, right, into its Thevenin equivalent, here I have this reactance of plus j4 here I have this minus j2, this will be 2. Okay, now I'll convert this into Thevenin equivalent. So what is the Thevenin impedance? ZTH, right? So this will be shorted then. If this is shorted, right? So overall this is basically a parallel combination of 2 and plus j2, right? So what is my ZTH? ZTH will be equals to 2 into j2 divided by 2 plus j2. So this will be j4 into 2 minus j2 divided by 2 square 4. So this will be basically 2 plus j2. Oh, same only. Okay, 4 will get cancelled. Yeah, 2 plus j2. Okay, so 2 plus j2. Now what do I need to do? I just need this, right? This, I don't care about VTH. I have this Thevenin resistance and this Thevenin reactance, and I have the load connected RL over here, right? RL. So what will be my value of RL for maximum power transfer? It will be RS whole square plus RXS whole square. So it is 2 under root 2. So it is 2.82, something like that. Am I correct? 2.82. Just give me 1 second. Let me cross verify once. 2 is here, okay. 4 is here, yes, everything is correct. 4, this is 2, this is 2 ohms, right? Yes. So 2 into J2 divided by 2, this is J4, yes. This is 2 minus J2, yes, J2, yes. 2, sorry, 2, oh, what am I doing? 2 square plus 2 square is 8, right? Or 4 into 2. And this is correct only. Oh, sorry. 2 square plus 2 square, 8, that is 4 into 2. So it is 2 under root 2. Yeah, it is correct only. What am I doing wrong? So it has to be 2.818 ohms. Yeah, one small mistake I just make here, right? This will not be 4, right? Because I'm cross multiplying here. This will be 2 square plus 2 square. That's why I'm thinking, where am I making the mistake? Okay, just give me 1 second. This will be 2 square plus 2 square, right? So that is 8 actually. So this will actually be 1 plus j1. So this will be 1 square plus 1 square. So this will be under root 2 actually. Yeah, under root 2. So this will be under root 2 is simply 1.414. That is what I was thinking, that what mistake I am making. So answer will be under root 414. This will be the answer of this question. So for the circuit shown, if the current I is equals to sine 1000 of t, okay, the instantaneous value of the Thevenin equivalent voltage across terminals AB at t equals to 5 milliseconds. So let me find out the expression for Thevenin voltage across terminals AB, then I will find out the value of that voltage at this particular time. So interesting question. So here at Thevenin voltage means like this will be open circuit voltage, no current will flow, all of the current will flow through here, all of the current will flow through here. So I current is flowing through here, I current is coming here. So from here what current will go? This minus Ix, right? So if I copy this circuit, so from here what current will flow? I minus Ix, okay, I minus Ix current will flow. So this will be okay, I can apply a KVL in this loop, right? Because it will be in terms of Ix only and I. So if I apply a KVL, this will be minus J10 into minus Ix, because this is in the opposite direction, minus 10 into Ix. I'm just applying a KVL in this loop. Plus 4Ix sorry, plus 10 into I minus Ix plus J10 I minus Ix, okay, so equals to 0. So what can I say? So this, right, will be plus J10 Ix minus 10 Ix plus 4 Ix plus 10 I minus 10 Ix plus J10 I minus J10 Ix equals to 0. So minus J10 Ix plus J10 Ix gets cancelled. J10 I, okay, that can go on that side. 4 Ix, right? Okay, this is 10 Ix. So this side I have minus 20 Ix. Okay, this Ix is also there, right? So yeah, minus 20 plus 4, so minus 16 Ix, that can go on the right hand side. So it will be 16 Ix will be equals to um, 10i if I take common, minus j. Okay, so from this I can easily find out what is my ix. What is my ix? Ix will be 5 by 8 1 minus j. Okay, that is what my ix is equals to. But what do I have to find out? I have to find out the vab, right? What will be vab? Vab will be like this voltage drop, right? What is this voltage drop? This voltage drop. So vab is equals to ix into 10 plus, sorry, minus j10 into ix, because the drop, like it is a capacitance. So it will be ix, if I take common, this will be 10 minus, sorry, 10 ix I can take common, it will be 1 minus j basically. Okay, so this will come out to be yeah, 1 minus j. Am I correct here? This is minus j, this will be minus j, right? Plus, okay, sorry, one small mistake I have made here. This is plus j10i, right? This plus j10i. Okay, yeah, this is plus j10i, this is plus, so this will be plus. So that's why you should do rough very carefully, right? You cannot do rough in a very messy manner. Okay, plus j10i. So this will be plus 1 plus j, sorry, this will be minus, this will be plus 1 plus j. So if I multiply these two, right, they are complex conjugate, so I will only get the real portion. So this will be ix is, I already know the value, so 50 by 8 into 1 square plus 1 square, right, it will be equals to 100 by 8, that is 12.5 volts. So vab is 12.5 volt. Remember, this is phasor, right? VAB complex quantity. These are complex quantity. This is not a constant value, right? It is a phasor. VAB is a phasor. This is a complex number, and Ix is a phasor quantity, right? Ix is a phasor quantity. It is not a constant number. Okay, all these are phasor. I, right? What is I? I have replaced here I. Have I replaced though? Okay, I forgot to replace I. Okay, sorry. Yeah. Okay, yeah. Forgot to write I here, right? I. Okay, this is my ix. Ix is 5 by 8, 1 plus I, right? So yeah, here I forgot to write. This will be I actually. And I, right, in phasor, if I assume my reference to be sine 1000 t, so it will be I will be equals to 1 angle 0. If I assume this to be my reference, right? So that's why I have replaced here with 1 angle 0. With 1 angle 0, so that's why this became 2.5. Now if I want to come back to my sinusoidal format, this will be magnitude is 12.5 sine 1000 t, right? And they are asking me the value of the voltage at time t equals to 5 milliseconds. Milli, 1000 and milli will get cancelled, so it is simply sine 5. So they are asking me the value at 5, sine of 5, right? This value. So this value will be, so these kind of questions can get asked easy, right? This is a gate IN question, I guess. No, this is a double E question. Not that difficult, but just you have to solve the circuit slowly. Okay, have patience. So sine of 5 will be into 12.5. Yeah, something 1.809. Am I correct here? Just okay, sorry, sine of 5, right? This is not, this is in degrees. So my calculator also is in degrees and radians. So make sure you are changing it. Okay, 12.5 into sine of 5. Yeah, minus 11 point 11.965. Okay, volts. So yeah, that's it basically. And yeah, this is the answer, minus 11.968. What they have asked in two decimal places. If I write this in two decimal places, this will be minus 11.99. Okay, this will be my answer of the question. I think approximately 12 was the answer. So with this we end our network theorems. Now we will start with two ports networks. So let's start with two port networks. So in two-port networks, mainly it is mostly mathematical. There are mostly four types of parameters that we have to take care of. Okay, and understanding one parameter is enough. Like Z parameter, if you understand Z parameter, you will be able to understand Y parameter. If you understand H parameter, you will be able to understand G parameter. If you understand ABCD parameter, you will be able to understand inverse parameter. So mostly you have to focus mostly on Z parameter, Y parameter, H parameter, and ABCD parameter. So mostly the question will be asked from these four parameters. Other two parameters you can derive. Okay. So first of all, let's discuss few basic terms known as terminals. What is a terminal? So terminal is nothing but either the input or output of a device, right? So it terminal is this one. This is the terminal. Okay, one point. Basically, in network analysis, terminals are the physical points where the circuit elements or components are connected. So I'll connect the terminals here. Now remember, sometimes what happens is we have a common terminal known as ground. We don't name it. Okay, here also for a common source amplifier, the source terminal is ground. So it is common, right? It will be always grounded. Only we can connect to the drain and gate terminal. So these are called as terminals. Each point out of the circuit elements are called as terminals. So input terminals are those terminals where we provide input to the signal. So for a MOSFET, we generally provide the input to the gate terminal. So that is why it is called as input terminal. And for a MOSFET, we take the output from the drain terminal. So that's why it is called as a output terminal. And with respect to what? With respect to the source. That is not mentioned, but it is understood that we are able to understand that we are taking the output with respect to the source. Okay. So this is my input, output, and common ground terminal. A two-port network is an electrical network with two input terminals, two output terminals. So port 1 and port 2. Okay. So yeah, that is the case. So what is a two-port network now? Two-port network is a network in which I will have two input terminals, two output. So two input terminals, two output terminals, those are called as a two-port network. A single port network will be a network in which I will have only a single port, that is two terminal device. Okay. A two-port network will be a device where I will have two ports, right? Each port will have two terminals. So each port consists of two terminals, and in two-port networks I will have two ports. That is what is written over here. Okay. So what is the condition for a port? Condition for a port is that whatever current enters through the through that port, right? Through a terminal of that port, it should come out. Same current should come out of that other terminal. Let's say this is port 1. If this is port 1, it has to satisfy the condition that whatever current entering the terminal through this port should be the same current that is exiting the other terminal through the same port. So then only it will satisfy the condition of port. Okay. The voltage between two terminals is known as the voltage across that port. Okay. So I hope now you know what is a terminal, what is a port. Okay. What are the conditions of a two port? Now in a two port network, right, I have four variables. V1, the voltage across the two terminals, the current entering through port 1, the current entering through port 2. So these are my four variables, like, and the voltage across the port 2. So these are my four variables. So I can write my V1 as a function of V2 and I2, and I can write my I1 as a function of V1, V2 and I2, right? So, or I can write my V2 as a function of V1 and I1. I can write I2 as a function of V1 and I1. So I have many choices. So actually what do I need to do? I have four variables. Out of four variables, I need to choose two variables so that I can write those two variables in terms of the other two variables. In how many ways I can choose two variables? So it is 4C2. So from this we get the derivation that 4 into 3 divided by 2, that is equals to 6. So total 6 kinds of parameters we will get. So that is what I have derived over here. That in total there will be 6 types of parameters. So out of 4 parameters, I have to choose any two so that I can write the other two in terms of the chosen two, right? To characterize any two-port network, so we can have at max 6 kinds of parameter. Okay. So there are many applications, like you will apply this in everywhere, analog electronics, in EDC, so not EDC, EMFT, in power system, in machines, everywhere we will analyze this, right? Use this two-port network concepts. So it is actually very helpful to us, right? So there can be total 6 kinds of parameters. So these are my 6 kind of parameters, as I have mentioned previously as well: impedance parameter, admittance parameter, hybrid parameter, transmission line parameter, inverse hybrid parameter, and inverse transmission line parameter. Okay. So very easy, not that difficult. So first we will discuss about the impedance parameter. What is impedance parameter? As the name suggests, the coefficients will be, the units of the coefficients will be impedance, ohms. The units of the coefficients will be impedance. Basically, in impedance parameter, I write my voltages in terms of my currents. In impedance parameter, I will write my voltages in terms of current, in terms of my currents, right? I will write my port voltages in terms of the port current. So V1 will be equals to Z11 I1, Z12 I2, and V2 will be equals to Z21 I1 and Z22 I2. Now this Z11, Z12, Z21, Z22 are actually called as the Z parameters of a network. So this will always be unique for a particular network. These cannot change. If the network is fixed, then the Z parameters also is fixed. Okay. So if I know the network, I can easily find out the Z parameters, and then I can calculate any value. Okay, any unconditional value. We will solve this question, then we will understand. So how do you find out the Z parameters? There are many ways to find the Z parameters, right? What you can do, you can make the I to 0, right? If you make the I to 0, and if you take the if you apply some voltage across the port 1 and measure the current, the ratio across the same port, the ratio of the voltage and the current will be Z11. What did I say? I said you open circuit my port 2. Okay, I open circuit my port 2. Okay, so I2 current is 0. Then I apply some voltage in the port 1. I apply some voltage in the port 1. Then I measure the voltage and the current. Then I measure the like I already know the voltage. I measure the current with the ammeter. The ratio of that current and the voltage will give me Z11. The ratio of the current and the voltage will give me Z11. Okay, that is what my Z11 parameter is. Now, similarly, as the port 2 is open, right? If I find out the ratio between V2 and I1, I will be able to get my Z21. Okay, so what I can do is I can keep a voltmeter here and measure the open circuit voltage across the port 2. So if I measure the open circuit voltage across the port 2, sorry, so that will be the V2 value, and if I take the ratio of V2 and I1, that will give me the Z21. Similarly, same experiment you can do by making I10, basically open circuiting the port 1 and measuring voltages at port 2. Like that was the physical meaning of how actually we measure Z11 in circuits. Okay, but in reality, but in like our exam, you will not be given like you will not be given ammeter, voltmeter, right? You will actually have to calculate theoretically, like in pen and paper. So basically, in our case, what we do, we simply make I to 0. We'll then find out the ratio of V1 by I1. How? We will solve few questions there, you will understand, and we'll make V2. Then we will find out the ratio of V2 by I1. So basically, your Z parameters, right, are this. Here. These are my Z parameters. So Z11 is actually sometimes called as the open circuit input impedance, because we open circuit the output port. We make I to 0. Okay, and we find out the ratio of V1 by I1. But please be careful that it is not the Thevenin impedance seen from this port. No, Thevenin impedance, if you remember, it was a unconditional parameter. We did not open circuit anything. In Thevenin, if you remember, we just, what we did, we nullified the sources. That's what we did, right? We just nullified the sources, but we did not open circuited the second port. Okay, because in this port some device can be connected. So this actually is not Thevenin impedance. Okay, it is just the Z11 Z parameter Z11, that is V1 by I1 when the port 2 is open circuited. Similarly, Z12 is sometimes called as transfer impedance from port 2 to port 1 when I1 is open circuited. Okay, and Z21 is called as a transfer impedance from port 1 to port 2 when port 2 is open circuited. Okay, similarly you can, like this ratios you can understand how to remember. So Z11, remember it is Z parameter, so it will be ratio of voltage by current. So Z parameter is the ratio of voltage by current. So V by I, anyhow I know whenever I will write Z, Z will be ratio of voltage by current. That is for 100% sure, right? Now if I write here 1, this one is for the top, this one is for the bottom, right? This second one is for the bottom, the first one is for the numerator. Now I also remember that in Z parameter I had to open circuit something. In Z parameters I had to open circuit something, right? So I1 is already at the denominator. I cannot make I1 equal to 0. This will be undefined. So I will make I2 equal to 0. Similarly, you can write Z21, Z12, Z22. That's how you remember what is my Z11, Z21, Z12. Okay, that's how simple it is. That is basically your Z parameter. Okay, that's it. Now one thing is for Z, like for Z parameter, once you will solve few questions, mainly you will use Z parameters if you have to find out the Z parameters, right? You will use it when you are seeing that it is easier for us to use KVL in the input side and KVL in the output side. Whenever it is easy for us to use KVL, we will use Z parameters, or if the Z parameters is given, we will use, of course, Z parameters. Okay. Okay. We will also discuss when Z parameters exist or it does not exist as after finishing the admittance parameter. Okay. Okay, I will say it here itself that Z parameters, right, will exist only if the port currents are independent of each other. Here, right? What do I mean by independent? That I1 should not be equals to some x into I2. So basically, there should I1 and I2 should not be related with each other. They should be totally independent of each other, right? If they are not independent of each other, then your Z parameters will not exist, because your V1 will be only a function of I2 and your V2 will be only a function of I1. So I2, sorry. Then Z parameters will not exist. Why? We will see in the admittance parameter. Okay, in admittance parameter, it is just the opposite. It is basically the reciprocal of Z parameters. So if I have this matrix over here, this is my Z parameter matrix, right? Z parameter matrix. So what will be my admittance parameter matrix? Admittance parameter matrix will be inverse of Z parameter. That's it. Admittance parameter matrix will be inverse of Z parameter matrix. Okay, that's how simple it is. Now, in admittance parameter, what are my independent variables? So if you see the equation of admittance parameter, right? Previously, I wrote my voltages in terms of current. Now, what is admittance? Admittance is current upon voltage. So I will write my current in terms of voltage, just the dual of impedance parameter. So in this case, what are my dependent variables? Dependent meaning I1 depends on V1 and V2. So I1 will be a dependent variable. I2 also depends on V1 and V2. So I2 also is a dependent variable. That's why I have written here dependent variables are I1 and I2 and independent variables are V1 and V2. Now, again, for Y parameters to exist, V1 and V2 cannot be dependent on each other. So basically, we will see why is this the case. Why is this the case? Because if let's say V1 is some function x into V2, and what is my Y parameter? Y parameter is inverse of Z. Y parameter is inverse of Z. So if I have to find out inverse of Z, right? What is if V1 is some x V2, right? So what is my Z parameter? Z parameter is Z11 I1 plus Z12 I2. V2 is Z21 I1 plus Z22 I2, right? Now I will do one thing. Just let me just reduce the size over here. So I have told you that V1 is x into V2. So I will write here, right? So I will write here V1. This is, let's say, or let me write a number 3. So this is Z11 I1 plus Z12 I2, and this is 3V1 equals to Z21 I1 plus Z22 I2. Now the thing is, what happens over here? I can subtract these two equations, right? I have written here that my V1 is 3 Vx2, so I can subtract these two. There is no problem. If I subtract these two, I get 2V1 equals to Z21 minus Z11 into I1 plus Z22 minus Z12 into I2. Okay. Okay, just no, give me 1 second. No, this is not correct. So this is my 3V1. Okay, no, let me divide this by 3, right? Let me divide this by 3. So my V1 will be equals to Z21 by 3 into I1 plus Z22 by 3 into I2. Okay, so from this I can equate these two equations, right? So I can say that my Z11 is Z21 by 3, and I can say my Z22 is, sorry, Z12 is Z22 by 3. So now what I can do, again I can rewrite the matrix. Okay, so let me actually take a new page, that will be better, that will be best actually. Like what do I mean by dependent and independent variables? Here you will understand it in a better manner. So here, right, what we will do, we'll simply write the Z parameter matrix, right? So what will be the Z parameter matrix? Z11, Z12, Z21, Z22. But I know what is my Z11 equals to, right, in terms of Z22. So I can convert this as Z21 by 3, Z22 by 3. Just give me 1 second. Z22 by 3, Z21, Z22, this. So for calculating Y parameter, right, I need the Y matrix, that is simply Z inverse. So Z inverse will include adjoint of Z divided by the determinant of Z. Now what is the determinant here? The determinant is simply 0. So if the determinant is simply 0, Z parameter, Y parameter will not exist, because inverse will not exist, right? And if inverse does not exist, Y parameter will not exist. So basically it cannot happen. Okay, basically your independent variables cannot depend on each other. That's why the name independent. If they are related with each other, then your Y parameters will not exist. Same experiment you follow for Z parameters. Same experiment you follow for Z parameters, you will see your Z parameters will not exist if your I1 and I2 are dependent on each other. Okay, so I hope that part is clear only. So basically, but one thing is there, if I1 is only a function of I2, like this will happen, like here in this case, if V1 is only, V1 is function of only V2, or V2 is function of only V1, then only the parameters will not exist, otherwise they will exist. Okay, I hope this point is clear. I have proven it to you why they will not exist. How to calculate Y parameter? Same thing, right? You know the I, sorry, you know that it is an admittance parameter, right? So you have to find out the ratio between current and voltage. This time I will apply a current source, right? And also I'm making, what we used to do, we used to make this 0, right? So previously I was making I2 0. I2 0 mean open circuit, but here I'm making V2 0. V2 0 meaning short circuit. That's why these are also called as short circuit parameters. There I was making currents to be 0. That's why those were called open circuit parameters. Here I'm making voltage to be 0. That's why these are called short circuit parameters. Okay, I hope this part is clear. Okay, the relationship I have already discussed. What is the relationship between them? How, when they will exist or they will not exist. Okay, I have already discussed like how are they dependent. If they're linearly dependent, the inverse will be simply 0. Okay, yeah, these things I have already discussed. Now a little bit about reciprocity theorem. Okay, so I hope you have already studied what is reciprocity theorem. Reciprocity theorem states that if I am applying a voltage here, right, and I'm measuring the current excitation here, right, sorry, if I'm applying a excitation here in one port and I'm measuring the output in the other port, if I swap these two, right, if I swap these two, the ratio will remain same. The ratio will remain same. So basically, if I apply V1 here and I measure the current I2, the ratio of V1 by I2 will be same if I apply a voltage V2 here and measure the current I1. This ratio will be same. If this ratio is same, right, if this ratio of excitation upon the measured value, response, excitation upon response, the ratio of excitation upon response is same, then the network is said to be reciprocal. This you have been taught in network theorems. Okay, the ratio of excitation upon the response, there is a small video of reciprocity theorem by Himanshu sir, like it's like 1 hour video, you can watch that. So here there he have explained this reciprocity theorem very well. Okay, so that basically we check the excitation about the response ratio. If these two ratio are same across the two ports, that means the network is reciprocal. Now numerically, how can I say if a network is reciprocal or not? If their Z12 is equals to Z21, if for that particular two port network Z12 is equals to Z21, then the network is said to be reciprocal, or Y12 is equals to Y21, then also the network is said to be reciprocal. Okay, very easy to remember. Basically their Z12 must be equals to Z21, the transfer impedance must be equal, or the transfer admittance must be equal of each other, then the network is said to be reciprocal. Okay, one more key point, that if the network only contains RLC elements, network will be always reciprocal no matter what. If the network only contains linear RLC elements, network will be always reciprocal no matter what. If the network contains dependent sources, then also the network can be reciprocal, but we have to check. How will I check? I will find out the Z parameters. I will check whether these values are equal, whether the transfer impedance are equal, or whether the transfer admittance are equal of each other or not. Okay. Now symmetry. So symmetry meaning, if I cut the network into halves from middle, right, the network should be symmetrical from on the left hand side and the right hand side, like it will be mirror image about the center, right? So that is what we mean by symmetrical network. So a network is said to be symmetrical if their Z11 is equals to Z22, or their Y11 equals to Y22. Okay, basically their input impedance when the output is open circuit is equals to the output impedance when the input is open circuit. Basically Z11 equals to Z22, or Y11 equals to Y22. So these are actually important. So these conditions you need to remember. Okay, reciprocal and symmetricity. Now we will come to H parameters. So in case of H parameters, the independent variables are I1 V2 and the dependent variables are I2 V1. How will you remember? How will you remember it? So you will remember it like this, that we will start with Z parameter kind of thing, right? So in Z parameter, I wrote my V1 in terms of I1 and I2. We'll start with V1, then I will have here I1, right? But as if I write here I2, right, it will be same as Z parameter. So I cannot have here I1. So H parameter is somewhat similar to Z parameter, but not exactly. So V1 will be equals to I1 plus something into, can I write here I2? If I write here I2, this will be same as Z parameter. So I cannot write here I2. I need to write something else. So what is left? I2 is gone, V1, I1 is gone, only one variable is left. What is that variable? V2. So I will write here V2. So this will be simply my H parameter. So that's how you remember the H parameter. You don't remember it like this. You write the equation. So you, in your head, you understand, okay, H parameter is similar to Z parameter. So first I will write V1, then I will write I1. As soon as I will write I1, I will realize, okay, I cannot write here I2. If I write here I2, then this will be same as my Z parameter, but it is H parameter. So what variable is left? Okay, V2 is left. So I will write here V2. So once this is sorted, right, this also will be automatically sorted. H21, this will be same, right? This will not change. H22, V2. So what variable is left here? I2. Sorry, I1, right? Sorry, I2, yeah, I2. So I2 is left, so I will write here I2. So this is my H parameter, that's it. How to find out the H parameter? Simply again make V2 0. If you make V2 0, you will find out H11, V1 by A1, H21, I2 by A1, okay? Again, if you make I1 0, you will find out the ratio of V1 by V2, H12, you will find out the ratio I2 by V2, H22, okay? Yeah, that's how you find out the H parameter, that's it. So this is how you remember H parameters. And what are the conditions? Like G parameter is just the inverse of H parameter. So you find out G parameter and you take, sorry, you find out H parameter and you take the inverse, okay? No need to remember G parameter separately. If you want to, you can. So in first you write the H parameter equation, and then you realize, okay, these are my independent variables. In G parameter, this will be my dependent variables. In G parameter, my I1 and V2, if you see, I1 and V2 are my dependent variables, and V1 and I2 are my independent variables, okay? So that is my G parameter. Not that important. H parameter is the most important one. What are the conditions for reciprocity and symmetricity for H and G parameter? Okay, this also you have to remember. This also you have to remember. For reciprocity condition, your H parameter H12 must be equals to minus of H21. For the network to be reciprocal, H12 must be equals to minus of H21. For the network to be symmetrical, the determinant of the H parameter matrix must be equals to 1. Okay, same condition for G parameter. So these conditions are copied. Okay, here also I have written the Z parameter conditions for reciprocity and symmetricity respectively. Okay, now let's come to the last kind of parameter known as transmission line parameters. What are my transmission line parameters? So transmission line parameters are nothing but defining your input voltage and currents in terms of your output voltage and currents. Just one thing you have to keep in mind in transmission line is that this current is represented, the reference current of this direction is in this direction. That is the only difference in transmission parameters, because in transmission lines, right, what used to happen is the current, this is my input current, and the load side, the current should always come into the load, right? It should not come out of the load. So that is our reference direction. So what happens is, because it was mainly designed to define the transformers and stuff, that's why, and in the direction of I2 current in transformer is going out of the port, not coming into the port, right? So what we do is, what we did is, our current, this is my plus I2, right, normal 2-port parameter plus I2. What we did was, we agreed on the engineer's suggestion that okay, the direction of current will be this, but we just made this negative. So if I multiply a minus sign, the direction can be changed, right? So because the engineers told us, please make the direction of current on going into the load, so we change the direction by multiplying a negative sign. So in the equation, minus I2 will be there, not plus I2, minus I2 will be there, that's it. In the equation, minus I2 will be there, that's it, simply. Why? Because we just changed the direction. So I2 current, remember, is not coming into the port, it is going out of the port, going into the load side. Okay, so this is one thing that you have to keep in mind. How to remember the ABCD parameters? Very simple. You just write the input voltages and currents. Sorry, what is the input voltage and current? V1, I1. So I will write my input voltage and current in terms of my output voltage and current. So what is my output? Output voltage is V2. What is my output current? I2. What is my output voltage? V2, I2. Here there will be A. This will be minus, because I2 I have assumed to be in the opposite direction. Minus B. This is C. This is minus D. That's it. That's how you remember the ABCD parameter. How to calculate? Simply make I2 0. You will be able to find out A and C. Okay, ratio of V1 by V2 will give you A. Ratio of I1 by V2 will give you C when I2 is 0. And you will make V2 0, and you will find out B, that is minus of V1 by I2, and D, that is minus of I1 by I2. Okay, so that is what my A, B, C, D is equals to. Okay, so yeah, what about inverse hybrid parameters? Just the inverse, right? Now your variables will be flipped. Previously my V2 and I2 were independent variables. Now my V2 and I2 are dependent variables, and V1 and I1 are independent. So the input side is now fixed. Okay, so this time input side I have chosen the reference direction to be minus I1. So actually the current should always come into the ports, but here I have assumed current is going out of the port. That's why I have written minus of I1. That's it. Okay, that's it. Now what are the conditions of reciprocity and symmetricity? Just the opposite of each parameter. In each parameter, we know that the determinant of H equals to 1 means the network is symmetrical, but here the determinant of ABCD parameters means the network is reciprocal. And what is the condition for symmetricity? Your A will be equals to D. If your A is equals to D, that means the network is simply symmetrical. Same condition for inverse ABCD parameter. Okay, so these are the 6 conditions that you must remember. Out of this, only you have to remember 3, because the Y parameter is same as Z, the G parameter is same as H, the ABCD parameter is same as small ABCD or inverse ABCD parameter. Okay, so only these 3 actually which you have to remember: condition of reciprocity and symmetricity. Now let's come up to the interconnection of 2-port networks. I can interconnect different 2-port networks. If I interconnect different 2-port networks, what will be the modified H parameter, Z parameter, Y parameter, ABCD parameter? So if I connect 2 networks in series meaning, first this is my network, right? Some IA1 current is going, and then the same IA1 current is going into the other network, network B. Okay, so the two networks actually are connected in series, although it feels like they're in parallel, but no, the two networks are in series, because whatever current is incoming in this network, right, the same current is incoming in this network, right. So these two networks are in series. If the two networks are in series, then simply your Z parameters will be added. It is very simple to understand. If I have a impedance over here ZA, and if I have a impedance over here ZB, right, and the two networks are connected in series, two impedances are connected in series, so what is the equivalent impedance? ZA plus ZB. So same thing is happening, but in terms of network, if the networks are connected in series, then their overall Z parameter matrix will be simply added. I cannot comment about other matrices like Y parameter, H parameter, G parameter, but I can definitely comment that their overall Z parameter matrix will be simply added. Similarly, like I have proven it, you can see the proof. Similarly, if you see, if the two networks are connected in parallel meaning the whatever voltage I am applying, same voltage is across this network, same voltage is across this network. So the two networks are connected in parallel. If the two networks are connected in parallel, I hope you can guess, their Y parameters will be added. Their Y parameters will be added. How? So simply let's say if this is ZA, ZB, so what is the equivalent Z? So 1 by Z, right, will be equals to 1 by ZA plus 1 by ZB. What is 1 by Z? It is the equivalent admittance. And what is 1 by ZA? It is the admittance of A. 1 by ZB is admittance of V. So simply you can see that their admittances will be simply added if they are connected in parallel. So that's why the admittance matrix will be simply added. That's it. Now there are a few more connections, series, parallel, parallel series, not that helpful. Okay, you can also study, like you can search, like I have taught that in my full course. If I connect two networks in series parallel, then their H parameters will be added. If they are connected in parallel series, then their G parameters will be added, but you will not be able to remember that much. Okay, only these two are the important ones, and the last one, final one, this one is the most important. Please make sure you like at least understand this, okay, and remember this. So if two networks are connected in cascade, then their ABCD parameters will be multiplied. ABCD parameter of network A into ABCD parameter of network B will be simply multiplied. Okay, if two networks are connected in cascade, this will be very helpful to you. Okay, so very helpful. Like I have also derived the ABCD parameter for this simple network, right? I like it was ZA plus 1 by ZA, something like that. So remember, this is ZA and ZB. Remember the derivation of this ABCD parameters of this network. This will be immensely helpful in power systems and everywhere else. Okay, make sure you remember the impedance. Okay, so now let's solve few questions, and with this we'll wrap up our network analysis. So I will show you the question. This is the first one, second one, third one, fourth, fifth, sixth, 7, 8. Yeah, this is the last one, I guess. Yeah, 8, last one. So yeah, let's solve these questions. Let me drink a bit of water. So they are telling us that in the given circuit, the two-port network is shown, has the impedance matrix this, the value of ZL for which the maximum power is transferred to the load. The value of ZL, basically they are asking me, remember this is a real circuit, right? Here like I don't have any imaginary component, so ZL is nothing but RL, right? So simply what do I need to find out? I need to find out the Thevenin resistance seen from this port for maximum power transfer, because RL will, because when RL is equals to RTH, then maximum power is transferred. When RL is equals to RTH, then maximum power is transferred. So to find out Thevenin resistance, right, we have to nullify the voltage source. So I'll short this voltage source. If I short this voltage source, right, this is 10 ohm, and here I have this network, right? this is V1, this V2, and V2 is like I'm measuring the current from I2, so that I can find out this ratio V2 upon I2, that will be equals to my RTH, right? If I apply some voltage here and measure the current, that will give me the RTH value, because the ratio of voltage and by current will give me the Thevenin resistance seen from this point, and I have to obviously nullify the sources. So if I nullify, what is my V1? So remember, this is my port current, right? I1. This is my port current. So I will take a KVL on the input loop, and the Z parameters are given, that's why KVL I will do. So if I take a KVL in the input loop, so plus 10 into I1 plus V1 equals to 0. So my V1 equals to minus of 10 I1. V1 equals to minus of 10 I1. Okay. And the Z parameters are given to me actually. These are my Z parameters, right? So I can write down my Z parameters. V1 equals to Z11 I1. Z11 is 40 I1 plus Z22, Z12 that is 16 to I2, and V2 is equals to Z21 that is 60 into I1 plus Z22 that is 120 into I2. Okay. Now I already know that my V1 in terms of I1, right? So I will replace my V1 in terms of I1. So this will be minus 10 I1 will be equals to 40 I1 plus 60 I2. So I can easily find out my I1 in terms of I2, that I will replace over here. So I1 will be equals to, this will be minus 50. So that will go on that side. So 6 upon minus 6 upon 5 I2. Okay. So this, if I replace it over here, right, V2 will be equals to minus 6. So this is 12 into 6, that is minus 72 I1 plus 120 I2. So sorry, I2, right? I have replaced my I1 in terms of I2. So your I2 will be equals to, this will be 848. So yeah, for V2 by I2 will be 48 ohms. So that's it. That's how you simply find out the Thevenin impedance. V2 by I2 will be 48 ohms. This is my RTH and this will be my RL. This will be my answer. So what they will do, they will mix concepts, right? They will ask you for maximum power transfer as well as two-port networks. Okay, they try to mix the concepts. Let's solve the next one. Consider the two-port network shown in the figure. Okay, the two-port network is shown. The admittance parameters in Siemens are, what will be the admittance parameters in Siemens? So like this is a very straightforward portion of two-port networks. So we have to find out the admittance parameters. So individually, you can find out individually or you can directly find out. So whenever you have to find out admittance parameters, always remember you have to use KCL. If you had to find out impedance parameter, you will use KVL, right? So I will apply the KCL at the input node and I will apply the KCL at the output node. So if I apply the KCL at the input node, minus of I1 incoming current plus outgoing current V1 by 1, another incoming current is here, right? Minus of 3V2 plus V1 minus V2, right? V1 minus V2 divided by the resistance, that is 1, equals to 0. Okay. So your I1 is equals to 2V1 minus 2V1 minus 4V2. Okay. So this is my like y parameter. I can eliminate the options now. So this is my y11, y12. Y11 is 2, y12 is minus 4. 2 minus 4, 2 minus 4. Okay, okay, it is present in. I should have actually taken the output KVL, output KCL actually. So A, B, and sorry, A, C and D, all of them are matching. So now I have to check the output KCL. If I do the output KCL, this will be minus of I2 plus V2 by 1 plus V2 minus V1 divided by 1 plus only three questions I have. This is actually easier. This one is actually much easier than the previous one. Okay, so this will be I2 will be equals to minus of V1 plus 2V2. So Y21 will be minus 1, Y22 will be 2, Y21 will be minus 1, Y22 will be 2. So option C is the correct answer for this particular question. Very simple, right? Not that difficult. Just you have to simply write the output KCL and the input KCL. If you have to find out Z parameter, you write the input KVL and the output KVL. Okay, let's solve this next one. This one is actually a pretty good question. I think this this question we have taken in our test series as well. So we have this linear two-port network shown. Ideal voltage source is there, and a variable resistor is there. As the R is varied, the voltage is measured across port 2. Voltage and current is voltage and current are measured. Okay, is shown. This voltage is shown and the current, like variation of current, is shown, right? As the R is varied. Figure B. In figure B, as V2 versus I2 minus I2. Remember minus I2 because like for a resistor, right? For a resistor, current can only come into the positive terminal because it will always dissipate power. That's why we have plotted it with respect to minus I2. Note, for V2 equals to 5 volts, I2 is 0, and V2 equals to 4 volts, I2 is minus 4 milliampere. When the variable resistance R at the port 2 is replaced by this load shown, the value of the current I2 will be, what will be the value of the current? So if I change this variable resistor with this load, what will be the current I2? They are asking me what is the current I2. Remember, current I2 is incoming, so don't mess up with the direction. So here what do I see is that, what can I say? Okay, so when the current is 0, voltage is 5, that is basically the open circuit voltage, right? Open circuit voltage VTH across this port. So I can replace this whole network with its Thevenin equivalent. So if when R is infinity, then only the current will be 0. So when R is infinity, current is 0, that means it is the open circuit voltage, and open circuit voltage is given to me, that is 5 volts. I just need to find out the Thevenin impedance. I just need to find out the Thevenin impedance RTH, so that I can replace this whole network with its equivalent RTH and VTH. So I'm observing that if I'm varying my R, right, R is, if my this V2 is if I'm increasing my R, then this V2, when this V2 is 4 volts, current is 4 milliamperes. Okay, so I can replace my source, right? This is my VTH, this is my RTH, and this is my load RL, right? So what is the current? Current minus of I2 actually, but I will write here IX current. So IX current will be VTH upon RTH plus RX. So from this graph, can I find out my RTH? Yes, because I know the current here, I know the volt. Okay, so when the voltage is 4, the current is 4 milliamperes, right? So I can easily say, at this condition, when the voltage is 4, I know VTH I know already, right? VTH is 5, and what is my current at this condition? So when V2 is 4 volts, current is 4 milliampere. So what is the resistance Rx? So Rx will be simply V2 by I2, right? V2 by I2 is how much? 1 kilo ohms. So when the resistance Rx is 1 kilo ohms, the current Ix is supposed to be 4 milliamperes, right? That is given to me, because resistance will be simply voltage upon voltage across the resistor divided by the current, right? So I will replace these values. Rx I will replace here, Ix I will replace. I will be able to find out my RTH. So my Ix will be 4 milliamperes. I will write in milli only because the denominator is in kilo. RTH is also in kilo. Rx is also in kilo. That is 1 kilo, right? 1. So from this, my RTH will come out to be 1.25, 0.25 kilo ohms, or RTH will come out to be 250 ohms. So I got my RTH value. Now simply what I will do, I will just solve the circuit. So I got my VTH, that is 5 volts. I got my RTH, that is 250 ohms, right? And I am connecting a new load that is of 1 kilo ohm, and the voltage is 10 volts. And I have to find out this current, right? That is leaving, coming into the port. This is my port 2, right? V2. Remember, this is my port 2. I have to find out I2. They have asked me to find out I2. Remember the direction of the current I2. So I can simply find out the current I2. What will be I2? I2 will be 10 minus 5 divided by 1.25. So it will be 5 divided by 1.25. In milliampere, they are asking me to calculate, right? This is in kilo, right? This is in kilo, and they are asking me to calculate in milliampere. So automatically this will be already in milli, right? So this will be 4 milliampere. This will be the answer of this question. Very elegant question. Okay, very elegant question, but bit tricky. Very simple but bit tricky question. Okay, let's now solve the next one. So yeah, let's come to the next question. So again, this is a gate double E question. So where we have been given the admittance parameters for the two-port network, what will be the power delivered to the RL network? Okay, this resistive network admittance parameter is given to us. Okay, how will I calculate this? So it is a resistive two-port network, right? Okay. So this V1, right, is same as this voltage, and this V2 is same as this voltage across the resistor. So if somehow I am able to find this V2, my job is done. Okay, so I need to find out this V2, right? That is my job. My job is to find out V2. So the current incoming I1 is not same as this current. This current, let's say, is some current I source current, right? And this current will be Is minus I1, and here Is minus I1 will be incoming, and this current will be I2, the port current. So this current will be what? This current will be Is minus I1 minus I2. Okay, so now it is sorted. Now I think we can do something with this. So I will first of all write the y parameter equation. So what are the y parameter equation? So y11 is given to me, right? Y11 is 5. So my I1 will be equals to y11, that is 5 into V1. This is my V1, correct? And this is my V2, plus y12. Y12 is y12 is equals to y21, that is minus 2.5. So minus 2.5. So this will be minus 2.5 V2. I2 will be minus 2.5 V1 plus y22. Y22 is 1, that is plus V2. Okay, plus V2. Okay, so these are my I1, I2. Now if I now what shall I do? Okay, I need to find out my, so one more thing, my V1, right? My V1 is 20 volts, right? V1 is 20, right? Correct? V1 is 20. Okay, one more thing, can I write this Is? Can I write this Is? Yes, I can write this Is. What will be Is? Is actually will be equals to this V1, that is 20, minus V2 divided by, or let me write this properly, V1 minus V2 divided by 3, right? That is what my Is current is equals to. So I can write my V2 in terms of is, I1 and I2, correct? So my V2 will be what? V2 will be, this will be a bit lengthy actually. uh, V2 will be equals to, okay, give me 1 second. So V1 is 20, okay, V1 is 20, so this is gone. 20 minus V2 by 3, 20 minus V2 by 3, is 20 minus V2 by 3, this is done. Okay, what else do I need to find out? Is I have replaced, I have to replace, okay. hmm. Okay. So one thing I can do, what is the current through this resistor? IL. It is is minus I1 minus I2. So if I take the minus sign common, it is is plus I1 plus I2. So what I will do, I will add these two equations. That will give me I1 plus I2. Okay, and V1 is already 20. That is known to me, and I know what is is. So I can replace all these things, right, in terms of V2. But will that help me to find out V2? That is the purpose, right? To find out V2. How will I find out V2? So finding out I1, will it help me? No, actually it will not help me much. Oh, sorry, this is not is current, right? Sorry. This is not is, this is is minus I1. What am I doing? Sorry. This current is here, this current is V1, that is 20 minus V2 by 3. Okay, this current is 20 minus V2 by 3. This current will be how much? This current will be 20 minus V2 by 3 minus of I2. Okay. Yeah, now finally I think we're getting onto something. So what is this V2 voltage? V2 voltage is basically 20 minus V2 divided by 3 minus I2 into the load resistance RL, that is 6. So I can replace my V2 over here, right? I can replace this V2, sorry, I can replace my, I can write my I2 in terms of V2. So this will be V2 divided by 6, right? V2 divided by 6 equals to 20 divided by 3 minus V2 divided by 3 minus I2. So this will be, okay, I can write my I2 in terms of V2, right? I2 will be equals to 20 divided by 3 minus, okay, 6. Okay, this will be 20 divided by 3. This will be 2. So minus of V2 divided by 2. Yes. Okay. So I can replace my I2 in this equation, correct? So this will be V1 is 20, V1 is 20, right? V1 is 20. So this will be 20 divided by 3 minus 2.5, 2.5 into 20. So this will be minus 50 plus V2. V2 is, sorry, okay, sorry, what am I doing? So I2 is plus V2, I2 is 20 divided by 3 minus V2 divided by 2, and this is minus 50 plus V2. So from here my V2 comes out to be, this will be 170 by 3, this will be 3 by 2 V2. Okay, so my V2 will come out to be, I can calculate my V2 here. This will be 170 into 2 divided by 9, so 37.78. So the power dissipated in the resistor will be V2 whole square, because the voltage across the resistor is V2 upon RL, right? So V2 whole square upon RL. Okay, am I doing this correctly? Sorry, this will be, sorry, yeah, this is correct, So this whole square divided by RL is 6 ohms. So this whole square divided by 6. So 237.86 watts. This will be the answer for this question. This was bit calculative. I do agree. This was a bit calculative question, but we got there at the end. Okay. So these kind of whenever the calculation is going higher, you will solve this in the round 3. Okay. So yeah, for the two-port network shown below, the Y parameter is given as this value. Okay, Y parameter is given for the two-port network shown. We have to find out the value of load impedance ZL for maximum power transfer. Same thing, right? We just have to find out the Thevenin impedance from this point, right? So to find out the Thevenin impedance, first of all, we have to nullify the sources and we have to take the ratio of V2 upon I2, right? So I will write my equation, Y parameter equation. So Y parameter equation is I1 will be equals to Y11 into V1. So Y11 into V1, that is 1 upon 50 into V1, 1 upon 50 into V1 minus minus V2 divided by 100, minus V2 divided by 100, and my I2 equals to minus V1 divided by minus V1 divided by 100 plus this is 100 times this, right? So this will be 1 by 75 into V2. So I've just multiplied this, right? That's it. Okay. 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 So what about the input side? Input side, if I nullify this source, right? If I nullify this source, this is my input port current I1. Okay. So I can write my V1 as, remember, the voltage drop is like this, 10 I1, right? So this will be minus of 10 I1 because V1 is like this, right? So it is negative basically. So this will be minus of 10 I1. Okay, V1 is minus of 10 I1. So that is what my voltage is, V1, right? So I can replace this V1 up here. So if I replace this V1, so I will get I1 will be equals to minus of I1 by 5 minus V2 by 100. Okay, so I1 will be equals to minus I1 by 5, V2 by 100. So from here I can get the value of I1. Or do I need the value of I1? Oh no, I don't need the oh no. Oh, actually no, I have replaced the wrong thing. I have to replace I1 in terms of V1 actually, because I have to replace here V1, right, in terms of V2. That's why. So I1 will be equals to minus V1 by 10. So I will place here minus V1 by 10. So this will be minus V1 by 10 equals to V1 by 50 minus V2 by 100. So this will go on that side. V2 by 100 will be equals to, this is 5, so 6 V1 by 50. Okay, so my V1 actually is equals to V2 by 12. So I will replace my V1 in this equation, right? So this will be, ultimately I have to find out the ratio of V2 upon I2, right? That will give me the RTH. This is gone. I'm just finding out the ratio of V2 upon I2 to find out the RTH. That's it. Okay. So this will be, I2 will be equals to minus of V1. So two-port network is nothing but calculation. That's it. Two-port network is nothing but calculation. So minus of V1, right? Minus of V1, that is minus of V2 upon 12, that is minus V2 upon 1200 plus V2 upon 75. That is actually coming out to be quite large. Okay, let me, okay, so 75 is this even a ratio? So 1 divided by 75 minus minus 1 divided by 1200 plus 1 divided by 75. Yeah. So this ratio is coming out to be V2 upon I2 is coming out to be 80 ohms. So this is your RTH and this will be your load impedance because it is a DC network, right? Completely real elements. So this will be my Thevenin, like maximum for maximum power transfer. This has to be my load impedance 80 ohms. This will be my answer for the question. Okay. So I think few more questions are left. Yeah, this question is left. Okay. So here what are they telling us that the H parameters of the two-port network are shown for the condition of maximum small signal voltage gain, that is V out upon Vs. What shall be the condition? So what are my H parameters? Do you remember what are my H parameters? So this is nothing but a H parameter network. Okay. So if you apply the input KVL, right? If you apply the input KVL, what will I see? It will be minus of Vs, that is simply minus of V1. Okay. So few things I will change. My V1 is equals to Vs, right? V1 is equals to Vs, same voltage, right? V1 is equals to Vs. So V1 is equals to Vs, and one more thing is there, that my V2 is equals to V out. V2 is equals to V out. Only this is what I will change. Okay. Other things I will keep as it is. So V1 equals to Vs and V2 is equals to V out. So if I apply the KVL, this will be remember this is just a impedance, right? So Vs is minus Vs plus H11 into H11 into I1 plus H12 into V2. Now V2 is V out, right? So this will be H12 into V out equals to 0. So I want my Vs by V out ratio to be highest, right? So my okay, I have to somehow eliminate this I1. I have to somehow eliminate this I1. I will eliminate this I1 in the next equation here, right? Here I will eliminate. I will try to eliminate. I will do my best. Okay. So if I apply the KCL at the output side, what is the KCL? The KCL is simply V out over RL plus V out by H22 and plus H21 into V1, okay, plus H21 into V1. This equals to 0, right? Okay. And V1 is simply V in, right? V1 is simply V in, and I1 is also there, right? Okay, I1 is not there. Okay. This I2 current is nothing but this V out by H21, So your V out over V in, right? Basically these two are in parallel, correct? So it is RL parallel with H22, okay, 1 by RL parallel with H22 equals to minus of H21 into V in. So your V out by V in, have they included the negative sign as well? No, is equals to minus of H21 into RL parallel with H22. Okay, that is what your V out by V in is equals to, right? If I am not mistaken here, everything is correct, right? I2 H22 V out, V out by RL, V out by H22. I think, okay, what is my H22? Do you remember what is the unit of H22? So let me write the H parameters, right? If I write the H parameters, in H parameters it is similar to Z parameter. So V1 equals to H11 I1 here it will be V2, it cannot be exactly equal, so this will be H1 to V2, okay, H1 to V2, and this will be I2 equals to H21 I1 plus H2 to V2, okay, that is fine. Okay, this H22 is actually the admittance, this is not the impedance, this is the admittance, right, because it is the ratio of I2 over V2, right, when my I1 is 0. So this is actually, I'm sorry, this is not, okay, this is not impedance, this is admittance, so this will be directly multiplied here, this will be directly multiplied, H22 will be multiplied, okay, that is wrong. So this will be actually RL parallel with H22, or I can keep it as it is. So basically this will be 1 by RL plus H22, or this will be H21 is what? H21 is this, right? Yeah. Yeah, H2 is just a, have they messed up something? I think there is something wrong. This should be I1, I guess. This is wrong. There is a printing mistake. The H parameters of the two-port network are shown below. This model is wrong. This should not be V1. Here if I see, it is H21 into V2. This is correct. This is H11 into I1. This is correct. But this is wrong. This should be I1 actually. This is incorrect. This is I1. Yeah, that is what I was thinking. There is a printing mistake here. This should be I1. Okay. So I think they gave empty or something. I guess this should be I1. So if this is I1, right? Okay. So what is my I1 equals to? From here, what is my I1 equals to? So I1 is equals to Vs minus H12 VO by H11. Okay. And this, right, will not be V in simply. This will be I1, right? This will be H21 into I1. Here this should be I1. There is a printing mistake. The expression will not be that simple. So this will be actually I1 is Vs minus H12 VO by H11. Okay. So now finally you can come to the voltage gain basically. So the voltage gain, right? Let me simplify this. So your VO will be 1 by RL plus H22 minus H21 H12 divided by H11 equals to minus of H22 divided by H11 into Vs. So I want this ratio to be maximum. I want this ratio to be maximum. So what they're telling us, so this, right, I want my ratio to be maximum. So of course the numerator must be very high, right, because VO upon Vs, H21 is coming at the numerator, so this has to be very high. So H21 has to be very high, H21 is very high, H21 is very high, H21 very okay, H21 is very high, it is present in all the options. But what about other one? H11 0, H12 0, H22 0. Okay, so if H11 is 0, H11 is 0, so this, okay, I cannot make H11 0, right, otherwise this will be undefined. I cannot make H11 to be 0, this will be undefined, right? H11 cannot be 0, H11 cannot be 0. Okay, so H11 cannot be 0. H11 can be very high. If H11 is very high, no, this ratio will come down, right? That is also bad. No, H11 cannot be very high. Okay, actually this, all the options are incorrect. Okay, I remember now. In GATE exam, this question came as empty. First of all, they here wrote this wrong. Okay, and even if they wrote this wrong, can I make H11 0? Actually, so yeah, you can make, actually if you multiply by H11 can be very low. It cannot be 0. If I multiply by H11 on both sides, right, this will be what? This will be VO H11 by R2 plus H22 into H11 minus minus H21 H12 equals to minus of H21. Okay, minus of H21 Vs. Now what will happen if your H11 is very low, then this will go away, right? This will also be almost very small. So this is going in the denominator. So the denominator is reducing, right? If your H11 is very small and if your H21 is very high, your numerator is increasing. So the ratio will increase. So your H11 must be very low. Same, your H22 also must be very low. Very low. Your H21 must be very high. H21 must be very high. Okay, what about your H12? H12 also will be, H12 can be anything, I don't know, I don't care. H12 can be anything. Okay, but these are the values actually. So according to this, option A will actually match. Okay, but like it cannot be exactly 0. If it is 0, then like all this does not exist, right? So option A kind of matches, but there the printing mistake was there anyways. And first of all, it cannot be exactly 0. It will be very low value. Just like it is H21 is very high, it has to be very low value. That's it. Okay. So yeah, we have one more question left, two more questions left actually. This is the second last question. So here we have been given a two-port network, passive network. These are both are passive network. The Z parameter impedance matrix of network P and the admittance matrix is shown. Let the ABCD matrix of the two-port network is two-port network of this whole combination of network is beta. Then is alpha, beta, gamma, delta. Then what is the value of beta? So if they are asking me to find out the value of beta, right, you actually don't use that property. What is the property? That you find out the ABCD of ABCD of P network, you find out the ABCD of Q network, then multiply these two networks, right, and then ultimately find out the ABCD of the whole network, that is R. Yes, you can, this property is very helpful, but when you have to find out the ABCD parameter of the whole network, then only, because if you see, these are not my ABCD parameters, so they have not given me ABCD parameters. So if they have not given me ABCD parameters, so what do I need to do? First I have to convert these into ABCD parameters, then I can apply this equation, and from there I will be able to find out beta. But as they are only asking me one particular parameter beta, so I will apply that condition in this network and find it out. I will apply the condition in the network and find it out. So I have to find out the ABCD parameter of this whole network. So let me name this as V1, V2. This will be minus of I2. This, let's say, is some input current minus of, or let me name this current as IP, and this current is as IQ, input current, right, IQ, and this voltage as VP, and this voltage as VQ. Okay. So first of all, let me write the ABCD parameter. So V1, I write my input parameters in terms of output, right, equals to A. In this case, A is alpha. So V1 equals to alpha into V2 minus of beta into I2, and I1 is equals to gamma into V2 minus of delta into, just give me 1 second now. Delta into I2. Okay, so I need to find out beta. So what is beta? Beta is nothing, V1 upon I2 when V2 is 0 basically. So I have to make V2 0. I have to short circuit V2, right? And I have to find out the ratio of the input voltage V1 and the output current I2. That's it. Minus. Don't forget the negative sign. Okay. So I have to actually do this. So let me write down the Z parameters, because the Z parameter for network P is given, right? So what is the Z parameter? Or let me start off with Q. network Q. The Y parameters are given, right? So for network Q, this is the input current IQ, that is equals to Y11. Y11 is 5 into the input voltage, that is VQ, minus Y12, so it is minus 2.5 into the output voltage. Now what is the output voltage? V2. And what is the output current? I2, right? Because this current is supposed to be incoming, I2. So I2 is equals to Y21, that is minus 2.5, minus 2.5 plus V2. Okay. So in our case, V2 is 0. So we will make it 0. So we will make V2 0. So if V2 is 0, IQ is simply equals to 5 into VQ, and I2 is equals to minus 2.5 into VQ. So actually I got the value of I2, right? What is value of I2? Because I need to find out I2. I2 is minus 2.5 VQ. And what is VQ? VQ is IQ by 5, right? So I will replace it over here. So IQ by 5, this will be actually minus IQ by 2. So I2 is actually equals to minus IQ by 2. Now I will use the Z parameter. So what is the Z parameter? So V1 will be equals to I1 for network P. V1 will be equals to Z11, that is 40 into I1 plus 60 into 60 into the current. What is the current? IP into current IP, and V2 will be equals to 80 into I1. No, not V2, sorry. This is not V2, this is VP voltage, right? Port 2 is VT for this network P. So this is VP is equals to 80 into I1 plus 100 into IP. 100 into IPS. Now the interesting fact is this IP, like if I apply the KCL here, right? IP plus IQ equals to 0 if I apply the KCL at this node. So my IP is actually minus of IQ. IP is minus of IQ. So I can replace my IP over here. And do I know my V1? Okay, V1 is simply, okay, I have, yeah, because what do I need to find out? I need to find out the ratio of V1 by I2, right? So I will use this equation because I need to write V1 in terms of my IP. So V1, okay, so hold on a second. Okay, one more thing is there, and VP and VQ are same, right? VP and VQ are same. VP is equals to VQ. So I can replace this VP, right, with VQ. So this will be actually VQ equals to 80 I1 plus 100 into IP. IP is minus IQ. So this will be minus IQ. Okay. And what is my VQ? VQ is actually IQ by 5, right? VQ is IQ by 5. So this will be actually very weird value. I'm getting a very weird value actually. So VQ will be IQ by 5. So IQ by 5, right? So this will be IQ into 100 plus 1 by 5. So this is like 501 divided by 5 equals to 80 I1. That is what my IQ is equals to in terms of, that is what my, yeah, I1 is equals to, right? So this will be, I1 will be what? I1 will be 80 into 5, 501 divided by 400. Okay, IQ is equals to 501 divided by 400. Okay, so yeah, that is my current. uh, okay, so this is becoming lengthy. So my V1 equals to I1 is this value, right? So I'll replace I1. This will be 540 into this, right? 501 divided by 10 into I1, so into IQ, and plus IP is minus of IQ, right? So this will be 60 minus of IQ. IP is minus of IQ. So this will come out, V1 will be equals to okay, quite complicated, 50, right? So this is 50 minus 60, so approximately minus 10, but they are asking me the exact values, so I have to calculate. So this will be 500 and so 50.1 minus 60, right? So this will be 9.9. 60 plus 50.1, 9.9, yeah. So minus 9.9 IQ. And what is my IQ? IQ is minus of 2 I2. So if I will multiply this by 2, so my V1 will be equals to 19.8 into I2, because IQ is this, and I have to find out the ratio of V1 by I2, right? This will be simply 19.8. That is what I have to find out. That is my beta, right? When my, remember, when my V2 was equals to 0. So that's how you solve this question. Okay. Somewhere I have made a mess up. This, okay, this will go on that side. This will be plus. This will be plus. This is plus. IQ is minus, because the answer is coming out to be negative, but according to me it should be positive. Where am I messing up? EQ is IQ by 5. Messed up somewhere with the sign. Okay, beta is negative of this, right? Beta is negative, don't forget the negative sign. So V2 by I2 is plus, right? But I have to find out negative of this, so don't mess up. You will solve this much, right? And you will mess up. Okay, beta is minus V2 by V1 by I2. So I do understand, like this happens with me as well. You cannot eliminate this, right? Beta will be minus V1 by I2. So this will be negative of this, that is minus 19.8. Just be very, very careful, right? Don't forget the negative sign. Don't forget the negative sign. Okay, so this will be my answer. Okay, I am also messing up because I know the answer already. That's why I was able to rectify. But in exam hall, you will never know. Okay, this is actually a good question. Let's solve this last question. So for the two-port network shown, the value of y21 will be what? Very simple. You have to just find out y21. What is y21? How to remember? Y parameter, right? So it will be a ratio of current and voltage. 2 will come at the numerator. Denominator 1 will come. So V1 cannot be 0. So V2 has to be 0. So I will make the V2 0. So V2 0 meaning I will short circuit this port, and I will find out the ratio of I2 upon V1. So I am applying a voltage here, right? Applying a voltage here, I have to measure the current I2. So what will be the current I2? So this is 0, right? This is 0. So from here, if I1 current is coming, this current is what? This current is I1 plus I2, right? So I can simply apply a KVL in this loop. Is that beneficial? What is my I1 actually? So I1, right? This I1 current is this volt, like this voltage is 0. This is shorted, right? This voltage is 0 automatically. So it is V1 upon 2. V1 upon 2. So I got my I1 value. So this is V1 upon 2, right? V1 upon 2. Now I think it will be beneficial for us, or let me keep it I1 only. So if I apply a KVL in this loop, right? This loop will be what? Okay, this voltage is actually V1 only, right? This whole voltage is V1. Okay, I can apply a KVL in this loop actually. That will be simpler. Or okay, let me keep I1 as it is. So if I apply a KVL in this loop, this will be minus of V1 plus 2 into I1 plus 4 into I1 plus I2 minus 8 V1 will be equals to 0. Okay. So this will be okay. So this will be cancelled, right? This will be automatically cancelled, and this will be 4 4i1, I1 is v1 by 2, right? So this will be actually 2v1 plus 4i2 minus 8v1 equals to 0, or I can say that 6v1 will be equals to 4i2, or what do I have to find out? I2 by v1, right? So I2 by v1 will be 1.5. Okay, so 1.5 will be the answer for this particular question. Pretty simple, straightforward. Just you have to find out the y21. Okay, 1.5 will be the answer for this particular question. So with that, we have ended our R-PYQ. So if you are feeling bit confident, bit okay with this all revision, if you enjoyed this video, make sure to hit the like button, comment down below which things you enjoyed the most, and if you are feeling a bit confident, like my task will be done. Basically, you have to just be a bit confident, and it's okay if you are not able to solve all the questions, because in GATE exam also you don't have to solve 100% of the question, you have to solve 70% of the question. To get a good rank, you have to solve 70% of the question, and you will be good to go. So we have done enough practice. With this, I will end this video, and yeah, I will see you in another video. Until then, happy learning.